Yeah, sure. If somebody else needs it, I'll have it right there. Thanks. I'm not a session leader. Yeah. I'm not sure. Are you speaking? Yeah. Do you want to use a clip-on mic or do you want to be at the podium?
Are you speaking?
There you go.
Do you like to read it?
Okay. Do you need your slide? Correct. Yes. Yes. So, okay. So I don't. I'm not.
Unless you want me to do it for you.
Did you upload the slides? Your slides to the Indigo? I need to bring them in. Okay, let me see. Need to bring them. Okay. So which one is yours? Yeah, right. So I need to probably go to LPC site to download. Do I need to log in? I don't remember. Do you have your slides? You uploaded to Indigo. Okay, let me see. Okay. I think this is where I can get them from. I haven't done this before. So. It's another room. We need to go to the right room. Okay, I'll go to the refrigerator. Okay. Over there, we should find. Yes. Okay, that's the one that we want. Yeah, that's what I'm looking. I'm having trouble too. Scrolling. Come on, why doesn't it scroll? Okay, gotcha. Okay. So presentation materials, we will bring this. Maybe I need to do save as here. Okay. Save and then I can bring it from the other one. Oh, I probably have to do all this for everybody. Not very good. I mean, yeah, it shouldn't. So yours is, which one is this now? Presentation, did we get it? Downloads. Just downloaded it. Now we should be able to bring that up now. That one? Okay. Upload. All right. Now you can pick presentation and confirm. Okay.
Yeah.
Yes.
Second, I just want to make sure I can switch slides. Perfect. Yeah, so good morning, everyone. My name is Alexander. I'm from Google, and today I'm going to talk about syzbot. After a short introduction, I'll share some interesting statistics that we have accumulated over 7 years of syzbot operation. Then I'll share some updates that have been on syzbot over the last year. And towards the end, we'll revisit some controversial topics about syzbot operation. This year, there have been quite a few hot discussions on mailing lists. Okay. So there's actually a distinction between syscaller and syzbot. Syscaller is a standalone coverage-guided kernel fuzzing tool. Well, syzbot, on the other hand, is a continuous kernel fuzzing system that periodically checks out latest kernel revisions, builds them, fuzzes them, aggregates the reports, and sends them to kernel developers. Syzbot uses syscaller for the actual fuzzing. And since 2017, syzbot has detected more than 17,000 findings in the Linux kernel and reported more than 6,000 of them to the Linux kernel mailing lists. So far, more than 3,400 Linux kernel commits directly mention syzbot, and on our web dashboard, we have recorded more than 4,800 resolved findings. So I think you might have seen our reports to mailing lists that look like this. We include information on the tree where the issue was detected. We include reproducers, console output, some VM Linux, kernel image, whatever might be helpful for you to understand the nature of the problem. And we also have a web dashboard that you can access at syscaller.appspot.com. We display all our findings there, and for every finding, we display information about every time we have hit it during fuzzing. So for every particular kernel crash, you can also see kernel configurations, kernel revisions, console log, reproducers if they're present, and all other data. On syzbot, we have 25 syscaller instances that cover different combinations of platforms and kernel trees. We fuzz on native ARM64 and x86 emulation virtual machines on Google Cloud. We fuzz on emulated and KVM-powered QEMU instances. And every year, we've been reporting roughly the same number of new findings in the kernel, roughly 1,000 per year. For every finding, syzbot tries to find a reproducer, though it's not always feasible, but 64% of all reported findings had a reproducer. Cause bisection is more tricky, so we managed to find it only for 23% of the findings that we reported in the mailing lists. And syzbot also provides batch testing functionality. That is, you can ask syzbot to build kernel at the specified revision and run reproducer against it. Optionally, it can also apply an arbitrary patch before building the kernel. The number of patch test requests that we have served is growing, and this year we expect no time maximum. Okay, let's look at what our accumulated data says and why some syzbot findings are addressed and some are not. Now, this graph shows the distribution of statuses of the reported findings over time since their reporting. Green area are the findings that have been addressed. And as you see, the share of addressed findings rapidly grows until 50th day or something. Then the growth slows down. Also, of course, not all findings that we reported fixed only because we reported them. So we cannot really track all their state. So we have an auto-obsolescence mechanism that kicks in to remove stale reports from our web dashboard. And as you see, it's colored in orange, I think. And the share also grows over time. And by the end of the first year after publication, around 20% of reports remain unaddressed. Okay, let's formulate a problem like this. Suppose there is a mapping from various report factors to a simple Boolean verdict, whether the report was addressed within 45 days or not. Then we can apply some commonly used mathematical approaches to analyze it. 45 days is just a convenient figure. Almost all reports that are ever addressed are addressed within 45 days, and automatic backup solution has not yet come into effect. And using the data on our reports to public mailing lists over last years, and applying both mutual information and chi-square approaches, we get this ranking of features. They give the same results. The most important predictor of whether an issue is to be addressed is the affected kernel subsystem. So yeah, to avoid any controversy, I will not mention any specific subsystems here. Surprisingly, a very important predictor is the average daily number of times we hit crash during fuzzing on syzbot. Then comes existence of a cause bisection, report time. There's characteristics of the moment when we did report the problem, and the existence of reproducer. So it was pretty surprising to find such a strong correlation between the number of times we hit the issue during fuzzing and how likely it is to be resolved. But it is. And it's not explainable by higher rates of reproducers or cause bisections for issues that we hit more often. Maybe if we can hit it so easily, other developers also can, and it boosts priority for these issues, or these are just more easier to fix than those that appear more rare. I can only speculate. Another surprising insight. the question.
So just a short comment regarding this. So for example, if syzbot is sending, these summaries of syzbot reported bugs, like per subsystem monthly, then, it's also sorted by the number of occurrences actually. So, and like for my personal, if I see syzbot is hitting like this 10,000 times a month, then I think, okay, maybe that will be something which is relatively easy to tackle. So let's fix this. So I guess it's kind of natural that actually the problems that are hit really frequently get more attention, and so they get fixed earlier. And also the reproduction is also kind of the point, because if you hit it so easily, then it's very likely other people are able to reproduce it.
Statistically, I did not notice any big correlation between share of reproducers and number of.
Well, the fact that you have a reproducer and share it doesn't mean that the maintainer is able to reproduce it on his setup. But it's when it is very easy for you to hit it, then likely even like some different setup is able to hit it. So I guess also making a difference.
Thank you. That's a very interesting point. Okay, so another surprising insight was how much cost bisection is more important than reproducer. Reproducer is important, but it brings the probability that the issue will be addressed from 14 to 19%, while existence of a cost bisection makes it 39%. And of course, the report type also makes a difference. UBSAN general protection fault reports are 3 times more likely to get addressed as info task HAN, which is, I think, expected. Okay, let's look at the notable changes over the last year. So we have put time into improving cost bisection quality. And as a result, now we serve more cost bisections. We used to serve around 20%. Now it's 40% of reported findings have a cost bisection result. And bisections have become more precise. But in general, it of course remains a very, very challenging process, especially if you do it automatically. And there are many reasons for that. For example, many kernel versions simply do not build or boot with syzbot config. So we have to cherry pick fixed commits for a number of known failures. Now we also do partial config minimization to reduce the risk of triggering not related crashes, not related build and boot failures. Another problem that bug reproducers are unfortunately not always 100% reliable. And the reliability may depend on how far back we are into the commit history. To somehow counter that, we now try to estimate the accumulated error probability by looking at every bisection step, we run 10 to 20 virtual machines. And by measuring how many of them crashed or not crashed, we can try to estimate our chances of having made an error. And we don't report bisections that are likely to be invalid. And maybe stochastic hit bisections could somewhat help here, but we do not have them yet. Another problem is that single reproducer might trigger several unrelated bugs. And for that, I'm not sure there's any automatic solution at this point. To minimize the risk, we do conflict minimization, we drop unnecessary instrumentation, we ignore some obviously unrelated crashes, and it somewhat helps, but not in all cases. And last big problem is that some commits do not introduce the bug, but they surface it by adding an assertion or by changing the execution path. And bisecting for that problem inevitably points to that commit, and technically the result is correct, but it's useless. And here I'm not sure automation can ever help us. So we have to assume some risk of false positives. The next new feature is that on our web dashboard, we now aggregate all the discussions related to the finding on the mailing list. These include both discussions under our report and all batch series attempts. Hopefully, it should minimize the duplication of work. And this year, we have begun to automatically assign subsystem labels to our findings. You might also have noticed it. We included it in email subjects, and we show it on the web dashboard where you can filter by these tags. If you want to see findings in a subsystem of your interest, you can navigate to our web dashboard. You need to click on the subsystem button, just like the arrow shows you. And you will see a page with the subsystems and number of open and fixed findings for them. If you click on any of those links, you will see a per subsystem page. It includes some statistics, general information, and a list of all related findings. As I mentioned, we auto obsolete findings that are no longer happening, so hopefully this should all be relevant. And it was actually not so easy to obtain the list of subsystems. There is maintainers file that contains very relevant information, but it's very big, almost 3,000 entries, and it has very long titles. It's not the medium-sized list of tag-like names we were looking for. But with a simple trick, we managed to obtain that short list. We group maintainer records by mailing list and attempt to extract the subsystem name from that mailing list. It works in almost all cases. There were a few exceptions we had to manually fix. But as a result, we got 238 subsystems with names we wanted. So we auto-generate a list of rules that map every subsystem to the list of regular expressions for source code paths that's taken from maintainers. And syzbot will match them against stack traces for crashes. And we take relevant calls from reproducers. Overall algorithm is straightforward. We take X-stop crash reports for every bug, extract subsystems for every crash, and aggregate the results. I will not go into many details here to save time. If you're interested, you can download the presentation and click on the link. You will see more details there. Okay, in general, from what I see, the quality looks reasonably good. There are, of course, some false positives, and due to subsystem classification relying on other functionality that's also not 100% reliable. But it works. And of course, currently we have implemented it like we saw it should be, but of course you know better. So please, if you think there should be more subsystem, you think we should classify differently, please let us know. Okay. The next section is the bug analysis functionality that syzbot has seen this year. And let's look at this simple example. So suppose we have found a bug on an LTS kernel. We have found a reproducer for it. We run this reproducer on the head of the mainline tree. It does not crash the mainline tree. We run it on the head of LTS. It crashes the LTS tree. So what can it mean? There can be several situations. One of them is that the bug was present in the mainline tree. It got duplicated when LTS was created. It got fixed in the mainline tree, but the fix did not reach LTS. In that case, you would see exactly the same behavior. Mainline not crashing, LTS crashes. It can also be that the bug appeared in the LTS branch as a result of some unfortunate sequence of cherry picks. It's more unlikely, but still possible. And of course, we must also assume there can be errors during this procedure. But hopefully, it's only a very, very small share. So syzbot has begun to perform this analysis automatically for its findings in LTS trees. And here you can see the current results as of October. For some bugs did not get classified because they did not have a reproducer. But out of those that were classified for 5.15, around 1/3 of what we found got an LTS on the label. For 6.1, the situation is better. It's about 1/4. So if you download the presentation, you may follow the links. You will see the actual list of bugs. And if we can detect issues that are only present on LTS, we can also try to find the missing backports for bugs that are really missing the backport. That is, if we have a mainline tree, we can check that if the reproducer crashes the kernel at the point where LTS tree diverged, and we know that it doesn't crash on some later commit, we can perform a bisection to find the actual commit that should fix the bug. And syzbot has also started doing that. So far, we have accumulated, I think, around 100 such commits that need to be recorded. I have analyzed some of them, and here are the results. So for 5.15, 65% were correctly identified. For 6.1, it was 81%. Interesting, though maybe not so interestingly, almost none of those commits had a fixed stack, which is probably why they were not backported in the first place. And what were those commits? 64% of them were actual bug fixes. Around 20% were various refactorings and optimizations that did not seem to have bug fixing as their main purpose, but as a result, they still fixed bugs. And smaller shares of issues were commits that corrected invalid assertions in the code. So basically, there was no bug, but the kernel was incorrectly claiming that there is. And kernel feature deprecations. We are currently trying to establish a procedure for actually sending requests to backport those commits. Okay, and here's the last section. This year, as I mentioned, there have been quite a few interesting discussions on mailing lists around various aspects of syzbot operation. So let's look at most common themes that were seen in those discussions. The first one is discussions around syzbot sending reports in all the kernel code that's either unmaintained or known to be very buggy, or that code that will soon be deprecated, or for findings that are not really perceived as bugs by the kernel community. And the usual counter-argument was that, okay, even if the code is to be deprecated and or known to be very bad, but it's still in the kernel and it's still compiled in by many distributions, and is it correct to ignore problems in it? And discussions got very big and sometimes heated, and it of course should not go on that way. And now we're implementing a compromise solution. We do not report such findings anymore to the mailing lists, but we do display them on the web dashboard with a special tag, so that you can filter them out if you do not want to see them. Another theme is syzbot sending low severity and low priority reports. And it's hard to argue, not every syzbot report is about some fundamental problem in the kernel code. But unfortunately, at least at this point, the bot cannot really automatically prioritize these findings. To somehow address the problem, there are now two new syzbot commands. One of them can set priority for the issue, so that you can filter issues by priorities on the web dashboard. And the other one excludes finding from monthly reporting. And if you see any repetitive cases of such reports, please let us know. And here are also a few ways that we can help syzbot and syzscholar and actually any other coverage guided fuzzing tool to find more interesting problems. If syzscholar has more descriptions of the target subsystems interface, it will be able to generate more meaningful programs that go deeper into the code. Also, sometimes it happens that kernel crashes not very deep into the call stack, so we do not really get to exercise the complicated code. So once these problems are resolved, the fuzzer can go deeper. And of course, it really helps when assertions are implemented with care. So for example, warn on and bug on should not really be used for validating user input. They should only be used for situations that should never happen. And then all kernel automation will be happy. It is also possible to find out how deep syzscholar has managed to get into the kernel code. We provide coverage reports on our web dashboard. So if you want to see one, navigate to our main page and click on one of the links in the coverage column, just like the arrow shows you. It might get you some idea of what we are exercising and what we can exercise with some little effort. Another big problem is maintainer burnout. And of course, it is much more fundamental problem, and it's not just syzbot. But still the question is, what can syzbot do to make the situation better, at least from its side? And one of the possible ways to improve the situation is to try to shift-led kernel fuzzing. That is to fuzz incoming patch series, and so that we could find problems in them before they are merged. The earlier problems are found, the less time maintainer has to spend later trying to figure out what went wrong. There is lightweighter approach possible, that is not to do actual fuzzing, but at least apply the incoming patch, build the instrumented kernel, and run the corpus of syzbot generated programs against it. It has a pretty good coverage of the kernel. And hopefully it can catch some not too difficult to trigger problems very easily, but it needs to be evaluated. And last big issue are various false positives that appear in multiple places. Can be invalid bisection results, incorrectly inferred subsystems, incorrectly merged reports, not fully minimized reproducers, and so on. Unfortunately, some false positives are always to expect with automation. So we try to focus on eliminating whole classes of false positives. If you notice any repetitive cases, please let us know. And while some of the false positives are purely our guilt and can only be fixed by us, in some cases we really need help from the kernel itself. Because in the end, kernel bugs are detected by kernel itself, and syzscholar just stress tests the kernel to trigger those problems. So any improvements to the kernel's bug detection benefit everybody, not just syzscholar. And another way the kernel can really help others is by providing options to disable dangerous functionality or dangerous kernel interfaces. For example, there is kernel config that disables access to /dev/mem device, so that for us it means that syzbot is sure not to mangle kernel computer's memory directly. And the recent examples, big thanks to Yankara for the patch series that we have already enabled, and that should eliminate a big class of undesired file system reports. Yeah, thank you very much for your attention. Small reminder, right after this presentation, there will be a BOF session related to how to make syzbot reports easier to debug. So if you have any experience to share or any ideas, please come visit the session. Your feedback is very, very helpful in making the tool better. And once again, thank you very much. If you have any questions, please.
Is there a way to tell like root versus non-root bugs? Because like writing to devm, hopefully that's root only.
You mean bugs which require, whose reproducers require root to trigger it?
Exactly.
Not at this moment, but it's an interesting suggestion.
So you mentioned the maintainer burnout problem, and I agree it exists. But one of the issues that causes burnout is by sending bug reports, not patches. So what we need is an automated way of turning syzbot reports into actual patches. Now, I'm told that various things like AI can actually do this, but we can smile now, but it's about time we actually tried, because I can bet my bottom dollar that a maintainer gets stressed by a bug report, especially when everybody else says, yeah, I ran into that bug too, why haven't you fixed it? They get a lot less stressed by patches. So if we could do something to try and actually turn the reports into patches, I mean, even if it's just a team at Google actually looking through the reports and saying, you know, set a bunch of interns on it and see if they can produce patches, that will actually help to reduce the stress. Because you can say, here's a patch found by syzbot, we didn't even send you the report because we sent you the patch instead.
Thank you. I have heard about researchers trying to find some ways to auto-generate these fixes for actually for syzbot bugs, but I don't know how maintainers would be really happy to see a lot of wrong patches.
But have you tried you bisect to something and then you revert it, rebuild, and then see if the problem goes away? If a simple revert would fix the problem?
No, we haven't tried that yet.
Yeah, but
That could be
then you can
help eliminate some false positives. Yeah.
So another right here, yeah. Another question, but actually a suggestion. I was looking at some of the things you said were problems that could be solved, and I think the first step would be to differentiate which of those issues are syzbot specific and which ones are inherent to CI by nature. So, for example, there was your kernel configs applied by syzbot causes some kernel revisions not to boot or not to build correctly. So that's something that's specific to syzbot and something that can be tackled at first, maybe. But there are some other things about, for example, bisections leading not to the cause of the bug, but to the commit that made the crash surface. I think there's not a lot you can do about that. That's basically how bisection works. And sometimes it's like that. Then you get to investigate where the root cause is. But maybe you can leave that for later. Maybe those kind of problems can be tackled in a more generic way instead of trying to address them yourself. What I'm trying to say is try to find the low-hanging fruit first what can be improved by syzbot and which issues are common to. Great work, by the way. I think you're doing great with syzbot. It works very well.
Yeah, thank you. It's indeed a very fruitful point of view, yeah, to differentiate issues we can fix and that are related to kernel. But the one you mentioned about kernel not building and not booting with syzbot configs, I think it's not really syzbot's fault, because it's not that by syzbot config I meant the normal Linux config, but just with the options we normally enable. And I think the kernel is expected to still be able to build and boot with different config combinations, but unfortunately it's not always.
Yeah, there might be needed to do some work there to address configuration dependencies to avoid these kind of situations. Yes.
So thank you for the talk. I read a blog post by Google Open Fuzz on their usage of LLMs to generate the harnesses, not the code, but the harnesses to do the fuzzing.
Mhm.
Is any of that work like available to you to start to try and like increase the amount of coverage?
We use our own language for defining these descriptions, which describe what system calls there are, what data structures they expect, what fields, and the rest. We try to experiment with LLMs, like here is kernel code, please write syscolor descriptions, but so far the results are not very promising.
Okay, this is interesting.
How much, right now, system calls are covered and some ioctls. What else are you working on? What parts of the kernel interface are undocumented, I guess, whatever, covered?
To be honest, we ourselves have, there was very little time left for actually working on these descriptions for kernel interfaces. So it remains, it grows by contributions from outside mostly. And we have a special issue on GitHub that lists all big uncovered chunks of the kernel. Which is like, not sure I can list some by heart, but there are many of the kernel. Actually, we do not cover much of the kernel, so there is a lot more work to be done. And we provide these coverage reports where you can actually see all the kernel code and see what blocks of code are covered and what are not. It can be a very good guidance in understanding what is done and what should be done. No other questions? This one.
So another suggestion would be, if you looking somewhere, like LLM would be in that direction, but something simpler. If you get some backtrace in some class of let's say a driver, and then you look at the previous fixes and say, oh, maybe this is related to the same kind of fix that that's like classes of bugs that you could, instead of just pointing the problem, bisecting, suggest that look at that previous fix that may be related.
It's interesting. At least on our web dashboard, we try to display similar issues, at least those that appear that had similar backtraces and that were already closed or fixed, so you can find it. So thank you very much.
I'm bringing your presentation.
Slide notes.
Oh, slide notes. I don't know. I don't think so. Those files. I'm bringing your presentation in now. That one, right?
It's okay.
So you can use that. That might work. Just make sure this is on.
Yeah.
And it's uploading your slides. Okay.
You guys.
They'll come up here. Yeah. Okay, so we'll get started. Thanks for coming. It's the last day of the event. Nice day, and there's many other talks on. So thanks for making the time to come here. So what we'll be talking about today is a project we've been working on for about a year in my team about bringing virtualization-based security to Linux. So in this time, we can't go into a lot of details, so some of this will be fairly high level. There was some more detailed discussions yesterday in the KVM forum on some technical issues, so you can, or the KVM microconf. Mikhail presented some more deeper updates on them. There are patches. You can go and look at those slides and the recordings, I believe. So what we'll be covering today, I'm just giving a brief introduction at a high level about the architecture, and then we'll have Tara will talk about our implementation of this using HyperV as the hypervisor, and then Mikhail will be talking about the KVM implementation that he's working on. So we're actually working on two projects in parallel here. So just briefly, what is virtualization-based security? So this is not a new concept, and the name of this is potentially open, in the community if people want to change it. It's a VBS is something we've taken from the Windows world, but essentially it's about utilizing virtualization to enhance the security of the guest OS, both the kernel and user space. And essentially what we're doing, if you imagine the principle that you have a security boundary between the hypervisor and the operating system. And what we want to do is sort of leverage that security boundary in a similar way that there's a security boundary between, say, the kernel and user space. So essentially what the model is, and it's fairly flexible, which we'll get into, is that you have a kind of a security monitor in the hypervisor, and it's going to depend on whether you have a type 1 or a type 2, exactly how that works. And this is able to make security decisions and enforce properties of the system that are very difficult to change from the kernel or the guest user space. So some of the features of this, or the primary features of this, include protecting the integrity of security critical guest structures, and that includes a whole lot of things. So that's doing a lot of work, that sentence. So this includes things like kernel and user space, memory protection, memory permissions, CPU registers, critical state, security-related state, certain variables, configuration variables, such as the SE Linux enforcing thing, which there's the flag that attackers often set, and even if that is somehow sitting in read-only memory, if it's still there, there are ways to potentially modify page permissions if you have the right attack chain. So we'll get into more detail on exactly what those are down the track. And one thing you can do here is help to prevent the bypass of guest security mechanisms and policies. As I just mentioned, you can potentially use this to enforce, say, that a security policy that's been loaded is authentic and has been verified before it's actually available in the guest kernel, and then that kernel, depending on the policy, will not be able to, if it itself is attacked, will not be able to, say, overwrite that policy. Another aspect of this architecture is that it provides support for a trusted execution environment for running security applications. And so it doesn't actually inherently provide a T of any particular type. The idea is that this is an extensible architecture, and if you want to set up a trusted environment for doing things such as key management, credential management, or by enforcing executable code integrity, checking checking the signatures on executables that are running, and kernel modules and various things. So in our work, we have used a port of opt to x86 initially, and then we've moved to a Linux kernel based mechanism for this trusted execution environment, which in VBS terms is called a secure kernel. And so people who saw the KVM talk yesterday, or KVM microconf yesterday, would have seen there was an Amazon talk about providing virtual secure mode, HyperV virtual secure mode emulation in KVM to allow Windows guests to run and use the CredGuard facilities that provides. So we're coming from a kind of a different angle. We're trying to provide the overall environment for this for Linux, and to allow different types of secure kernels and security models to be implemented. So why are we doing this? We really think that there is a gap here, that Linux is not currently, or mainline Linux is not at the state of the art, both in terms of attackers and the threat environment. So Linux is obviously scaled out into every sort of corner of the globe and beyond. And so the value that it's protecting is increasingly high. We have all kinds of government, military users, health information, banking, and so on. And the sophistication of the motivation of attackers continues to grow. So we want to try and raise the bar here, and we're trying to build on existing mechanisms. So there are existing hardening mechanisms such as KSPP and the kernel lockdown and so on. So this does not try and replace those. It will potentially enhance those mechanisms to help enforce them and bring some new mechanisms with it. In the proprietary and out of tree space, there are several enhanced security and lockdown mechanisms such as GR security, for example, in Linux, which is not virtualization-based security, but it's significantly advanced, I would say. And there are some other out of tree mechanisms such as that. And there's also some proprietary virtualization-based security mechanisms. I think Samsung is known for their RKP and so on. So we would like to try and bring this into mainline. And we're acknowledging, we'd like to acknowledge that we're building on a lot of existing ideas and concepts. We're taking patches from the community in terms of KVM, such as the control register pinning patches. And there was a previous presentation at a KVM forum by Google on this topic, and we studied that fairly closely. So we would really like to invite collaboration across everybody in the community. Very briefly, this is an architecture, so we're not trying to prescribe a specific way of doing things that is independent of the ISA, the hypervisor, the type of VMM you have, but also the type of hypervisor. This will work with type 1, type 2, and things in between with different mechanisms for that. And the security monitor, this is just something this is the part that will live inside the hypervisor, and that can be very minimal, which is probably preferred. And the T implementation, as I mentioned, we call that a secure kernel in our code, but it could be opt-T, it could be any number of other mechanisms. So yeah, we think that mainline acceptance is critical across the ecosystem, so it's not just the kernel. That's why we're here, is there's various virtualization projects, particularly KVM. And yeah, we have interest at Microsoft in supporting the existing Hyper-V mechanisms, and Tara will be talking about that. We're also very interested in the team in the KVM side of things, and so we're developing a reference implementation that we hope can be adopted as a mainline project. And Mikhail will be talking about this. So this includes the changes to KVM that are required. We're working on, and we'd like to collaborate on the kernel APIs and mechanisms. And then there would need to be a policy, a flexible policy mechanism so that people can achieve different types of security goals with this. Okay, so I will now hand over to Tara, who is going to cover the Hyper-V aspects.
Hello. So I will go through some of the architecture considerations we had for this with Hyper-V, and then maybe briefly touch upon implementation when appropriate, and then leave you with links of code base that we have basically in the GitHub and what we plan to do with it. Okay, so starting with, so this is a very simplistic view of how a Hyper-V based system looks today. There is hardware, Hyper-V runs in ring -1. And the system itself gets divided into partitions. There is a root partition and multiple guest partitions. And each of these partitions can have kernel running at ring 0 and user space at ring 3. And now moving on, I want to introduce something called virtual secure mode. I think if anyone attended the AWS session yesterday at the KVM forum, they also would have spoken about this. This is primarily a Hyper-V concept where it allows you to divide these partitions in the system into security boundaries. And it is called virtual trust level. These boundaries are called virtual trust levels. And ideally, you can have up to 16 trust levels, theoretically in Hyper-V. For practical purposes and for the purpose of this talk, we just have two, VTL 0 and VTL 1. And again, there is Hyper-V running at ring -1. System is divided into partitions, root and multiple guest partitions, and each of these partitions can now be further divided into two secure boundaries, or two VTLs, VTL 0 and VTL 1. And each of these trust levels can have kernel running at ring 0 and user space running at ring 1, basically, ring 3, sorry. And one thing I want to mention here is that in the Hyper-V's architecture of VTL, higher a VTL, more privileged it is, and that is how it guarantees security boundaries. In this particular case, VTL 1 is more privileged than VTL 0. And Hyper-V Hyper-V restricts access between VTLs. Hyper-V restricts tampering between VTLs, tampering of data, tampering of address space, tampering of execution between the VTLs. So some of the features that get offered under this bucket of VSM and virtual trust level, one is virtual processor state isolation. Within each of these VTLs, each CPU running in a partition has now two execution states within a partition, a VTL 0 execution state and a VTL 1 execution state, and they are separate, basically. Memory is split between the VTLs, and memory is split, and then Hyper-V controls the access. Like I said before, Hyper-V controls the access across the memory boundary of the VTL. And memory access permissions are hierarchical. Hyper-V guarantees that as well, by which I mean that within a partition, within the physical address space, the access restrictions that are set by a higher privileged VTL takes preference over the access permission, memory access permissions that are set by a lower privileged VTL. And this forms a key tenet of what we are trying to implement later on. We'll see that. And finally, what VSM offers is separate handling of interrupts and intercepts between these between these execution environments, which means each VTL can handle their own interrupts, which makes it easier to handle secure interrupts and secure intercepts without any interference from the software running in the normal kernel. I just want to go back to this picture and say that in our example, what we will see is that VTL 0 will run the normal operating system, the guest kernel or the host OS or whatever the normal operating system, and VTL 1 is where we want to try and run the secure kernel, basically. Moving on. So now that Hyper-V has VSM and we want to do Linux virtualization-based security, there are a bunch of features that we can target with this architecture that Hyper-V gives us. First and foremost, what we can do is kernel hardening, by which I mean you can back up the access permissions for all critical kernel structures or kernel resources, memory, critical data structures, critical system registers, things like that. The other thing you can do is to offload some of the policies and some of the authentication mechanism into this higher privileged execution environment, thereby making sure that it is tamper-proof and all these critical policies run at a higher trust level, basically. And finally, you can use this separate execution environment or a higher privileged execution environment to store critical sensitive data like passwords, keys, and make sure that there is no unauthorized access that can happen across the boundaries. With all this, I don't think we are not targeting all this one shot, and probably we should not be doing some of this ever. But what we are targeting for at least the first phase of the project is basic kernel hardening, backing up some of the kernel hardening features with VSM and LVBS. With that, I want to talk a little bit on the threat model for the kernel hardening, just to be on the same page on what I'm talking about. So what we are trying to protect here is critical kernel resources from a user space attacker who has somehow gained entry into the kernel by exploiting an existing vulnerability. The idea here is that the attacker has already an arbitrary read-write access to the guest kernel due to this vulnerability, and we want to protect the system resources from such an attacker. That is the basic premise. Yes, excuse me.
I have been wondering, I mean, what's the advantage of doing this instead of just, for instance, creating separate guests with different privilege levels and making sure that each of them have, higher priority or running security stuff, or even using confidential VMs, which is, available today, or even, secure zones or something like that?
So confidential VM has a separate security model. The premise of confidential computing is to protect the system from hypervisor itself. Hypervisor is out of TCP in confidential computing, whereas here, hypervisor is still within TCP. So this is a space where it is they are complementary features.
Right. So what is the advantage of using this feature instead of using different models? I mean, I'm not seeing...
No, so this is the evolution. I think once we have confidential computing, there will be pieces of this that will need to move into the confidential computing system. Okay. So this is probably an evolving model that we are talking about. Okay, so where was I? Yes, the threat model. Yes, so such an attacker, what I was trying to say is the attacker already has read-write access to guest kernel, and we want to protect the system resources from such an attacker. That is the premise here. I want to call out here that in this whole process of the architecture and implementation, we are piggybacking on the fact that we can trust secure boot, by which what I mean is we assume that the kernel or the operating system is not tampered with during boot, because there is secure boot, and secure boot is already authenticated and validated, and so it is not tampered with at boot till the first user process starts running, which is the init process as far as Linux is concerned. And finally, I want to say that with this, what we are targeting when I say kernel hardening, we are not actually offering any extra feature. We are not introducing any extra feature to Linux kernel. All we are offering is defense in depth. Linux kernel already has these hardening mechanisms. Kernel already allows you to protect critical system registers. Kernel already protects pieces of memory by marking them as read-only, or the text section as read-execute and non-writable and all that stuff. We are not, so there's no new feature itself being added. What is happening is defense in depth. They say that even if the kernel is tampered with, if you can back these up via hypervisor or a higher trusted environment, a higher trust execution environment, they cannot be tampered. These resources cannot be tampered with. And I want to briefly talk about the hardware requirements we have here. One is support, the architecture should support second level address translation feature. And the other one is that we need the CPU feature that actually differentiates between the execute mode, kernel execute mode, and user execute mode, like MBEC. Finally, yeah, so when we come to the architecture, I've tried to break this down into piece by piece. And then finally, we'll look at the big picture of what the system should look like. So first and foremost, what we, like James mentioned, we wanted to have an hypervisor agnostic solution. So what we are trying to say is that we want to have all the kernel frameworks there, and we want to have the protection mechanism and the monitoring all go into this common layer. And from that common layer, it gets distributed to whichever hypervisor driver has hooked into it. And so one such example of this common layer is Heki, which Mikhail will actually talk about, and we talked about it. He talked about it yesterday in the KVM micro conference. And it's a hypervisor enforced kernel integrity layer, and we want to have such agnostic layers to which hypervisor drivers can hook in, and so that this is not the architecture is not constrained to either Hyper-V or KVM or any other hypervisor itself. Secure kernel, I think James talked a bit about it. So now that there's this big question of what to run as secure kernel, now that there is this trusted execution environment. And some of the things, I don't have time to go through everything we considered for this, but some of the key considerations we had was, one was that we wanted a small TCB in secure in the software that runs in VTL1. We also wanted the support to add the secure interfaces for communication between the normal world and the secure world, between VTL0 and VTL1. And finally, we wanted it to be maintainable. We didn't really want to go and write our own piece of software to be put in VTL1. Opti was actually a very, very strong contender for this. The only reason why we didn't choose Opti as for the first phase of this project was because Opti doesn't have x64 support. The x64 support for Opti is very minimal, and that's the primary reason why we did not choose this as Opti as a secure kernel. So the initial choice is a minimal Linux kernel, where we are trying to strip down most of the things we don't need in the Linux kernel to run it as a secure kernel. This is evolving. It is not set in stone that we should use Linux as a secure kernel, and as we progress along with the project, and if we find more suitable candidates to run a secure kernel, we will change this. So a bit, so now.
Second.
So I just wanted to ask a question about the idea that the hypervisor would be the one that actually does all of this security, because you're running into the problem that we're investing less trust in the hypervisor. This is exactly the other way. You're investing more trust in it. In a world, say, of confidential computing where the hypervisor can't actually protect the guest, how does this interface fit into it? Because realistically, it would have to be in the kernel itself, in the guest.
Yeah, so Tara, did you have a... I was just going to mention that we do have a work stream on this. We have somebody looking into this and has done, we haven't presented this publicly yet, but we do have confidential computing architecturally.
I just want to say that, see, again, like I mentioned, confidential computing is protecting the system from hypervisor. It will not give you user space to kernel space protection still. So these are complementary technologies. So even when there is confidential computing that comes like let's say we include confidential computing, you will still need pieces of this to sit in the kernel to enforce the user space kernel space integrity, basically.
So Tara, if I could chime in there.
Yeah.
The reason we use Hyper-V here, James, is to implement the software notion of VTLs. That's really the only thing Hyper-V provides. Now with new hardware, where hardware is giving us that abstraction of different privilege levels, we don't need to trust Hyper-V to run a secure kernel in a higher privilege level, right? So these concepts really map very well to the emerging hardware in the confidential computing space, number one. Number two, as Sarah says, right, even if I don't trust the hypervisor, confidential computing stacks are still vulnerable to some user space process, attacking the kernel. And this would allow us to really lock down those kinds of attacks.
Yes.
So you talked about the minimal Linux kernel config. One of the thing on Windows, the secure kernel actually has less syscall interfaces, and that's one of the things that expose the kernel to attacks. So in the minimal Linux kernel config, you are reducing syscalls as well?
Yes. So right now the kernel doesn't even have a proper user mode running.
Okay.
So, but yes.
One last question that I have is for like Windows-based VBS, one of the first user was something like credential guard. Do you have use cases, something like that for Linux as well? Because right now you're focusing on like
yes,
kernel security hardening.
So like I said, there are multiple things that are possible with VSM and LVBS. One of it is something like CredGuard, whatever you said, like where you store your keys and you isolate your keys and passwords and all that stuff. Yeah, but that's an evolution of this project. We haven't considered it. We are not working on it yet.
So what I wanted to tell you is the choice of Linux, as Tara said, is simply the initial choice. As we look at new environments that are coming up, like Coconut, for instance, that can run in the higher privilege level, we would choose that.
I see, yeah.
Right? And in fact, somebody is looking at a project where the LSM in Linux can be hosted inside that secure kernel.
Yes, I think, yeah, that's a good idea.
If I get a good port of Opti on x64, I will switch any day. A secure kernel. But yeah. Anyways, so moving on. Talking about the control interfaces between VTL0 and VTL1. One is synchronous. I think you should have heard of this yesterday in the AWS talk. So by synchronous, I mean the VTL0 can explicitly issue a VTL call. It is transferred via the Hyper-V and the VTL call, and the Hyper-V switches the execution environment for that CPU into VTL1. And similarly, VTL1 issues a VTL return call, and Hyper-V switches the execution environment to VTL0, basically. And the other interface is via interrupts, where the premise is that if there is an interrupt pending in a higher priority VTL, in VTL1 in this case, the Hyper-V will switch execution of that CPU from VTL0 into VTL1, which becomes kind of asynchronous. You have not, VTL0 doesn't explicitly call into VTL1 in this particular case. And on the flip side, if there is a interrupt pending in VTL0 while a CPU is executing in VTL1, Hyper-V does not switch. So VTL1, the CPU has to explicitly exit VTL1 and then enter VTL0 for that interrupt to be delivered and handled. So yes, boot. I want to again come back to that. So for in this particular case, while we are with the Hyper-V architecture, we trust secure boot. What it means is, and that is very important for how we have designed the boot here. So we are saying that till the init process runs, because of secure boot, the kernel is not tampered with. which is important because when we started architecting and designing this, we didn't really want to go and modify bootloaders to get this design up and running. And if we are talking of deploying this across architectures, it is better for us if we don't have to modify bootloaders. So in this model, what we can say is we trust secure boot. We let the kernel boot in VTL 0. We let the normal operating system boot in VTL 0 in lower privilege environment. And at some point in the boot process, earlier in the boot process, we allow VTL 0 to boot VTL 1, or allow VTL 0 to send processes into VTL 1 and boot VTL 1. That's what we do. And somewhere during the late stage of the boot, we enforce all these, we send the policies and the monitoring policies and the enforcements that we need into VTL 1. And at that point, we lock down the guest operating system. I think am I out of time? Yeah, maybe. Yeah. Okay. So I will not go through this then because this is probably too much for this. And anyway, so again, the big picture, this is how it looks like. There is a regular normal operating system running in VTL 0. There is secure kernel running in VTL 1. Regular user space applications running in VTL 0. We want trustless to run in VTL 1 at some point when this architecture evolves. Right now, the code we have, we don't have anything running in secure user space. During boot, like I said, the early boot driver comes up and boots the CPUs in VTL1 and returns back. During the later stage of boot, we have all these kernel frameworks that boots and comes up and it call into this common hypervisor agnostic layer, which calls into your hypervisor driver, and then that issues the calls into VTL1 to enforce all the policies, monitoring all the memory protections that we want, the control register monitoring and all that kind of stuff. And at that point, we assume that this guest is locked down and we can hand over the control to user space. And finally, I want to show this picture where in case of a violation or an access policy violation or an access violation, what happens is that HyperV, this is where that asynchronous communication comes into picture. HyperV pings or HyperV intercepts VTL1 saying that there is an access policy violation. There is probably a memory access violation or whatever. And then VTL1 gathers information on what happened and injects an exception into VTL0, at which point either guest kernel can choose to die or take appropriate action. With that, I leave you with the code. So we have both the secure kernel code and the guest kernel code with the changes in these GitHub repos. What we intend to do is to now start breaking down into smaller pieces and send patches for review and feedback and all to the community. And I hand over to Mikhail to discuss the KVM portions of this.
Thanks. So I will focus now on what is specific to KVM. So first here, the big picture of the architecture, and I would like to highlight because there's some interest in computational computing. So again, with the picture, it might be easier to understand. So in a nutshell, the threat model-based computational computing is to protect the guest from the hypervisor and the host. And with our threat model, it's to protect the guests from itself. So that's not the same goal, and both can be complementary. So with that in mind, so in a nutshell here, we have the guest kernel with some changes to implement some hypercall called KVM, but also to kind of enlighten its own memory management, for instance, or even the control register changes. So for this to kind of request to the hypervisor to enforce some translation or not, or allow some changes. And well, this architecture is much more simple than the HyperV one with VTLs. But as we said, this might evolve with computational computing features such as concurrent services and things like that. So we sent an NRC a few days ago. You can take a look, and we'll provide some link at the end of the talk. And also, it brings common guest kernel implementation on which each hypervisor can plug in its own specificities. For KVM, there's two new hypercodes, one for CR control register pinning enforcement, another for memory permission enforcement. So mainly security policy definition. And there is also a new KVM interface, between the hypervisor and the host to know the host about the guest security policy. So it might be required, in fact, because, for different reasons, but one of them might be, for instance, to report attack attempts, or even to act, like, I don't know, to shut down the VM, or to freeze it, or to do a snapshot, I don't know. Can do a lot of stuff. And another thing is to let the host knows about the restriction of the guest and be able to kind of contribute to these restrictions. For instance, the host might expose some drivers, so some memory mappings, and we might want these memory mappings to be also constrained by the guest wishes. So two app goals. First one looks like this. So the idea is to be able to pin some flags or control registers. So this includes critical control registers, so mainly CR0 and CR4. For instance, the ability to disable the write protection mechanism, which is, of course, really important in case when you want to harden your guest kernel. And there's also a lot of other flags as well, like for SMAP, SMAP, and a lot of different security features. When there's a policy violation, KVM in this case can create general protection faults that might be handled or not by the guest kernel. So, but the information there. And it can also create a VM exit before that for the host to know and react if it wants to. So highlight on some specificities on this second hypercall. So we're using, mostly leveraging EPT, so the extended page table attributes. And the hypercall is, looks simple, but it's not, in fact. The idea is to pass a list of page ranges.
So
yes.
if you look back at what Tara presented, the interactions were between the guest kernel and the secure kernel that's running in a higher privilege level. And then from that secure kernel, we interacted with the hypervisor. That's the flow, right?
So that is the flow for the current HyperV implementation.
On HyperV implementation.
Yes.
So as I look at the KVM implementation, we are completely bypassing a secure kernel.
There is no secure kernel.
Right. And yesterday we learned about the plans the KVM folks have, at least in Amazon, in terms of building these VTL abstractions in KVM. So perhaps we should look at how we integrate this. As opposed to having hypercalls for doing this directly, we should be looking at interacting with the secure kernel in a way that is not hypercall related, a slightly higher level interaction, because down the road we will have other services like CredGuard or LSM and things like that can't be all encapsulated in a hypercall. So maybe that's the right abstraction at which we do that. And from the secure kernel, we could do the hypercalls.
Yeah, so that's right. It's definitely something we are interested in. There's something to keep in mind. So first, we need an interface. So this interface might be VM calls, this might be hypercall. Anyway, we need a standard interface that can bring some security guarantees. And then, first of all, the VTL patches are not in mainline, such as our own. So we may want to start with something simple with the first interface. And for instance, for the CR pinning patches, it's not complex at all. So this can fully be implemented by KVM itself. And later on, if we have another way to enforce that with VTL, Coconut, or whatever, we could leverage that. So that's not a blocker, but we could see it as an incremental evolution of implementation. What matters is really the security guarantees we want to provide and the interface, the guest interface with the hypervisor, so, and all the abstraction around that.
Okay, so I wanted to comment on your question, actually. So you said, well, this is not going through the secure kernel. It's a straight hypercall to KVM. Can't we make it go through the secure kernel? But I would say the opposite. Isn't it a good thing that this is just KVM and it doesn't actually involve the secure kernel? Because there might be other use cases where you want to use the CR pinning, for example, without secure kernel, without LVBS. This actually seems like a generally useful thing for many KVM users, not just for this.
Right,
So keep it. It's good.
My response would be that maybe there's a class of activities that should be directly supported by the hypervisor, right? And we could do that on the Hyper-V side too. We don't need to go to the secure kernel and come back to the hypervisor. These calls could be made directly from the guest onto the hypervisor, irrespective of whether the hypervisor is Hyper-V or KVM.
Okay.
But then there are higher level constructs, like hosting the entire LSM in the secure kernel and the interactions with the LSM going through that east-west interface, or maybe CRED guard or driver guard and things like that. So we need both kinds of interfaces for both KVM and Hyper-V.
And one thing to keep in mind is that Hyper-V is already ready for this kind of security features, and it has been for a long time. KVM is not, and we might not want to wait for years for KVM to kind of get the Hyper-V features, and in fact, might not be needed. So yes, both of you are right. So let's go to another feature we implemented in KVM, which is already in place in Hyper-V, but now we are implementing that for KVM 2. So it's really important because it's able to enforce memory restrictions, especially on executable pages, in a way which is efficient. So I'll go really quickly about that. The idea, it's an Intel, this is also the same for AMD, but in this case, it's called mode-based execution control. It's a way for the EPT, so the hypervisor manage memory table permissions, to kind of split the executable bits into two, executable for user space or executable for kernel space. And that enables you to enforce security policy only on one of this side. And what's interesting in our use case is to enforce on only the kernel side, because user space might be much more complex and might be also handled by the kernel itself. So in a nutshell, without MBAC, we need to make a lot of the guest memory executable, because we don't know, and it might be used by user space, because, here we are talking about physical pages, not virtual pages permissions. And with MBAC, we can make the guest kernel memory protection much more secure. So to control really what we want on the physical memory pages to be executable or not. So you can find the code of the first RFC and the second one in this GitHub organization, GitHub repo, and it's along with the other set of comments. So to wrap up, what we like to do is, and what we're working on, is to improve the security of Linux, and that might be by using either KVM or IPV, or even other hypervisors like Zen or whatever you want. So we're definitely open to new contribution on this part, and for now we are focusing on KVM and IPV. It's a different dev mechanism. So security is not perfect, and we're trying to improve that thanks to virtualization. So we're open to any feedback. So please talk to us, send emails, on mailing list or here. I don't think so. We have 2 minutes.
So there's a demo in the slides which should run.
Yes, and it's on the GitHub too.
A quick question.
This will be a hard.
Quick question on the page permission enforcement that you just had up. The implication of being able to control those bits. Some of what you talked about imply that you're trying to also protect the kernel from itself after it's booted, right?
Yes.
So the implication of what I'm hearing is that at VTL1 or maybe in the hypervisor, you are going to protect against changing the permissions of already set permissions, right? Doesn't that imply you have what amounts to shadow nested page tables then?
So, well, the thing is, well, there's different use cases. So here we are mainly targeting hardware-based virtualization, so using VTX and MBAC and so on. So for instance, all these changes also work with nested virtualization, except the executable bit permissions, because it requires MBAC, and we didn't implement it yet, MBAC for nested virtualization. But yeah, we need to take, well, a lot of things into account. And but yeah, everything which is managed by the hypervisor can be dealt by the hypervisor.
Yeah, it's just I guess I'm making sure I want to understand the mechanism, because once the permissions are set, then you have to enforce them against potential future calls to unset or change them.
Yes.
And in that case, you have to have a record of what is.
Yeah.
Right. Okay.
So yeah. So
it just sounds like it implies the nature of there's a set of shadow page tables somewhere to enforce it.
Wait, one thing so we don't have time to explain everything. But yeah, the simple use case is to make some memory pages permission immutable, to not be able to change that. And that also is the main use case for CA pinning. But in some use cases, and what we talked about yesterday, for instance, is how to make the guest kernel memory protection more dynamic, because, for instance, when you want to load the kernel module, when you want to use the eBPF-JIT or kprobe and stuff like that, well, you need to change the kernel permissions. And for that, well, you need to kind of move your trust from the guest to something else. And that can be done, for example, with kernel modules, with kernel signatures. You can, well, first sign your kernel modules, pass these public keys to the hypervisor, VTL1, whatever. And then later on, when the guest put it and is compromised, then the HyperV can still keep the trust from the initial boot kernel and then do this kind of check. But yeah, it's getting complex.
I have a question for Tara. So do you already have some idea of parts of Linux that could be moved to VTL1? And if so, what kind of kernel would you use, and would they be in user space or would they be in kernel space?
We haven't really explored it, but one thing I want to say is, like Mikhail said, the module authentication is probably one of the first things we will get to doing, because it is needed if we enforce memory permissions in the kernel, right? So in which case, the authentication itself can be moved into VTL1. We can do it in a step-by-step manner, where we first say that we protect the keys, we make sure that the keys that exist in VTL0 is read-only and things like that. But then eventually it is probably we are looking at the authentication itself to move into whatever kernel is sitting in VTL1. So yeah. And then when you say, I think that it is better for development and support if we can have most of these services run in a secure user space than in the kernel, because you don't have to go ahead and change the kernel for everything that you need, new services that you want to introduce. But again, that is an evolution, and probably the first thing we will do is to move it to secure kernel, and then we will evaluate if we can move it as a secure user space.
So that's one of the shortcomings of Coconut. Coconut doesn't have a user space right now. It'd be nice to have a full-fledged
I don't know
user
who
space.
asked first. So
I think this guy.
Yeah.
Have you thought about device accessing VTL1? You know, interacting with devices somehow?
Oh, sorry.
No, we don't. No, we're not doing, we have not thought of the device access in VTL1. I want to say that there is another project happening in Microsoft where there is a piece of software running, Linux kernel running in a more higher privilege level in VTL2, where there is some kind of device access and emulation and all happening. But that is kind of out of scope of what we are trying to achieve here with respect to security.
And how much of the current VTL TLFS spec do you want to reuse, or are you thinking of reusing it, or you want to create something from scratch?
For secure kernel?
Yeah, to introduce all these VTL, to generalize VTLs out. Are you planning on reusing TLFS to some extent?
Oh, yeah, we are reusing
Fully?
TL fully. Yes,
Okay.
we are not going to change the Hyper-V at all for that matter.
Lovely.
Yeah. We want to keep changes as minimal as possible. That is the premise in which we started this project.
Perfect.
So it may be possible for your work to integrate potentially in some ways, but from our point of view with the Hyper-V side, there's not going to be any change to Hyper-V. So we're out of time. We'll be up here for a while if people want to continue the conversation. It's during the break. Thanks.
Thank you.
I feel cut off. I feel cut off.
Yeah, probably. Some level of shock. It's not done.
Well, you don't need to. Properly instructing your background reboot mismatch of approaches of like
In the container space, you don't need that much.
oh, absolutely, you still do. Even if you have a minimal set, people, I mean, like even we get it's asked for all the time. Even for like not just obviously not the ellipse or not the kernel, like don't reboot the toast.
Yeah.
And it's just not okay because even if you bypass K-exec, you can still have this running in things that are like you have to restart the disk and then you're talking to application owners how to restart gracefully or whatever. Like
But isn't most of the container world in a stateless?
There's lift and shift. People are like literally, look, I just put like SAP, whatever blade or Oracle database in a container. And you're like, you don't fucking do that. Like it should be redeveloping the thing. People literally lift and shift. So
What do you think as a person? I'm just mildly curious now because I always thought that it would be heavily favored towards the stateless. You're not saying.
New development, but all the companies that are wanting to embrace it and be hip and be cool are wanting to reuse what they've invested in for the last 20 years. So they're like, cool, I want this Postgres database. And you're like, well, we can do that, but it's not going to, whatever. So it even live patching K-exec feels like a reboot. And they're like, no reboots. You got to follow it. Hey, fuck. Oh yeah. Hey y'all, yeah, I'm going to re-ask you, you might get a microphone question.
I think actually somebody else does it for us. I'm not sure that we can. Here, I find right here. Oh, yeah. But I think that the next slide thing. I have seen you figuring around in other solutions. Read this, and you can use Yes. Probably, this is probably like. So I think you just. Only one slide today. All right. I remember. Oh, and the thing where you say I got one. I think there's one up here for you.
We have a question for you. Can you have a device with a runtime system, suspend the system, will that device resume what we call
Yeah, that's optional.
So having a problem.
Spends all this time resuming before you suspend it.
No, it's first, so what happens is that you suspend then you suspend the system, because of the hardware and how it works, there's decent so then it has exactly.
Oh, okay. It's working. We're good.
Yeah, this is Raphael. You may have an answer to your question, or at least some insight into it.
Problem currently that I'm trying to fix is that when you load the suspend test, which is just a pure ATA, right? To this suspend itself, you can only and in that state, suspend the system, resume it, because of the way the algorithms and how ATA resume is done, this will always but it's like the resume function disguises this that does not call. And if you look at the runtime status, we see it says suspended. This so it's trying to the user, and I would like to resume to force runtime resume the drive. And I don't see it working. Yes, with the hardware, which is not. So the hardware, all the students enough, I know. But no, my point is that the review function of that device, system review function of that device, is not one can. But the CM core is called I was about to get into that and try to figure out why it's not being called, then trouble with years. Or some figure out done when we suspend. And just to figure out the reason all of that, and if I don't see what it's
No, I'm good. I'm good. Thanks. Yeah. I'm just going to make sure Raphael has a microphone because I know he's going to want to sing a song for us during this presentation. Oh, don't tempt me. I have my ukulele in my car. All right. I think it's past. We should get started. I'm Lynn Brown. I've got some other introductions to do in a second, but first what I'd like to do is ask you by hand raise, who has a laptop that doesn't suspend resume properly? Okay, all right. Do you have it with you? No, okay. Who has a laptop with you that does suspend resume properly? Okay, almost everybody, okay. All right, so what I'd like you to do is join me in a round of applause for this guy because he's the reason that actually works. Okay. Yes, thank you, Raphael, for your decade plus or 2 decades or unstoppable dedication to making suspend resume for all of us. Thank you. Let's see. My other helper is Sleepgraph maintainer Todd Brandt, and after you use the tool, maybe you'll be applauding for him as well. He's hopefully remote. I don't actually see who's remote right now, but I suspect he's online and he can answer the detailed questions on Sleepgraph itself. So what we're going to do right now is I'm going to do like the world's shortest introduction to suspend resume, just in case somebody walked in and doesn't even know what they are. And that will be a repeat probably for a lot of you. And then we're going to go right into using this tool because I want you to leave running this tool and knowing how easy it is and how useful it is and how powerful it is. I think it's awesome, and thank you again, Todd, for writing it for us. And then I've got a bunch of rambling slides about interesting topic, and I'm hoping you guys will say, here's an interesting topic you didn't think about, or what have you, and that's more of the discussion-y Q&A section, okay? So let's get right to it. In Linux, syspower state is the user kernel API to invoke a system suspend on a laptop. You may see these words. They may not be in that order, but they're ordered that way because the ones on one side save more power. Hibernate to disk saves the most power. It's a cold off state where a freeze, also known as a suspend to idle, is the fastest and the least power saving of all of them. Standby is sort of deprecated. I haven't seen standby on a machine in a number of years. Inside, so a lot of GUIs use mem as the only state, like when you press the button. And so what happens is we had a transition where we have systems which basically suspend to idle by default now because they have a low power idle. And so to co-opt mem, this file says, hey, the hardware says you really want to use suspend to idle instead of ACPI S3 in the case of an Intel laptop. So the kernel will actually set S to idle to the default there, but you could override it if you wanted to go the other way. Here's a picture of that. Red is bad, red is power. So the more power, the worse that is. Busy is, your running state. Active idle, the purview of CPU idle, is a fraction of that. And so if you're not running anything, you get that sort of for free. Your system suspend states, so freeze can also result in active idle. If you have a system without low power idle, it would basically give you the same thing as runtime idle would give you. You're in C6 or what have you. If you have a low power idle state, it's significantly less power. And today, mem, which could go to S to idle, as I said, or it could go deep as a synonym for ACPI S3 on, say, an Intel laptop. That's, in the old days, it saved more power than suspend to idle, but today it's neck and neck. It depends on the implementation. Basically, you want to use what the default is because the OEM decided, hey, we've got a great low power idle. It's better than S3, and so you should use it. And if they don't export low power idle as the default state, you should probably use it. And they export S3 as the default, you should use that because that's basically what's tested. Questions on that? Good? All right. So I want you to whip out your Linux laptop right now. And if you've got a Linux kernel tree, I don't know if anybody has a Linux kernel tree. If you do, you have SleepGraph on your machine already and didn't know it because it's under source Linux, it's under tools power PM graph. Or if you're on the network, you can git clone github.com Intel PM graph. Do this right now. If you don't have a network, I do have one thumb drive. USB-C, USB-A. You really want to, I have some screenshots, but it's much more fun if you have your own local result you can play around with because you can do some things I can't do on a static slide. And then there's the make install. It actually doesn't build anything. It's a bunch of Python scripts, and it just installs them to where you can execute them. All right? Tell me if you have that. Somebody say you have this on your machine right now. Do I have at least one customer? Two? I got two. I got two. Do I have three? Do I have three? Do I have a third? Okay, 3, 4. All right. Okay. So do I need to leave this on the screen for a second? You know how to get to that URL? Okay. So now we're going to run SleepGraph. And actually, I left off the yes, you do. Yeah, you need to run it as root. Sorry about that. And there's a couple of options. So remember, we're talking about freeze versus mem. This says, I don't care what your default is. We're going to try freeze. We're going to, change that file around. So we're going to do suspend to idle. Dev is an option. I'll show you what dev does. It puts a little more information because we're developers. We generally like more information. RTC wake 5 says, hey, great, sleep, set the RTC to wake you up in 5 seconds. The default's longer than that, so we usually use a shorter one. And out there is just where you want to put the stuff. If you're following along with the slides, we think we have got some pretty decent documentation. So you can click on these if you downloaded the slide deck. The README is in the source file, and it's actually quite detailed. Maybe too detailed for our discussion here, but it answers pretty much all questions. So this is what you'll see on the screen. This is the command line I just said, sleepgraph freeze dev. I have the sudo on it this time. And first thing it's going to say, you know, am I root? Yes. You know, do I have ftrace? Yes, and so forth. Down here, there are some optional tools which enhance our output. They are optional. If you don't have them, that's fine. But you'll get more information about your suspend, particularly if you're debugging it, if those tools are installed.
I get syntax error.
Oh my gosh. So sudo, so what's M3 R228? Oh, out there. Get rid of the slash. Let's try that. Yeah, it's probably, there you go. So we'll report that to Todd. Todd, if there's a slash on the end of the output directory, that's my guess. No, you got something else. Syntax in the Python? Yeah. Oh my gosh. Is this, are you running it from the Git repo or from the kernel? Kernel tree? Okay. Kernel tree is a snapshot. I actually never run that version.
Unmatched closing bracket.
Sorry, I can't hear you.
Unmatched closing bracket.
Todd, there's an unmatched closing bracket. Oh my gosh. So here, try what's on here. This is from the Git repo. You can trust it. I formatted it right before this.
Or get it from the Git repo, and that could be a different version of.
Yeah, if you pull from the Git repo, try that one.
Yeah, and we fix the.
But anyway, let's. I'll show you how it works. And this is what you'll see on your screen. Okay, so to review the results, that's the same invocation on the top. In out there, choose the browser of your choice. Start at HTML. There's actually one HTML file. And when you look at that file, you're going to see this. Okay. Along the top, you know, what's my host name, my kernel. I'm doing a freeze when, on what machine. Suspend time, 517 milliseconds. Freeze time, remember we said, please give me 5 seconds. Well, we got, you know, 3.8 in this example. A resume time just under half of a second. This picture here, time goes from left to right, and it counts down until you get to this SR thing right in the middle. You could put a gap there, but we like to use all the real estate, so they're stuck together. That 3.8 seconds is between the S and the R. And then you count forward until you're fully resumed. In this case, it's the kernel resume time is, in this case, 489 milliseconds. Now, a couple of things to see on here. You know, there's a summary for this, but obviously the 915 is sort of the slowest device we have, both to suspend and to resume. Jesse remembers the old days from when that was around 10 times longer. It's way better these days. Usually it's related to the display rather than the actual GPU. USB is right behind it. This is actually pretty typical. This is an Alder Lake system actually that I have in my hotel room right now. And so if you see something faster than this, I would consider that a fast machine. If you consider something slower than this, I would consider it not as a fast machine. All right, so you can zoom in on these. You can also hover. We'll talk about it in a second. Like this sched timeout, you can say, who is doing the sched timeout? That's really helpful. You know, typical culprits are, you know, ACPI methods with sleeps built in. There's a couple of other sort of killer ones. If you left off the dev, so this slide actually shows two things. One, if you left off the dev, you don't get the, you know, the timeouts because we don't have the K-probes, but this one's actually a mem, as you can see in the first line. And so on mem, you see this extra thing here, firmware resume. It may be lying to you, but it's trying to tell you in a table how long the firmware took. So if you did do the ACPI path and went into the BIOS and then back out of the BIOS and way back, that tells you how much time you spent there. That's not plotted on here, but when you're comparing suspend to idle and ACPI, that's one of the big differences is this firmware tax going through the BIOS. Another thing I meant to say is, if you have something that's in red like this, you can hover on that and click on it. It will take you to the D message. So here we've got, well, this one has ftrace, which is another option, but you can click on this as the D message of your suspend, and then the log. Remember those commands like lspci and that stuff? All that stuff for the run is in the log. sometimes very helpful. Let's see, here's the dev version, and we already showed dev and we already showed mem, so I think we've done that one. Oh, here's an interesting option. So there's an option, sometimes you care about how long it takes to suspend, do something very short, and then suspend again. So there's a special option called X2, which says back-to-back. That's why there's sort of 2 of everything. And with the proc option, it will trace all the processes that are running. So you can see SleepGraph itself is running, and GNOME shell, and you can see how much CPU time it's using. So you can see if there's user space getting in the way of your race back to getting to suspended. All right. Okay, so originally we created SleepGraph. I think it was called Analyze Suspend originally, and we were sort of obsessed about the performance because we thought our performance really needed improvement, and that's what we focused on. And then the performance got to be acceptable, and we'll talk about, maybe I'm interested to know what acceptable is in your opinion. Then we got to a point where, well, okay, but is it reliable enough that we can basically base a product on it, right? And we can talk about how reliable that is, but the tool became a stress test tool in addition to a performance and a debugging tool. And so the way to do a stress test is this is, well, O stress out. So we're stressed out, we'll send it to stress out directory. If you add the multi 3.0, 3 means do 3 iterations, 0 is just how much time between. We're also going to add this Wi-Fi option. I'll show you that too. And then it will create a subdirectory where all your tests are, and it will summarize them all for you. Okay, so you could do, you can do this in a number of ways, but we'll just show you the example of the summary for 3. This is what you'll see. If you did 100, you'd see of these, it estimates when it's going to be done based on how long it's gone so far. And at the end, it's actually writing 3 files. The summary, there's a summary for devices because you may be trying to identify the slowest device. And then there's also a summary of issues that it has found. It looks through all the logs for keywords like, abort or panic or, all these really nasty words. And we'll show you those. So here's a summary file. And since we've got a 3, we have a fastest, a slowest, and an in-between. And so the min suspend, reading from left to right, is 465 milliseconds. It happens to be on the last one. So if you have a whole file of these, you can actually click on the guy and find him in a list of 1,000 or what have you. If you want to say you're looking for the worst case, you can easily find it. Similarly with the resume. Then we single out for each one what's the actual device, the device which caused it to be so fast or so slow, both for suspend and how long that one took. This guy was 291 milliseconds for I-95, 288, 279, and that's on this particular machine the slowest device. Similarly for resume, usually we're worrying more about resume time than suspend time. And sometimes there's situations where you can pay the piper for suspend time and then you're faster on resume, and sometimes the reverse, depending on the device. So the other thing is we added the Wi-Fi option, okay? So in Wi-Fi, it's going to track how long it took to reconnect your Wi-Fi. Many people would assert that you really haven't done a suspend resume until Wi-Fi comes back. I really can't use my machine if I don't have a network, right? So this is pretty important. You click on the detail for that guy, and it will take you to the graph we just looked at. Let's see, that's just the files. I think I have a Wi-Fi example in a second. So when you have a lot of data, and you've got it, in this case, you probably can't see, but that's going back to like 5.15 up to 6.6. And this is the laptop I have in my hotel room. And so this is its freeze on the Dell 9315, and the percentage success, in this case, endurance. And so we have some tools in which help summarize this data, and they're in the Git repo. The graphing part we have internally. We don't have this in the tool, but we can, if you want to set up your own database, we can help you use those tools. If you want to graph things and summarize them, just get in contact with us. Or you can send us your data and we'll be happy to throw it into our system and graph it for you. Yeah.
I was curious if there's any functional aspects of tests with the value of testing with real hardware.
Test in virtualization?
Yeah, I'm just trying to think about the other areas in the kernel that need proper testing, and if this has been used in KVM to find a.
So
Really?
RTC Wake is the default Wake device, but if you had another Wake event, the tool's perfectly happy with it. It needs some kind of Wake event.
I understand. I'm just saying.
Yeah.
All right, I guess that answers that.
Okay. Yeah. So you could do that. You could. So yeah, we don't. It's very convenient the way that we do it for automation, but we also we test wake up with Magic Packet sometimes when we're screwing around with that. You could wake up in a number of ways. If you have another wake up source, that's perfectly fine. The tool really doesn't care. It just it will work fine when it wakes up. Okay. Okay. So anyway, if you have a bunch of data and you want to summarize it, you can send it to us. Some distros do that today, and we look at it for them. And we can also help you summarize your own data. All right, so if you're doing endurance testing, there are a couple of gotchas. If you did it right now, you would probably start with your screen on, and then there's some other thing over in the GUI that says, hey, after 5 minutes, turn off the screen, and then your results will all, you'll see your speed change because you're now going into a suspend with your screen off versus with your screen on. FS trim, actually this is an open bug right now. A couple of file systems kick off an FS trim, and it happens to be at midnight. And we're looking at our data and going, we got 8 machines for here, and they're all have this FS trim bug at midnight. We're like, what the hell? You know, and it turns out they all kicked off this FS trim at the same time. What happens is it refuses to suspend, and then it kills suspend. Suspend gives up, and then it runs for sometimes a long time, sometimes like 5 minutes. It's really, really quite a bad design. It should be fixed. Let's see. When you're doing endurance testing, some things are transient, but some things fail and then they stay failed. The network's one of them. Sometimes your network goes down, stays down, and then you go into the next suspend without your network. And it says, well, I didn't have a network to start, so I'm not going to worry about it to finish. And then you're not really testing what you wanted to test. So we actually have one of the utilities you saw in the beginning was Netfix will just say, damn it, I'm bringing the network up no matter what, you know, it does software hardware reset, it does everything it can possibly do to get the network back. And we need this both for wired and for wireless. So anyway, those are some gotchas. So yeah, here's the detail for Wi-Fi. And so the kernel resume is 504, but then Wi-Fi on this particular example is another 190 milliseconds, which is not great. Not terrible, but not, we've seen worse, we've seen better. And then the total is here. We don't actually plot the Wi-Fi part. It's pretty boring. You can ask to plot it if you want. One thing we've noticed is this depends a lot on who you're connected to. It may depend more on your access point than the actual device you're testing. I noticed this because I move around with the same machine. I end up in a different hotel room or something, and it's like, you know, it doesn't work at all here, and it worked great somewhere else. So you got to be careful about that. Yeah, toss the mic over to this guy here.
Hey.
Look out.
I was thinking the same thing about it's depending on the AP actually responding, right, for the Wi-Fi. So would it make maybe more sense to just measure up until your device sends out that first association request and say, like, we tried, and that's that's the best your device
Well,
can do.
so we tried, you know, we have a lab, okay? We have around 30 machines. We're not a testing lab, we're a development lab, and we co-op our development machines on weekends to run these tests. And so we have some control over that, yeah. So usually it doesn't change on you. I'm usually not on a train or in transit when I'm running this. So it sort of is what it is, but you'll find like, sometimes this will be 3 seconds and sometimes it's 0. Sometimes you come up and it's already on, which is the best.
I mean, that makes sense in your lab, but what about like if I'm doing it at home and like, or I'm running it somewhere that I don't trust the Wi-Fi network?
Maybe we want a shortcut option. Right now, Todd has this thing where he's polling some sysfs file that indicates you're connected, proc, something, blah, 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 wireless. But yeah, you're right. There might be something more deterministic. Good suggestion. Let's see. Okay, so that's sort of all I have for screenshots and use of the tool. If there's any specific things on the tool, now I'd like to, how are we on time? Are we keeping track of time? We're at 54 and we got till 1/4 is that right? Okay, great. So I have a couple of slides which are kind of going to try to impart the wisdom we have learned, but also questions for you. And if you have questions for me, this is a great time to just throw them in there. So I think we'll all agree that job one is if suspend resume's not reliable, nobody's going to use it because your session will get lost, right? Your whole idea is you want to save your session. So that's job one. Job two is if it takes a long time, they're not going to use it either. They're just going to leave the system on and shut down at the end of the night or what. So today, the acceptableness measure seems to be around a second, right, for a laptop. You know, a lot of people use a lid to open and close, and you know, you took half a second just to get the lid open. However, that's not the only use case, right? We have a touchscreen. Really, people expect that to be instant on, instant off, right? You want to make it look like the system never went to sleep. And the third one, which is probably the hardest, is that you know, if a packet comes in and you do dark resume, screen stays off, you process the packet, you want to get to sleep, all that time that you were awake is time that you're not saving batteries. So really what you want to do is, you know, wake up, you want to get to sleep as fast as you possible, and you want to reduce that, you know, that X2 time, you know, that the time to the next wake up. So I think these are sort of the drivers. I don't know if there's any other drivers for performance. Acceptability. That's where we're at today. How much endurance testing is enough? Well, the most important is that the very first suspend works, obviously. I find that, you know, if you do it once, you might as well do it 10 times. It only takes a few minutes. And most functional issues you'll find in the first, second, and then this diminishing returns. After 3 minutes, you're in go get a cup of coffee, or you've set the machine aside, you might as well do 1,000, right? So when somebody says, we're doing 50, I'm like, well why bother, right? Do 1,000. There are device transient issues which we've run into. We never would have found that FS trim issue if we hadn't run over midnight. In our testing, usually a machine, if you do it overnight, it's either a 12-hour or 24-hour run, just for practicality of accessibility to machines. We have some distros and some validation people who say 10,000. I don't know where 10,000 came from, but today it seems the gold standard is if you have 10,000 and everything's perfect, ship it. Yeah, that's where we're at. I don't know if you have any other opinions on that. I'd be interested. Let's see. One weakness which I think I've mentioned already is, you know, device driver and their suspend method can return failure. And if they do, the core says, oh my God, you know, there's, you know, you're driving a car and we don't want it to drive off the road, or who knows what this device is in charge of. So we abort the suspend. It's generally, in our experience, bad. It's generally not a good idea. The classic counterexample would be, I've closed my laptop, I've thrown it into the case, it's in my lap, and now it didn't resume. I wake up and the battery's dead. And so, you know, we really, you know, this is the architecture, and for right now, what we're in whack-a-mole. When drivers do this, we tell them not to. That's sort of. Did you have a question on this?
A lot more comment than question. I mean, I would say I agree with you unless you have spinning rust in that machine. Because if spinning down the drive fails and you think you're suspended while your drive is still running, you'll be in trouble, like big trouble.
So you're worrying about a mechanical system, right? The other one I picture is we used to have these tape drives. You know, you can't shut off the power when it's got the tape is flying in the air or something. So, yeah.
No, but there are still. I mean, that's the problems I'm dealing with. There are still a lot of people with laptops that have a 2.5-inch ATA drive in there.
Yeah.
And so.
Yeah. So
some
analog world needs a veto, basically. So it has one.
Super interesting talk. Thank you. This is also the question is it more important to terminate or not terminate if something fails, right?
It depends on who you are.
Exactly.
Yeah.
Exactly. So I'm thinking, like you're saying, it's generally better to not terminate. But if you do not terminate, then you could get into like a power state that's like not really deep enough, and you don't reach S2 idle, and then it's in your backpack, but it's still. Whereas if you do fail, now the user space can keep retrying.
Now the fantasy begins, right? Yeah, the fantasy is that somebody deals with it. The problem is I closed the lid and put it into my case, so nobody's doing anything. Some software could look at it, but in reality, what we have is sort of like, in the previous resume, some device failed to load its firmware, hardware error, reset 3 times, and then the next time we suspend, it says, hell no, I'm totally screwed up. And then we're like, well, now, you know, if we suspend into BIOS, that thing might have got healed by getting a big hammer on the head by the BIOS, a reset, or just the fact of reloading it again might have fixed it. So.
Problem of some driver people thinking that they are the most important people on the planet because their driver is obviously the most important driver in Linux, and therefore if it cannot suspend, then the system should not suspend as well. But the reality is, in the majority of cases, that user may not even know that the device is there, because like a Bluetooth adapter that's never turned on actually by the user or similar, right? And
the cases we hit are what Raphael talks more often than yours. I acknowledge that the real world exists, the analog world exists.
Yeah, and that's why there is a way for a driver to refuse to suspend, right? Because there are legitimate cases in which that is the thing you should be doing. But
I was going to comment a little bit more on the case I raised, is that say you have spinning rust on your laptop, fails to spin down on suspend. If you continue, what is going to happen is you're still going to cut the power to the drive, which is fine because then it's going to spin down, park the head. The problem is that users complain because then they see, if they go to their smart data, they see unexpected power loss counter increasing, and
that would definitely be a bug. Yeah, we shouldn't do that.
And we shouldn't be doing that in the first place.
We get it.
Sure.
We get
but
it.
etc. But I would agree. Continue on that case.
So there might be a better way to please both camps on that one. The second one is, and we were talking about this earlier. So we've got runtime suspend versus system suspend. If a device runtime suspends, it's possible that then we system suspend. We can leave it suspended. We can come back. We can leave it suspended when we resume, and the suspend and resume goes faster. Or there's another case where it needs to resume, particularly if it needs to, on the system suspend path, it needs to PM runtime resume so that it can arm its wake-up devices. And then we've got to wait for it to resume so that we can suspend. And that's something we run into. I think this mic's not working so well.
No. So I need to stand up because then people don't see me. So I would like to comment. So there is a difference between runtime PM and suspend resume regarding the handling of wake-ups. So the runtime PM will always enable device wake up. Because it has no reason not to do that. Whereas for system sleep, the user or the admin decides which devices are wake up devices. So it very well might happen that your system, the device can wake up, but the sysadmin doesn't allow it to wake up the system as a whole, and therefore it has to be reprogrammed on the way into system sleep. And so it may be necessary to resume it from runtime PM, suspend, and reprogram, and then suspend again.
We need both cases.
Which you really don't want to do if you have an HDD, because resuming takes like 20 seconds until you speed up.
I'm not going to say that I don't care about ATA drives, but I'm just going to let you know that you're the only one in the room that has one.
I don't want to care as well, but I'm the maintainer and I have to deal with people complaining about problems. So
acknowledged. Okay. So anyway, this is something we wrestle with, and so I thought I'd highlight that. There was a UConf session on Android. I don't know if anything there bubbled up that we should talk about here. I looked at this. I'm sorry. I think Raphael was there. I saw the slides. It was a lot about the dependency, the device dependency ordering, and some.
Yeah, so this is a slightly different use case because we are talking about laptops mostly here, right?
Yeah.
But Android has a usage of system sleep, which is much more like a runtime kind of thing. Because
runtime's a big deal.
They suspend a lot and resume a lot. Whatever screen goes off, basically, an Android phone will suspend. And then resume when you turn the screen on. So they really are on the very far edge where they need super short suspend resume times and all of that, and the architecture is different. So yeah.
Yeah, but I don't know if anything architectural bubbled up. Why don't we get a mic over here?
This is perhaps a little off topic. Maybe I'll talk to you afterward. But I would be interested in a little more background on how the skip and autocomplete stuff for runtime PM works in conjunction with regular suspend and resume, because it doesn't seem like it. Okay.
All right.
It doesn't seem like it works the way you'd think it would work. But anyway. Okay.
Maybe it's broken. Okay. Let's see. So a couple more lessons from the Endurance Lab. Consistency is remarkably difficult to maintain. We talked about the Wi-Fi router. In our lab, somebody comes in and changes the BIOS, or the device firmware, says, hey, I just updated the distro. My favorite is, I travel along the East Coast. I end up in Florida, and my machine took longer to suspend resume, and because something was waiting for the temperature to lower, it was warmer in Florida. We did not expect that. I'll probably say this a couple of times. We can test the same machine over and over. It's diminishing returns when you get past 1,000. What we'd really like to do is one test on 1,000 machines is more valuable than 1,000 tests on one machine, because most of the problems we run into are devices, and we get to the diversity of devices across different machines. For us, a remote automatic power reset is invaluable, but we've also got some prototype machines in there, and so sometimes that's super useful for those. For some reason, we start to use these USB Ethernet things. Those are a real pain. I don't know if there's a gold standard for them, but we're always ripping them out and stamping on them and putting a new one in. We talked about Wi-Fi wired. We talked about preventing suspend. Oh yeah, here's interesting. So yeah, performance regressions happen constantly, even up through RC8. We find a majority of issues we run into are device specific. Actually, here's a list of some interesting bugs. Let me see. Yeah, so some of them very interesting, very recent. I mean, thank you for rewriting the console driver, but 100 milliseconds is a long time in our point of view. We do get to bisect. You can look at those later. I don't think we have to dig into any of those.
Yeah. So one comment is, I'm not sure if you have that on your slides or not. So we use that test infrastructure for regression testing. A lot. Like we test every kernel version that comes
Every
out.
RC, yeah.
And to catch regressions.
Yeah, so I don't know if that graph I showed, it showed all the RCs along the bottom axis. And so it's actually a pretty good cadence for us because we get access to our machines on the weekends, and that's when a new RC comes out, or at least it comes out on Sunday. And so it's great time doing overnight tests, nothing's going on.
Question. As a developer, how can I try not to break suspend resume for you?
The best way is to test it before and after whatever you do. Probably the most important thing, and Raphael will reinforce this, is that when you have a new device that it has suspend resume support. A lot of people will write a driver, here's my new device. Yes, I don't know, sent a packet, received a packet, I'm done, right? It's like, well, no. And copy the other device drivers that actually have suspend resume support to make sure that that works. That's really the biggest gap is like this, no support at all. We've talked about a little bit about low power idle. Low power idle depends on devices being in a low power state. And sometimes you may benefit from having even a skeletal driver that just gracefully turns this thing you're not using off, because sometimes if you don't do that, it interferes with the entire system getting into a power saving state. So a skeletal driver that does that before the big fancy one's ready, that's useful.
There are other like hints, like if you already have like a suspend method, maybe don't use sleep in it.
Yeah.
Use something else.
We're waiting for you when you're sleeping.
Yeah.
Yeah.
Sorry, I have another question.
So.
I have a question about your testing. In your lab, are your devices plugged in, or are they running on battery, or do you like plug them in and mock out the battery?
We have all combinations, but usually often what we do is we disable the battery and put it on an AC power meter so that we can monitor the power for other reasons. That's like a form factor device. So we sort of have to do some surgery on it. Not all devices allow you to do that. So we have all combinations. Yeah.
Very cool.
Oh yeah, so here's another random topic. Hibernate to disk. We've been neglecting it for years, and then we're starting to hear about people are using it again. It's actually disabled by default in Fedora, Ubuntu. It's configurable in SUSE without any surgery. Fedora and Ubuntu require some, advanced administrative skills. The reason is that the images are not encrypted. I don't know if there's renewed interest, and I don't know if Hibernate will be used more often when that is addressed and it's easy to enable again. But there's not opinions.
It's being used for virtual machines. If it's cheaper to run virtual machines at certain times of day when the cloud provider is less busy, then they will suspend to disk and be launched when it's cheaper.
Launched later.
And
yeah.
Suspend to disk is being used for that.
Okay. Yeah, that's what we've heard. I don't know if there's other use cases.
And we're using it on Chrome OS now, so we're integrity, and it's working pretty well for us right now. So we're trying to send things upstream to improve it as well, because it is important. At least
all right, so maybe Chrome is pushing this. And so from a user's point of view, will they know Hibernate versus sleep? Will they have an option?
This is a product decision that's still in progress. But I mean, as of now, the primary things we're trying to address is your battery's about to die. You don't have to lose all your work.
Right.
On Chrome OS, the default behavior is shut down after a couple of days. Now we'd rather hibernate.
You might as well hibernate. Right.
Exactly.
Yeah.
With Chrome OS, we don't do options. What you get is what you get.
Yeah.
So from the Fedora perspective here, since Fedora's mentioned over here, in Fedora Workstation and Fedora KDE, we are very, very interested in having this work again. Actually, I was asked on Monday to find out more about this, and so that's I was trying to find the requisite people about this. So if this actually does become a thing again, like we will instantly turn it on for Fedora Workstation and Fedora KDE, and it will be available distinctly as both sleep and suspend modes.
Yeah.
So we want it like now, like very now.
Yep.
from the Android perspective, there are some devices that would benefit a lot from this because Android takes a lot of time to boot. Being able to sort of have the system ready to go from
An image ready to
flash,
resume,
and then,
yeah.
like for example, you turn your car on instead of waiting like a minute for the IVI to come on.
Yeah.
You sort of unsuspend from disk. That will be way much faster.
Yeah, unfortunately, our unsuspend from disk isn't particularly fast. It's faster than it used to be. But yeah, reading an image is ready to go. You can have a lot of stuff already initialized. So that is a savings there.
Yeah.
So I guess the input is that, okay, yeah, there's still simmering interest for this and maybe some active use cases right now. We really haven't been paying a lot of attention to it. I mean, when a bug's filed, we'll look at it, but it's not something our team has really been testing.
The main problem for us, that why we have it turned off in Fedora, is because it's automatically switched off at the kernel level when lockdown is switched on in secure boot.
Right.
So you can't do it without some way to make sure that the RAM state, that's when it's saved to disk, is not able to be hijacked and manipulated when it's offline.
Yeah.
So that's supposedly what their guys' work is supposed to fix.
Yeah, so to address that, we're doing DMcrypt, DM integrity, where the encrypted payload is derived from the user's password, and then the integrity metadata is also layered with DMcrypt with a
Right.
key derived from a TPM. So
All right.
that's how we're addressing
We
the
have 2 minutes, so let me just hit my last 2 slides, see if a couple of punchlines. It seems like I hit a sensitive topic, which is great. The lessons are, we've achieved a certain amount of endurance, but we found that we need to constantly test it because we do get regressions all the time in every RC, particularly RC1, but dark suspend resume is particularly important for the speed case. Low power idle, I didn't really talk a lot about power, but from an Intel point of view, that's sort of all of our laptops go out with that today, and it basically has to work. ACPI S3 is sort of dwindling, but it hasn't completely died yet, and Hibernate we just talked about. I think in the next 10 years, we do have these other states. They're still in use. We still do have to support them and test them, even as we lean into, say, like the suspend to idle case. And we must continue to test, and we must, and we should try to test on a more diverse set of peripherals. So like you guys from the distros, we would love to have you guys every night, give me 1,000 tests on some interesting assortment of machines. Our team would be happy to look at your failures because it's something we can fix before it gets upstream or before it gets to a customer, instead of the worst case is, oh my God, the customers are failing. Can you help us with this thing? And then it's a big emergency. It would be much better to get it done before it releases. Yeah, you got a mic for this guy?
Big question, the fix for the closing bracket, do I send it to the kernel tree or to the GitHub project? What is, huh? Okay, thanks.
So quick question. If we run like a regression test and we see that something fails with suspend resume from upstream and we identify which patch it is, what do we do with that patch? How does it get
Well,
reverted?
it's an upstream patch, you can report a regression on LKML, you know who wrote it because you have the patch. There's kernel bugs, though. It depends on the subsystem usually.
Okay, but that's something you can always do. So there is a list, Linux-PM Vger, and you can see your bug report to it. So we know that there's a system resume issue, and then let the regression trackers pick it up, and I know if you go basically. What is the address? Linux-PM at vger.kernel.org.
Yeah, which is in the maintainers file.
Yeah.
I think, are we kicking us out? Have we hit your time? Yeah, okay. I'm afraid we're after, Raphael, me, catch us in the hallway. Thank you very much. That's right. That's right. Do you want to use this?
I run sleep trash. It's just like
I like.
Right, I can debug this.
How you run it, you can get the so, but it's all describing the documentation. So the example execution kind of just made it without such. Yeah. I would any other way. Yeah, you can just use syzbot as your default like suspend the script because that's.
Good morning, everyone. I'm Sweet Tea. I work at Meta on ButterFS type stuff. I still haven't recovered from the name change to MetaX, so my Facebook is still on the side. Sorry about that. Before I worked on ButterFS for the past year and a half-ish, I worked on a device mapper target at Red Hat. So I have seen many different options for encryption running around. And today I want to talk about encryption for file systems with advanced features, which is what I've been working on for much of my time at Meta. So I'll that case. I'll start over. Good morning, everyone. Now I can hear myself. I'm Sweet Tea. I work at Meta. I still haven't recovered from the name change, which is why Facebook is still on my slide template. Sorry about that. Before I worked at Meta for the past year and a half on ButterFS stuff, I worked at Red Hat on a device mapper target. So I've seen encryption in the kernel in different areas. Today I want to talk about the work I've been doing for much of the time I've been at Meta, encryption for file systems with advanced features. So I want to go over, first off, what FSCrypt is and does and why we care about integrating it into file systems with advanced features. The extent-based FSCrypt that we've been working to get upstream over the past 2 years, then some of the details and the history of how we got to where we are now, and then some of the future goals, which include getting FSCrypt into more file systems all the time. So first of all, I want to apologize. I'm not a cryptographer, so please don't judge my cryptography too badly. The glorious thing about FSCrypt is that it uses the kernel crypto layer, and people much smarter than me have already dealt with that part. So I, as a file system person, don't need to know very much about crypto. I also don't want to be judgmental about what an advanced file system is. Ext2 is a perfectly decent file system. The file systems that currently use FSCrypt are also glorious file systems. It's just a convenient way to refer to file systems that have ref links or subvolumes or snapshots or checksums and things like that, which, well, this is probably not an exhaustive list. I would claim that ButterFS and XFS and Bcachefs, I suppose, all count as having the features that would make me call them advanced file systems. I put an asterisk on Bcachefs because it has its own thing. And I'll talk about that more at the end. So how many of y'all here in the room have used FSCrypt, have developed with FSCrypt, have even heard of FSCrypt? Okay, so about half of y'all. So I'll run through it quickly to provide a general summary of it, especially for the folks remotely who I can't see the hands of. Basically, it's a kernel library providing standard encryption features to file systems which choose to call the FSCrypt hooks and the FSCrypt functions at appropriate places. My impression is that it was developed for and is used widely on Android, although I don't develop on Android, so I don't know personally. Currently, it's integrated into several different file systems. Ext4 was where it began, F2FS, Ceph, UBFS. Currently, Ceph was just a year or so ago, I believe, which was pretty exciting. Really, only a couple months ago. I've seen patch sets for a very long time. So very cool. The fundamental idea of FSCrypt is that it integrates your encryption into the file system layer. So the idea is you have one master key per directory tree, but you can set encryption up on different directory trees as long as they don't overlap. You can have some unencrypted base directory and then have various encrypted directories within it, all of which have their own separate keys. But you can't mix keys within a single tree. So you can't say, oh, I've got this encrypted tree. Let me change the key of this new folder within there and have a different key up this subtree. Another key feature of FSCrypt from the user's point of view is that you can delete files if you lose your key still. So you don't have to reformat like you would with a whole file system encryption solution. When we were thinking about it for ButterFS, we contemplated the notion of encrypting everything, the file metadata, the file system metadata, everything with a single key. But the problem with that is that if you lose that key, you then cannot ever delete those files. You never get that space back in the best case. And that's a trade-off that isn't acceptable for many folks. Now, the one biggest trade-off of using FSCrypt is that it does not encrypt everything, as I just referred to. It only encrypts the file names and the file data. If you use a block device-based solution like Lux with decrypt and so forth, that encrypts everything, which fits a different threat model. Some people believe that file metadata is sensitive. Some people don't believe it's sensitive. It depends on your threat model. There's nothing stopping you from using both of them, although it seems a bit redundant to use both a file system with FSCrypt and also a device mapper target with encryption also. FSCrypt has been uses one of two different backends. It can use the standard crypto API, or it can use the block layer crypto. With block crypto, it's really elegant. The file system never sees encrypted data, which is beautiful. And technically, the encryption information is stored within, on a per file basis. It gets loaded off disk by the file system and provided to FSCrypt, which hooks it into its inode info with instruct inode. When the file system then goes to write file data, it needs to call an appropriate encryption or decryption function, depending on IO direction. It retrieves the encryption info out of the inode and encrypts it based on the file and the file offset. There are various ways of deriving the key. From the user's point of view, it's not very important. It's gloriously abstracted away from file system developers, which makes me happy. However, this way works very well for many file systems, but with the advent of reflinks, things get a little more complicated. Subvolumes get a bit complicated. And block crypto is a very elegant way of keeping the file system from ever having to deal with encrypted data itself, but it can be awkward for checksumming. As I mentioned before, FSCrypt doesn't allow you to have different keys within the same tree. This becomes very awkward if you have a subvolume inside of another subvolume. I mentioned the elegance of block crypto, but it's unsafe to store checksums of plain text along with your encrypted data for probably obvious reasons. You could just, and most of all, reflink becomes extremely awkward since you could have one piece of data reflinked in two different files with two different inode infos at two different file offsets. Trying to make those work in the existing FSCrypt model is rather awkward. So when we looked into hooking it up for ButterFS, we realized that we would need to expand FSCrypt to be able to do more things in to do more things. We've been talking about encryption for probably 10 years now, but ref linking and checksumming are very important to Btrfs, so we didn't want to give that up. It's very exciting to allow Btrfs to do encryption on a per subvolume basis, because then you can have a bunch of different users, all of which have different keys, none of which can read each other's data when each other aren't logged in. There are other interesting, unlike with the block device-based solution, it's very easy to add more storage to your Btrfs file system and choose later on whether you need to, whether you want to use that new storage as encrypted or unencrypted. So it's a lot more, it's a different trade-off than with LUKS. So the idea is just that instead of just having that inode encryption information, we also stick some encryption information on a per extent basis. I assume that everybody is familiar with the notion of a file system extent. But with extent-based FSCrypt, we encrypt the data based on the extent plus the offset within the extent of the data instead of going off of the inode. Suddenly, you don't have issues with reflink anymore. It's great. And we can also store the key that we use to encrypt within each extent, which opens up a vast possibilities of having a bunch of different keys. Maybe you want to be super paranoid, and maybe you want to give each systemd service its own encrypted subvolume and delete everything afterward. Terrible for logging, but maybe you're paranoid enough to do that. Obviously, though, for file systems, they usually have quite a few more extents than inodes, so it does take up more metadata space. Some work that one of my colleagues did indicated that on a representative file system, at least within Btrfs, you have about 4.5 extents for the average inode. So it ends up being quite a bit more metadata than just storing 50-ish bytes per inode. But on the other hand, it's still a very small structure, very affordable. So we started working on this back in October of 21. Omar Sandoval started the work. One of the things that I think was really great was that we sent out design documents with each design before actually reducing it fully to code and patch sets. This allowed various community members who might not be technically able to review the patch sets to be able to review the design and comment on the suitability of it. So I think that was a really good thing that we did. However, some of the difficulties with having design documents are that folks really want to see code. And so there can be a mismatch of expectations there. And you can get several months into it, and then the code for a particular design turns out not to be safe or not to be quite as glorious as you were hoping it to be. We redesigned it in November. I inherited the project from Omar in March-ish of 22, sent out patches for it, redesigned it in November. FSCrypt is hoping to mostly aim toward using the block crypto interface in the far future. So we implemented extent-based encryption just for the block crypto side of FSCrypt. It's just a compile time option. It's not particularly onerous. However, I was overly committed to elegance and wanted to do away with inode contexts entirely and just have extent contexts, which is elegant, but not optimal. It used extra space, and so we ended up throwing out that. Also, we've got a third design going on now, being spearheaded by Joseph, who is doing glorious things with it. It's a lot smaller. It doesn't yet support nested subvolumes. It's just the bare bones that we need for Btrfs, but it has the information stored on disk so that we can one day expand if we need to have nested encrypted subvolumes with different keys. We added a callback to block crypto in this patch set, which checksums encrypted data, since you really don't want to checksum unencrypted data. Currently, it uses the block crypto fallback stuff, which is not as widely used as block crypto proper. So there's a little bit of risk there of unexpected things. There's a link to a patch set here. It was definitely hoped that we would have it in by now, but it's not in yet, so please go review it. It should be extendable to other file systems pretty easily. It still doesn't allow changing keys within a single tree, but we can add that very easily in the future. We do require the use of block crypto, but as mentioned, FSCrypt is moving toward using block crypto altogether. The callback part, the callback addition to block crypto is a little bit awkward, and we'll get to that later. And it makes encryption work for ref links, and it's really glorious. One day we might even be able to have ref links between inodes that are using different keys, because the extent can use the same key for both of them. Why you would want this? Maybe a good question. I haven't actually come up with a good use case for this, but I want the possibility to be there. Obviously, we're trying to get a minimal patch set in that addresses all of our essential needs, but we've got several future goals because, as mentioned, there are a bunch of alternatives to using Btrfs with FSCrypt or using any of the other file systems using FSCrypt. One of the hottest topics of the moment is Bcachefs, which does things absolutely differently. It doesn't use FSCrypt. It encrypts the entire file system with only one encryption key, which has different trade-offs. As mentioned, it doesn't fulfill our desires to have per subvolume keys. It does have subvolumes, but you can't set a different key for each subvolume. You can't delete anything without, if you lose the key, you have to reformat. It also, in a really cool innovation, it uses authenticated encryption instead of encryption plus checksums. Basically, the idea here is that instead of taking a checksum and then decrypting, the encryption and the checksum are key dependent and happen at the same time. So this is cryptographically more secure and excellent. I'm not a cryptographer, so I can't tell you too much more than that. I'll talk about it a little bit more later. And Bcachefs currently, as far as I understand it, has a single choice for encryption algorithm. So there are interesting questions about many people have different requirements. My understanding is that some countries require you to use a particular crypto algorithm for various reasons. If that were the case in your country, then Bcachefs would not currently work for you. I also mentioned that deencrypt plus deemintegrity are the most common solution for encryption. It presents itself as a software-defined block device, so there's, again, only one encryption key per file system, assuming that you partition with LVM and do LUKS on top of that. Again, no access to anything even for deletion when the key isn't loaded. Again, it has the option of using authenticated encryption. It also has the possibility of changing your encryption key, which I think is a very important feature for the future. Sometimes you need to change your encryption key because somebody stole it, or you need to change to a newer encryption algorithm, and LUKS has the possibility of re-encrypting your data, which is cool. So my aspirations are to bring FSCrypt up to add these features to FSCrypt within the realm of feasibility. Obviously, I don't want to have whole disk encryption for the reasons elaborated, but being able to change the key of your data is pretty cool. Fedora has a proposal to possibly use ButterFS encryption in a multi-step encryption process where each individual contributor to the final laptop image has their own key and re-encrypts the stuff that the previous layer in the stack encrypted with its own key. So that's a possible use case there. Meta once and might again in the future want to install a package in a subvolume and then give that subvolume a key, have everything written by that package in that subvolume be encrypted, so that when we shut it down, we can easily securely delete whatever that package ended up writing. We have other solutions for this. As I said, we once wanted to do this. We found a different solution for now. We might one day want to do it in the future. We'll see. However, there's interesting questions about how to implement changing the encryption key for a subvolume that already has encrypted data. One way we could do it is to have, on a per subvolume basis, have the key that's inherited by new extents for new data being written. And then when you write new data to your ButterFS subvolume, you look up the subvolume, grab the key, and use that for your new writes. This means you would have multiple keys potentially being used within a single subvolume, which is a bit awkward. Then you have to load all of the keys for the subvolume to be guaranteed to be able to read everything in that subvolume. There's also questions of whether you do this on the fly, online, or whether you need to do this offline or something else. You could alternately have a per subvolume key and have kernel space recursively update as inodes are accessed and re-encrypt. You could have user space recursively re-encrypt things. Interfaces are hard. If anybody has comments on how key changing should work or would be most effective for your file system that doesn't currently use FSCrypt, that would be really cool. Also, as mentioned, authenticated encryption is available from Bcachefs and from Lux. Authenticated encryption detects corruption in a cryptographically clever way and means you get EIO instead of some sort of corrupt data, which is helpful. Historically, FSCrypt hasn't had it because it requires storing an authentication tag on a per block basis, and many file systems don't have the space to store basically a checksum per block. ButterFS obviously already has checksums, so a long-term goal is to store the authentication tag and the knots used per write in the place that we currently store checksums if you choose to use authenticated encryption. DM integrity does magic with device mapper to store the authentication tags, but they do it in their own DM side of the world. It's not in block crypto at present. So it might be interesting to pull some of that to make FSCrypt use block crypto to do authenticated encryption and then return the authentication tag back to the file system in some fashion instead of having a callback to do checksumming of the encrypted data as the patch set currently has. It has exciting implications for ButterFS scrub and relocate and nocal files. If you need to have the key in order to read the data and generate the correct authentication tag, that becomes a bit awkward and you have to end up leaving your data in place if you don't have the key. But regardless, it would presumably be an option, not required to use authenticated encryption. And once it's in, hopefully that will become an exciting option for ButterFS. And my chief goal, of course, after some version of the extent-based FS-script patch set is actually landed upstream is to help other file systems adopt encryption. So I'm very interested in hearing what keeps your file system from using FS-script and how I can enable folks to integrate it into their file system. So with that, I'll open it up for questions and thoughts about rolling keys, block crypto, authenticated encryption, your file system's challenge with FS-script, anything like that.
So you mentioned changing keys. My understanding, at least with FS-script from my work with it, was that you really don't really have the option to do that other than to copy data, right? You know, essentially what you need to do is copy your data from one to the other. I don't know if there's a way around that really. So
one way that I could, I mean, yes, you do eventually need to do that if you want to use the new key. If you could have multiple keys in a particular directory tree at present, then you could say all new writes are being encrypted with the new key and everything you used to write is using the old key. You could have a background job that attempts to re-encrypt things to the new key, etc. Is it a thing that Seth is interested in?
I'm sure they are probably. I'm not really working on Ceph these days, so. but you know, it's but yeah, I mean, you know, being able to change keys is kind of a nice thing. I don't know that they're going to want to move to the extent-based thing though, because the storage requirements are pretty onerous. You know, for some. I mean, you know, you have your question up here. What keeps your file system from using FS-script? And I started looking at it for NFS too, but the big problem we had with Ceph was is tracking links. So the server is mostly a client. Storing data out there, but the file marker lock as far as the server is concerned, right? But the actual file. Getting that right. Difficult actually is that was one of the big hurdles. So I'd say that, you know, if you want to look at you need to be able to track two different links if you're working in a network file system. And I really think FS-script is probably most compelling in network file system case, because one of the things we always want to be able to do is, here's a big chunk of data, you guys go have fun over here, right? And being able to encrypt a subtree of that is very powerful feature.
I'll be the daring one and say something. So, as you mentioned about the changing keys thing, maybe you covered this earlier while I wasn't here because I got dragged into another conversation. But what are your thoughts about handling like when you have to do cryptographic upgrades and stuff like that? Because that's like the big concern I've had across all these different encryption systems has been cryptographic upgrades aren't really supported, and that scares the bejesus out of me because every once in a while somebody says, this algorithm is close to being broken. Oh, this algorithm is now broken. You can't use this anymore. But then, you've got this added complexity of your data is basically stuck, and if you and you can't really do anything about it, and you don't have space to do the whole whoosh. You got to move everything over and then whoosh, move it back. So, what are your thoughts about solving that particular pain point? Because I think that's a pretty universal one with how disk encryption has generally worked in Linux.
I think that's basically the same problem as changing keys.
Mm-hmm.
So whatever solution works for changing keys can probably be relatively trivially adapted to change crypto algorithm altogether.
Yeah.
Probably not from non-authenticated to authenticated, though.
Yeah, the reason I was kind of worried about this is because like some of the different systems and mechanisms, like over the years that I've used some of them, have been kind of picky and choosy about which ways they want to do it, and sometimes they've been not so smart about how they've encoded what your cryptographic choices are into these into the data, and like these are the sort of things that it's just like, now that you're introducing encryption to a new thing using a new subsystem with a new way of doing it. Have you thought about, like, how to handle this case? Because it would be nice to not repeat this mistake again, again.
So like, at least for FS Crypt, the nice thing is like the downside is the upside. The downside is that we store all of this bullshit with everything, which means that we know the policy that's currently in use. So it's a matter of changing the policy and the metadata. And so that's the tricky part. And like, which is why right now the FS Crypt answer is just copy create a new directory, set the policy and whatever on that you want, and then copy all of your data into there and delete the old one, right? ButterFS has the ability to do this sort of in place because we're doing it on the extent state. So like, again, the overhead sucks, but the nice thing is the overhead allows us to essentially have multiple policies per inode. Now, right, we can't do that right now. We don't we can't but that's a software thing. It's not a metadata disk format change. It'll be a thing that like, okay, we've decided this is how we want to make it look. We just decided this is how we're going to do it safely. And then ButterFS already has the ability to with defrag or whatever, rewrite stuff. So thankfully the format and everything makes this future proof that okay, we've decided that this policy is bad, we want a new policy, then it's just a matter of hooking up and coming to an agreement amongst FS Crypt and everybody else of okay, we agree that this is safe, it's okay to do this, and now we can go do it. But as far as future proofing it, we're pretty future proof, right?
Anybody have any more thoughts about FS Crypt? We've got.
I have a question that's maybe for Jeff. I was curious. One thing I ran into when I first started this was that the FS Crypt user space tooling assumed certain things about devices existing, which isn't the case for a network file system like Ceph. And ButterFS has its own weird device numbering thing. So did you guys fix the user space tooling to handle that, or
not at all? No.
Okay.
just dealt with having this. There's a dot directory that it creates at the root of the file system, so that where all the keys go, right? We just kind of worked with that. Kind of the user space tooling for Ceph. So the Ceph team is really interested in doing this for most of the cloud providers, right? It's what they really want, and so they are looking at probably reworking some of the user space tooling and integrating it maybe into Kubernetes or something like that. So where they would have, where your orchestration tool would sort of go and set the keys for you for this particular application that you're going to run under FS Crypt on the thing.
Okay. Yeah, so that might be another thing that advanced file systems or just anything that's not single block device based might run into.
Yeah, and I mean I think this is all still very much up in the air. Actually, they're not quite sure how they want to do this yet. So looking at it.
I mean, this is kind of where I'm really, my hat is off to Biggers, right? Okay, so the tooling and stuff kind of is a little silly and its assumptions or whatever, but at the end of the day, he provided all of the interfaces to do this. So yes, okay, that's how it looks currently, but there's nothing to keep us from doing whatever we want with the ioctls.
The stuff is fairly low level, and so it's all driven by IO cuddles that you just drive into the file system, right? So you can use that to set keys however you like. We're not necessarily tied to this sort of the way he manages keys in the FS Crypt tool. So
It's a very elegant system. Very elegant. Somebody has more things, then I guess we could break for lunch early and maybe get a seat at a restaurant this time. Thank you all very much for coming.
I'm only giving you the best answer I can give you.
Yeah, it's also bad for presenting because if you go out and have lunch right before and then come out and then break state of mind. But I actually have an early lunch this time because I learned from my mistakes. I've done it in the past.
This is the next step. Basically, the source. That was a speaker.
Yeah.
I don't think he doesn't have like a concrete vision box because when we work on these lines together, we actually we have kind of just one of those questions. That these are things we need. Should be something like some kind of policy thing where you
Might bring this one up.
keep the user figure out what kind of devices.
You said everything's straight for our guests here?
Yep.
All right, good. All right, cool.
But we don't have.
So, man, how you doing?
We know that.
He's a meta guy.
All right, thank you.
Yeah, I understand. They say we're not going to be sure. You're the first. Yes.
Everything just hijacking this. Everything's ready. You should just, put yourself. I guess I'll just say my name. That's fine. I can just introduce myself. Okay. Thank you.
I'm sure you're not editing. Yeah, this is gonna be one heck of a last couple hours now. All right, do not touch the main phone, just move it back. Definitely not. It's like circle clutch.
Okay, we'll get started. I think there's literally someone sleeping in the back. Okay, I'll get started. My name is Stefan Heinutzi, and I prepared this presentation together with Michael Zirkin. Michael couldn't attend in person today, so I'll just be presenting it. So we're going to talk about trust, confidentiality, and hardening of the Linux Virteo drivers. And so what that means is I'm going to talk about the status of the Linux Virteo drivers trust model today, and also how we got here. So that means kind of the hypervisor architecture and where Virteo comes from, as well as how IOMMUs fit in, and hardware Virteo devices and Linux VDUs, how they change the trust model that the Virteo drivers had. And then we're going to look at where we're going, and that means new work that's related to confidential computing, in particularly untrusted devices, as well as trusted TDIS devices and how they will fit in with the Virteo drivers. Okay, so first a quick introduction to Virteo. Virteo is an open standard for I/O devices, and it's supported across a range of hypervisors, as well as guest operating systems that are running in VMs. So it comes from the background of virtualizations, running virtual machines. Now it's used in kind of a wider context as well. But the basic thing that you have, and the thing that we're going to focus on today, is the fact that you have a driver that is talking to the device. And we're going to look at the trust relationship between the driver and the device. So if you want to go and check out the details of what Virteo is, what it can do, and so on, there's a link to the specification. So what Virteo has is it offers a set of standard devices. This is kind of similar to USB class compliant devices in the sense that there's the standard that tells you here's how a Virteo network interface works, or a Virteo block device, or a Virteo GPU, and so on. And if a guest driver exists for your OS, then you'll be able to use that driver with any device implementation that is compliant to the Virteo specification. So you could be running your guest OS on any hypervisor that implements Virteo. Okay, so what are the applications of Virteo? This is kind of interesting just to, if you don't have a background in Virteo, to kind of understand where it's used, but it's also very important today for what we're going to go through, because these applications actually have different trust models. We're going to start with the traditional virtualization use case, which is that you have a hypervisor, and this hypervisor offers these Virteo devices to the virtual machines. That's how the virtual machines do I/O. These Virteo devices are doing I/O on behalf of the guests. Then we're going to look at Linux VDUs, which is a way of kind of reusing Virteo devices, even for bare metal and container applications. So you don't have a virtual machine there anymore necessarily. That's what VDUs does. Then we'll look at the hardware Virteo devices, which are becoming more popular, where you can have an actual physical Virteo net device or so on, like a PCI device. And then we'll look at confidential computing. both with software devices and with hardware devices. There's lots of interest from CPU vendors and cloud vendors around this right now. And this is where the most, where the open questions that I'm going to present really are, and then the work that we still need to do. Okay, so let's start and let's look at the trust model. So in traditional virtualization, where you have a hypervisor and you have a VirtIO device, the driver is going to send I/O buffers to the device, and the device will then copy in and out. So say it's a network device, then the device is going to DMA, it's going to copy in the packets that are being transferred to and from this network device. In order to do that, the devices need to have access to guest memory. So that's kind of the starting place. And in traditional virtualization, the device, especially with KVM's model, I mean, it depends on your hypervisor, but here I'm talking about Linux, VirtIO, and KVM. The devices have access to all of guest memory. So let's look at what that means. What if the device is malicious? What if a malicious device can read from guest RAM? Well, it can extract any sensitive information you have in there, any passwords, any cryptographic keys, any application-specific sensitive data. And this is basically why, in most cases today, if you are running a virtual machine with some hosting provider, they can actually see everything that's going on inside your VM. But it gets worse, right? Because what if the device is malicious or the hypervisor is malicious and it writes to your guest memory? What can it do? Easy thing is just overwriting memory, right? Can pretty easily crash your driver or your OS or your application. But the more worrying stuff is changing the state of the VM. So say you have an application that's keeping track of account balances, then it can suddenly have $1 million, right? Because you just changed that variable. And even worse is code execution. Not just changing some values, but really being able to gain a foothold inside the guest. So breaking the isolation between the guest and hypervisor. That's pretty easy to do too, right? Because what could it do? It could overwrite some instructions in guest RAM, and then the vCPU executes them. One way or another, you'll be able to do that. So what that means is that the guest is basically fully under control of the hypervisor in the traditional virtualization use case. There's not much you can do about it because the memory is exposed. And as a result of that, although the Linux VirtIO drivers, historically, of course, they've tried to follow good software engineering practices and have defensive coding and so on. But at the end of the day, there was no way they could protect themselves from the hypervisor, because the hypervisor could always scribble over memory or spy on it if it wanted to. So it's kind of futile to try and add any security in there. And that's what the state was for a while in VirtIO. So now let's look at some of these other use cases that I mentioned. They came later, and that's where we had to extend the trust model and harden things. Okay, so the first one I'll cover is Linux VDUs, because this is an interesting use case that flipped things on its head. So with Linux VDUs, the use case you have for using VDUs might be that you already have VMs, and you already have a VirtIO-based I/O stack. Could be storage and or networking. And now you want to add bare metal workloads or container workloads. What do? Do you duplicate your I/O stack and have to manage that as well? Or is there a way to unify them? Well, VDUs is a way of unifying them. You can use VirtIO devices even on bare metal and with containers, for example. If you want to check out more about VDUs and how to use it and what it is, check out that link. I'm not going to go into the details. I'm going to focus on the trust model. So what does this mean? So what VDUs allows you to do is you take the existing VirtIO driver, say a VirtIO net device, but instead of that driver talking to a hypervisor below the kernel, it actually talks to a user space VirtIO device that's implemented in user space, running on the same kernel. So that way you're using that same driver. And we flipped the model on its head. Previously in traditional virtualization, as I explained, there's really nothing that the guest driver can do to isolate itself and protect itself from the hypervisor, which has full access to the guest driver. But now what we have is we have that driver talking to user space. And the kernel shouldn't trust user space. So now we have a problem because the drivers are likely to be vulnerable. So let's talk a little bit about that kernel and user space trust model in Linux, because it's not 100% intuitive. You might think, hey, I have a root process. It can do anything, right? So why do I need to have any trust or any security? If I have root in user space, I can reconfigure the system, or I can access any user data. But actually in Linux, there's a distinction there. Even though a root process, and whatever Linux capabilities that process has, can do all these things, it must still not be able to corrupt kernel memory. And it must not be able to gain kernel code execution. And the reason for that is things like signed kernel modules and trusted boot and kernel lockdown, because they add a nuance to this, and they basically say, we're going to keep the kernel safe, and it won't be modified, unless you are able to load a signed kernel module, for example. So only safe things like that. And so VDUs has to honor this model. And as I mentioned, the I/O buffers that we have that are VirtIO drivers trying to transfer packets to a VirtIO net device, for example, well, we don't want user space, VDUs, to have access to kernel memory just in order to transfer the packets, right? Because that would be unsafe. It would be able to do anything it wanted if it had access to all of kernel memory. So for Linux VDUs, when this was introduced, and the patches were on the mailing list, people pointed this out and said, well, we've got to harden stuff. This is not okay. We need to have some layer of isolation. And the two things we need to look at there, these two arrows on this diagram here, are one, when the driver parses a response from the device, it really now needs to go through everything and validate all inputs. It can no longer trust the device because the device lives in user space and it may be malicious, so we're not going to trust it. And two, we need the memory isolation that I just mentioned. So let's talk first about the input validation, how that happened. So when people realized this, there was a community effort. It was like a multi-person effort. People went through the Linux VirtIO driver code and they audited it. They had a look at places where the drivers were fetching values from the device where there could be some danger. And we needed to do more careful input validation. And so a bunch of these patches went in. I put on one, sorry, the font is a bit small, but it's one of the smallest ones that I was able to fit on a slide. And basically what this is doing is when the VirtIO block driver starts up and it asks the device how many vert queues there are. Previously, if the device said, I have 0 vert queues, the driver would have been like, okay, 0 queues, which makes no sense, by the way, because then you can't actually use the device. And it would have just run, and it would have had some null, empty memory allocations, and trouble would have kind of occurred down the line. So this was not safe, and this patch simply just added an if statement to block that. And a number of these patches were written by people who were auditing the code. And so now the VirtIO core code, by that I mean the vring code, the stuff in drivers VirtIO, as well as a bunch of the devices have been fully audited, and they now validate all input. Another way of looking at this would have been with fuzzing, but I don't think we explicitly did this. It would have been to fuzz the VirtIO drivers by feeding them garbage and then seeing, okay, so you did it. Okay, excellent. Yeah, so that would be another way of finding these places, but this is something that needs to be done in order to harden them for the VDUs model. Okay, so back to the kernel, how to expose kernel memory and so on. So the way that this is done in hardware, like in PCI, for example, is that you have, if you have an IOMMU, the IOMMU is a component that can interpose the memory accesses between the device and the actual memory. Instead of allowing them through, it can check permissions that have been programmed into the IOMMU by the driver or the operating system to make sure that the device can actually only access certain memory regions, the memory regions that have the IO buffers you actually want to transfer to the device. If the device tries to snoop some other memory, the IOMMU will block it because it's been programmed not to allow that. And so VDUs kind of has a solution that's very similar to that. It has this IOTLB, and it has an IOCTL where user space, when it wants to process buffers from the vert queue, it has to ask the kernel, and it says, please give me a file descriptor, and this magic file descriptor will only give you access to the IO buffer pages and nothing else. And by the way, I think there's also a bounds buffer inside VDUs. So if that kernel buffer is not a full page, it copies it to a separate page and only has the payload there. That way, if the kernel had any other data structures or things on in the same page frame, they won't be leaked to user space. So yeah, the memory is isolated, and this is how VDUs solve that problem. Okay, and that's kind of the end of VDUs. So with that, it was possible to run these user space VDUs devices and use the VirtIO drivers on a bare metal kernel, and they were talking to user space, and we had fixed that, that trust relationship to make sure that we were safe, even if user space is not trustworthy. Okay, so the next use case I wanted to mention is hardware VirtIO devices, because hardware VirtIO devices are interesting because they are not actually part of the hypervisor. So they don't actually have all those same access rights that I mentioned in the beginning. I said in the traditional virtualization use case, the hypervisor can touch anything. Well, with hardware VirtIO devices, if you have a separate PCI device, you do have that IOMMU in the middle. You can confine that device so it cannot access all memory. So that's great. And we also have the hardening that we did for VDUs to make the drivers not trust the device anymore. And so with those two things together, when you use a hardware VirtIO device, there is actually more isolation than when you just use a software device that's built into the hypervisor. Okay, I think there's not really that much more to say about hardware VirtIO devices because they're basically covered by what was already done for VDUs. Okay, so next we'll move on to confidential computing. So with confidential computing, the idea is that you can deploy a workload with a hosting provider that you don't necessarily trust. Or maybe you do trust your infrastructure because you're self-hosting it or something like that. But you would like to have an additional layer of security, so if a host is compromised, the VMs aren't automatically exposed as well. So those are some of the goals people try to achieve here. And it's still a work in progress. I mean, there's been the microconference track and a lot of talks here today at LPC are about confidential computing. So still a lot of things haven't settled yet. If you want to see, there is an article about the different platform-specific implementations of confidential computing and how Power and Intel and ARM, and so on, how they do it, and a short comparison if you're interested in that stuff. But I'm going to talk about how the VirtIO drivers can be dealt with in a confidential computing scenario. So first, I want to just mention that the way confidential computing works is to reduce the trusted computing base. So reducing the number of software and hardware components that you need to trust in order to run your workload. And the unique big feature, the surprising thing is you don't need to trust your kernel or your hypervisor anymore. They're no longer trusted. So you still have to trust the CPU, obviously, because it's executing the CPU instructions. So you can't really hide anything from it. And the important thing I think to mention is that the physical and side channel attacks are out of scope in confidential computing. So it's not a silver bullet. It doesn't automatically make everything safe, and someone determined could probably still find other issues. And denial of service is another thing that's kind of out of scope. It's still always possible because even though the hypervisor may no longer have full access to everything that's happening inside the guest, the hypervisor is responsible for managing resources, so they can easily withhold resources and just not give you the resources. So denial of service is possible. So how does this work? Well, the two important mechanisms are that the hypervisor does not have access to the CPU registers and CPU state when the guest is running. So there's some protection there. Otherwise, the hypervisor could just single step the guest and see what's going on, but it can't. The other thing is that guest RAM needs to be protected, right? Because we've that was kind of our starting point here, where we said, well, if guest RAM is accessible to the hypervisor or the device, then it's very hard to isolate it and have trust. And confidential computing takes care of that. It protects guest RAM. So how does it do this? Memory encryption is seems to be like the common approach that the different implementations across CPU architectures are taking now. And that basically means that while the CPU is in guest mode, the loads and stores are transparently encrypted and decrypted. And when the CPU is not in guest mode, when it's in root mode, so it's in the hypervisor or in the kernel, then that transparent encryption is off. And so if the hypervisor tries to snoop and read guest RAM, it will just read the encrypted data, the ciphertext, and it will just be junk. So that's the mechanism for guest RAM. An important thing here is integrity protection, because just encrypting it, just having confidentiality is not enough, especially from the point of view of the VirtIO drivers. Our drivers expect that if they load a value from RAM, they will not get junk back, right? So if someone has tampered with it, we need to detect it. We don't want to read junk back if the hypervisor has just written something to an encrypted memory page. I think that's important because it's a very difficult programming model if in your program, anytime you read something, you might read junk back. So again, I think this is now the current state of the art. I think that the different CPU vendors are all offering it, but it was not from the beginning. So I'm just mentioning and pointing out explicitly that integrity protection is probably something that any sane driver that doesn't trust its device really needs. Okay, so oftentimes so I think probably a lot of people here know about confidential computing, so I'm not going to go through this, but in case there is anyone who says, prove it, how can this even work? I do have a slide here we can go back to later. If you ask questions later, I can show you, because sometimes people think, oh, how do you not trust the hypervisor? How do you not trust the kernel? But I'm going to skip that part, because we've had plenty of confidential computing content here. So untrusted devices. This is our first step. So let's say we have one of these confidential VMs now, and we give it a VirtIO device. What can we do? So let's start with networking. If you have a network interface, obviously you don't really want to send unencrypted traffic. This is an untrusted device that's in the hypervisor. You're all good. Your memory is encrypted. The hypervisor can't tamper with your state. But if you're using unencrypted network connections, you're going to be in trouble, because the hypervisor can easily tamper with the traffic that you're sending over your network interface. So that's an obvious thing, but luckily for a very, very long time, the kind of security model in the networking world has been, well, there can always be an evil router. And so you need to use encryption, end-to-end encryption. And so there's not a lot you actually need to do to secure networking in confidential computing. You can have an untrusted VirtIO device that the hypervisor provides you, and you don't need to trust it, right? You just use TLS. You just make sure your traffic is end-to-end encrypted. If it's tampered with, TLS will detect that. It can't be snooped. Of course, the traffic analysis and so on, patterns can be seen, but the data is protected. So that's VirtIO Net. So what do we do about store? And by the way, if anyone disagrees or has questions, then jump in and let me know. If you feel there are open issues with networking or something you want to mention. Okay. So next up is storage. What do we do about the disk? Luckily there are also pre-existing solutions. They weren't even made for confidential computing, but they can be used here to protect us and achieve the trust model that we need. So normally when you have a disk, maybe some data can be corrupted just due to the nature of the physical media and so on, but you're not really expecting to have a malicious disk. So with confidential computing, it can be malicious, right? So now we've got to protect against that, but dmcrypt exists in Linux, and so does DM integrity. And when you combine the two, dmcrypt gives you the confidentiality, DM integrity gives you the integrity protection so that the encrypted data isn't tampered with. So if you use those two, then you have an encrypted disk. And now you don't need to trust the VirtIO block device. Now it's okay to data there. You only have one problem. Like, what do you do with the key? Where do you put the key for unlocking the disk? And so there's various schemes to do this. I won't get into it, but it can be done. And so then you're able to use an untrusted disk. So the only missing piece here that I haven't mentioned is that if you have an untrusted device, a device that's part of the hypervisor, and you had this encrypted memory that I mentioned, how can the device actually talk to the drivers? Because the drivers, when they put structures into memory for the device to consume, that memory will be encrypted. How do the two worlds talk? So the answer to this is that the confidential computing implementations, the CPU architectures, they allow the VM to be set up so that some of the memory pages are not encrypted, they are shared. So this way, you can communicate between the two worlds. And the way this is integrated into the Linux driver ecosystem is that the DMA API in Linux that drivers use can go through the software IOTLB. And software IOTLB doesn't come from confidential computing either. It's a pre-existing piece that was made to get around address limitations in hardware, but it can be used here. So basically, what software IOTLB does when it's enabled is it uses bounce buffers. And what it can do is it can place these bounce buffers into unencrypted memory. And then you give that address of that unencrypted memory bounce buffer to the device. And the device can do I/O, and it works. The encryption isn't getting in the way. And then before the driver consumes it, it gets copied back into encrypted memory. The driver makes progress. There was a paper this year that looked at the performance overhead of software IOTLB in confidential computing. That's kind of interesting to look into. I'm not going to go into the details now, but check that out. They also have some optimizations that are worth looking into. The spoiler is that basically they say, well, if you're already doing end-to-end encryption, like disk encryption, then what's the point of having the bounce buffer? You should just encrypt straight into shared memory. And then the device can consume that. So it gets rid of the bounce buffer, which is nice for performance. Okay, so now I'm going to start to move on to the open issues, because everything I've mentioned right now, I've said everything is great, everything is working, and it's not. So the first thing is interrupt hardening. So one of the things that's an open issue in Virtualization for sure, and probably also in other Linux device drivers, is that when the driver initializes, it will configure the interrupts that the device has. And right now, in Virtualization, those interrupts are immediately enabled. So the interrupt handlers that are installed are enabled. And if you think about it, on a well-behaved device, a non-malicious device, those interrupts will only fire in response to some driver activity, like the driver submitted some I/O, and then I get an interrupt when the I/O is done. But a malicious device could raise that interrupt at any time. And so there's a window here where perhaps drivers were never tested and never considered that interrupts might come in and trigger the interrupt handler function. And that's a bad thing, because maybe that handler function accesses some device driver state, and interrupts are set up at some point during driver initialization, and then a bunch of other stuff gets initialized. So maybe your state is not fully initialized yet. And so there's a risk that there are basically there's some undefined behavior in interrupt handler functions that can be triggered if a malicious device sends interrupts that we don't expect yet. And so there's a solution to this. Linux actually does provide a way for request IRQ to register the interrupt handler, but not turn on the interrupt yet. And I think that was attempted. There were some patches upstream, but they couldn't be merged because they didn't work with Linux's affinity managed interrupt. So basically, we don't have a solution to this yet. So this is something where more work is needed. But I also don't think I don't know if anyone has a concrete example of where there's an exploit or something, but it's definitely a questionable area where there probably could be some dangerous things. So this is something that still needs to be done to protect against malicious devices. The next thing is speculation barriers. Because in the traditional model, if you trusted the hypervisor, and you couldn't hide anything from it, then you didn't really care about speculative execution attacks. The hypervisor didn't need to use them because it could just read stuff from guest RAM. But now in this world, it is important. And if there's a software device and you're switching from the guest driver into the software device, then speculative execution attacks become a problem, like Spectre style attacks. So the only thing that kind of helps us a little bit here in confidential computing is that the memory is encrypted, right? So, but maybe not. So it's definitely, I think, something that still needs to be audited and thought through. There are currently no uses of the no-spec macros in the Virteo driver code. So I don't think anyone has really done anything to protect against this. So this is another area for future work where probably some hardening still needs to be done, because until now, the drivers have never had to worry about this. Okay, so what I've talked about so far are the untrusted devices, where you can actually just use the hypervisor's VirteoNet, Virteo block, and it will work with confidential computing. But there are some device types that you probably really need to trust in order to use at all. And if you think about it, if you have something like the serial console, the Virteo serial console, well, you can never really use that. Because say the user logs in, well, the device can sniff their password when they log in. Or the device could inject some fake input events in order to, run a shell command inside your VM. So you're never really going to be able to trust them unless you have some kind of end-to-end trust relationship where you really do trust the source of where these input events are coming from. And it's the same with output, right? If you don't want the hypervisor to be able to see what output your Virteo GPU is producing, what do you do? So we're kind of have a problem here with these types of devices. Like, how do you trust them? One way is to just say we don't need trusted devices at all, these types of devices. Instead, we'll just use SSH, like just use networking and end-to-end encryption for absolutely everything. But there is a way to do trusted devices. So that's the next phase. And PCI has TDISP, which is a way for you to basically extend the TCB. We said we're going to try to reduce the TCB, but if you really need to trust a specific device, TDISP will allow you to authenticate, to check it's really the device you're talking to using attestation, and then protect the communication that's going on between the driver and the device. And the nice thing is that if you attest the device and you're using TDISP, then you don't need to use software LTB. Then the memory encryption stuff is handled, and you can get the performance boost back. So in this mode, if we had trusted devices, then basically what we need to make sure is that we only load drivers and talk to devices that really are trusted. And what I mean by that is, in Linux, when you have a driver, say VirteoNet, which device implementation are you actually talking to when you load that driver? The driver will work with, I said there's a Virteo standard, and it will work with any hypervisor's implementation. But you probably only trust one implementation, and maybe even a specific hardware revision or a firmware revision of that device, right? So if you have a VirteoNet driver in your kernel, you need some way to specify and say, oh, actually, I don't trust all VirteoNet devices in the world. I only trust certain devices where I actually trust the vendor. And I know that model is the one I want. And so we don't have this today. There's no way of doing this in the kernel today. Like, either you have VirteoNet and it will just happily talk to any VirteoNet device that you want, or you don't. So we need some way to specify that. And if you don't have a trusted device, then you need to decide whether you don't want to load the driver at all and talk to that device because it's untrusted, or whether you're willing to do it, but you want to use software LTB. So with VirteoNet, it would make sense to use software LTB. With something like Virteo serial, you would not want to because you cannot trust the device. Okay, so what I'm getting at here is that we need some policy, right? We need some user policy where users can say, okay, on my systems, I have these device implementations. This might be a specific Virtual block and a specific Virtual net or whatever. And I want the driver to load with them. And I don't want the driver to load with any other devices. And that way, your confidential VM can select which devices are trusted. But it goes deeper than this. There are a bunch of different options that users of confidential VMs have. Like, for example, when you use Virtual PCI, you drag in PCI, and you drag in, maybe you'll also drag in ACPI. So you have these dependencies, and some users may say, no, I need something very minimal. I want Virtual MMIO. So you can see that there's different choices here between like how minimal do you want to make your VM. And on top of that, there's also some functionality that you might want to disable. Like, do I want to allow hot plug or not? And in Virtual, if you've looked at Virtual, there are a bunch of optional features. Some of them add complexity and could be a security issue. Do I want to enable specific features that Virtual has? So these are all things that I think there's no one answer. Different users will have different policies. Okay, so how do we set this policy? Well, no single kernel parameter will express it. It needs to be, more expressive than just that. And I don't really have a solution. I don't know if anyone here has solutions to it. I mean, one thing might be some policy tools that allow you, when you build your confidential VM, to say, okay, these things are okay, these things are okay, and everything else, don't do it. And the question is like how to actually do that, how to add that into the kernel. And I think the only thing that I still want to add to that is, this is not specific to Virtual. This talk is about Linux Virtual, but actually all drivers need it, especially with TDISP, where we're going to see arbitrary PCI devices that can do attestation and be trusted. So this is more general than Virtual. It's probably as general as all devices in Linux, so probably should be part of the base or core driver API. Yeah, so I think that's where things will be going, and Virtual will have to be part of that, and will have to fit in there. Okay. Yeah, so in conclusion, the Virtual drivers have been hardened, in particular for the VDUs and the hardware Virtual use case. And confidential computing is still work in progress. So we have these untrusted devices that work, but they're just the first step. And the second step are the trusted devices, so TDISP. But for that, we definitely need user policy and configuration to make that work. All right, thank you. Are there any questions?
Hi. So one thing I think get a little bit confused in here is if you only want to trust the device, you don't need TDISP. You need the early bit of the stack, SPDM, CMA, all that side of things. If you just want to know, I'm talking to the device I think I'm talking to. TDISP only tends to come in if you want to be writing sufficiently trusted that you write directly into the encrypted memory, where you've got to set the magic T bit.
Okay.
So there are various layers here, all more policy. You may want any of them, who knows?
Okay, so I think that's an interesting point. Thank you for clarifying that. Yeah, so TDISP, if you want to turn off software LTB.
That thing about the interrupts, where you were getting them before it was, we've actually had that in the real world on physical hardware before, where the BIOS would have done something, and then you turn it on, and then it would interrupt your stack, and things would explode. So there has been a few cases of that in actual physical hardware. The other one that used to get us, I think, IOMU stop is when you turned on PCI bus mastering, if the BIOS had done some DMA transaction was left in the device, and you turn on bus mastering, and it blows up your whole stack as well. So yeah, I don't think that's a problem when you have an IOMU. But one thing I wanted to just, you talked about the GPU access. We've just added a new feature to the Virtual GPU to allow passing through like the host native contexts. I'm not sure if that's something how that would work. I think it probably have to go towards SRIOV or something to actually do access to the GPU acceleration as opposed to just GPU outputs. I think that's all up in the air on how it's going to work. But
yeah,
be interested if there's anyone that's talking about it.
I think the only thing that like I would like to respond to that is that I think that native context stuff, which is like a pass-through kind of solution, is an example of one of these features where maybe people need to have like the user policy. Maybe when you're doing something where you don't trust the device, you turn that off, but maybe you still want a basic frame buffer and basic Virtio GPU there, just not the stuff that's dangerous and too complex. So that's why we need the policy.
Yeah.
So you're talking with like, you made this statement with like, Virtio has been hardened. So that, and we said that it's for core and Virtio drivers. So does it apply for all the modes that Virtio operates, like, split versus packed and so on? So, because that's, I think, there are a lot of details where like.
So you tell me, because so I think this is.
That's what.
This is your document.
We looked into it. Okay, you're
Yeah.
referring to our docs. Yeah. So this is
Yeah, so I thought this was very interesting that the document that was released for TDX says we have looked at Virtio, but Virtio PCI, use it with a split vert queue and disable indirect descriptors, because this is not how you would run Virtio on a non-confidential VM. You would enable packed vring, you would enable indirect descriptors. So it's clear that there are some features here in Virtio that for some reason, like someone who audited the code maybe wasn't comfortable with or didn't want, so you decided to disable.
So the logic, like, we had to look at everything. So we were trying to just minimize to say, okay, so what is the minimal set we can run with? And of course, like, things like console is just for development and stuff. But like this split word queue was selected because it was Jason Wang's patches, which like, moved to addresses and things. It wasn't done for the packed one. So that's why it was like, big, not like, it is a packed. Packed doesn't look secure. So, but I mean,
So fundamentally in its design, the packed vert queue layout is not.
So it doesn't seem like, this address, things such as split queue, the address of descriptors and things, they were moved to a private memory. So now that's protected. So we know that, like, the device can't really, mess up with that. But with packed, it doesn't seem like that's the case.
Okay.
Or I don't know, maybe we misunderstood something, but like, but that's just.
Okay.
And same, like, if you use split word queue, but you enable indirect descriptors. Now I don't remember on top of my head what was like, but it also looked like what something is you're giving like more, playground for the device to play with this. So that's why I wanted to ask, like, how much, because you're making this statement, like, that Virtio is hardened overall. So how did you look at this combination?
No, I did not. I basically relied on this and the hardening patches that had been done by the community.
Yeah, we looked in very small subset, and we haven't even ventured fully to say, okay, and this is also the subset. So nothing else has been even for our fuzzing. So.
Okay, that thank you. Yeah, I'll look at the packed vert queue layout to see if there's like a fundamental problem why it's not something that's safe, because usually these layouts use indices rather than some kind of pointer that can be abused or something. That I don't think there should be a reason, but maybe. Yeah.
No, just to say that, like, I think we are like, we are not Virtual maintainers. So this is not, you have much more expertise in this code. So if you can indeed, like, make the statements that you have audited it, maybe we can have the fuzzing and so on. And then we can kind of, say that, okay, we believe that both of these modes are secure.
Okay.
There's, there's what I believe to be, sorry, go ahead.
Yeah, this is Michael. Yeah, I just wanted to say, yeah, we kind of looked at the code for packed as well, I think. I mean, just the Virtio maintainers, I think me and Jason tried to look at it, just, from code inspection, I don't think we see issues, but we didn't do fuzzing.
Okay, we have time for one last question before we need to move on, unfortunately.
Yeah, there's what I believe to be another open issue that I'd just like to point out for attention by this community. If you go to slide 22, I think it was. Yes, the second bullet point, storage device encrypt disk with DMencrypt plus DM integrity so device cannot inspect or tamper with stored data. I believe that claim needs a qualifier. DM integrity, when I audited it, didn't seem to provide the guarantees that I think a lot of people assume that it does. DM Verity has a Merkle tree across the whole block device, and so you can't modify any of the things. And DM integrity does not, at least if I recall correctly from when I looked at it, but rather has a per sector authentication tag. If those are not tied into some kind of Merkle tree for the block device as a whole, then that means that it seems to me that there is an opportunity for rollback attacks against selected sectors. If that's part of your threat model, then that seems to be unaddressed by the stuff that's available right now. There was something in the academic literature called DMX, which did a full block device Merkle tree thing like DM Verity, but for mutable block devices, but that's not upstream. And so there appears to be this opportunity for attacker malleability. If anyone's interested in solving that, I'd super like to talk to you.
It's too late anyway. We need to move on, unfortunately. Otherwise, we're cutting into the other speaker's time. Thank you so much for your talk.
Thank you.
There we go. Pretty obvious, right? Okay.
Hello, everybody. My name is Bharata Rao. Today, I've come here to talk about using hardware-provided memory access hints within the kernel for doing some efficient page placements. So that's the ideal goal. Let us see what we have here. And by the way, I work for AMD, and this is the agenda. Initially, I'll spend a bit of time going through the basics of the page access hints, which are the subsystems that are interested in obtaining memory access information in the kernel. Then we look at what kind of information recent platforms provide in addition to what the typical information that we have, and how can we make use of them. And I will spend some detailed amount of time looking at how this hardware provided memory access information can be used to drive NUMA balancing within Linux kernel. So I must say here that this is an experiment that I have done to figure out or analyze the feasibility of using hardware provided memory hints within the kernel by taking NUMA balancing as an example. And we look at some of the the results that have got. Then we can look at how feasible this approach or this entire approach is, and discuss about the potential opportunities and the possibilities that we have moving forward with the usage of hardware provided memory access hints. Yeah, so first some basics. So why do we need page access hints? So typically in the OS, right, it matters, especially if you are working on systems like NUMA systems, it matters where the application runs and where its memory resides. So operating system is in the constant business of moving pages across, migrating pages closer to the node from where it gets accessed. And in order to efficiently use the available system capacity, it keeps discarding pages wherever it possible. And also in case of tiered memory systems, it will try to see if any of the unused memory pages or cold memory pages can be demoted to a lower tier, right? And also, it would try to get the memory that is, or the pages that are getting accessed from the lower tier and get them promoted to the DRAM tier or the highest tier that you have. So all these activities kind of need to know the page access information, which are the pages that are getting accessed, which are the pages that have become cold. So these are the typical use cases or the applications within the operating system that you would need to use page access hints. And the subsystems that typically make use of this are systems like Numa balancing and hot page promotion, which anyway is kind of tied to Numa balancing. So Numa balancing uses completely software-driven mechanism or a full software mechanism to figure out the tasks access patterns. And then we have systems like Reclaim and LRU list management, which do use the PT access bit to find out when a particular page has been accessed and when was it accessed last, right? So those kind of information can be obtained from PT access bit. Then there are subsystems like idle page tracking and daemon monitoring, which do use a PT access bit in some form to understand the memory access patterns of a workload. And they, in addition, provide some interfaces to the user space to take action based on the monitoring that they have done. And of course, there are system calls like migrate pages, move pages, etc., which kernel provides for users to explicitly move pages if they find out that it will be useful to do so by themselves. Yeah, so now let's look at the hardware provided access hints. So I just mentioned that one of the most typical case or the usual way to get information about the page access is by looking at the PT access bit. For that, you need to walk the page tables, which is not always, which is kind of expensive. So if there are alternatives that exist, why not make use of them? That's the thinking here. And to aid that, newer platforms have started providing this memory access information in various ways that operating systems can use. The platforms that provide such information have different capabilities. They export different kind of information, but the idea is to see that what would be that information which would be most commonly useful, which will be kind of basic information that you would need for determining page access hints and to take further actions based on that. Typically, you would need to understand or you need to know the target address of the memory load and store pretty basic information and data source information. Where is your data coming, or where is that address located in the memory hierarchy, whether you are fetching the data from the cache or from the DRAM or from the external memory, etc. That is the data source information and the cache information. And for any of this information which the platform provides, for this information to be useful and effective, the expectation is that it should be presented in an actionable form where you will be able to kind of take action based on that, like whether to migrate, etc. Right? And it should be easy to consume with as low overhead as possible. And these are some of the flavors of platforms which do provide this kind of information in some way or the other. AMD CPUs have this instruction-based sampling, and Intel has this processor event-based sampling or PEBS. And then there is this thing called hot-cold affinity in IBM Power. All of them do provide some sort of memory access information. The information and the kind and the way they provide all these things vary, but the facility exists is what matters here. Yeah. So now I want to spend some time looking at the details of instruction-based sampling or the IBS, because this is the feature that I have used in the experiments that I've done here. Instruction-based sampling is a hardware facility that has existed in AMD processors for some time now. What it is useful for is to gather metrics related to instruction fetch and execution. When I say metrics related to instruction fetch, it means like when you're fetching the instruction, of course, what is your IP, where is your has the instruction completed, has the instruction retired, or has it been aborted, and information like whether it missed the iCache, whether the translation missed the ITLB, etc. So these kind of information can be obtained by the fetch sampling or the fetch execution part of IBS, and then there is this backend or the execution sampling or the ops sampling, which gathers or which provides a lot of information related to instruction execution. This is about the kind of information like what sort of information, what's the kind of instruction that got executed, when it executed, if it is, let us say, a load or a store instruction, where was my data, what is the address, whether it missed the cache, whether it was a remote access or a local access, what was the state of DTLB, whether it was a miss or a hit. This kind of information can be obtained from the op sampling or the execution sampling. So this fetch sampling as well as op sampling, these are kind of independent units, and then they can be used separately also. One of the other important point to note here is that this entire thing, this facility is independent of the PMU subsystem. What it means is that we are not constrained by the number of PMCs that exist in the system, because they are kind of independent of each other. And one instance of IBS exists per hardware thread. And typically there is no overhead in the data collection either during fetch or execution part, but overhead exists in the reporting part of it. How do you report the collected data to the operating system? The way the hardware collects information is by tagging a specific micro-op within the pipeline, and which micro-op gets tagged is based on the programming sampling interval that user can set. The sampling interval can either be specified by number of clock cycles or as number of micro operations. What happens is when the such a tagged operation kind of moves in the pipeline, when it is executing, a lot of information related to that is collected in the MSRs, and when the operation retires, micro-op retires, right? This information is kind of is reported to the operating system in the form of an interrupt. And OS can take subsequent action based on that. More information, of course, in the processor manuals to which links I have provided here. So traditionally, IBS in the AMD processors have been used for doing performance profiling. Linux Perf, in fact, supports using IBS-based precise event profiling. But the use case that I am talking here is about using the execution sampling flavor of IBS for doing memory access profiling. And let's quickly go through the workflow to understand how this IBS can be used to do memory access profiling. So the way to start here is the software loads the sample count, or the rate at which it wants to do this access sampling, right, into a register. We can call it as max count, and then you need to enable the counting or the access profiling. Once that is done, hardware starts incrementing a periodic counter for each dispatched ops. When the number of dispatched ops becomes equal to the sample that you have specified, either as number of ops or number of clock cycles, then a micro-op in the pipeline gets tagged as it moves, and when it gets executed, as I said, information is gathered in MSRs. When it is retired, the information is moved up to the OS via an interrupt, that is NMI. And software will start taking action, or expected to take action based on that. And in case of memory access profiling, right, what really is useful is that you really don't want to profile all sorts of instructions. So some sort of filtering would be required. It can be done at different levels. In the software, the kind of filtering that you would be expected to do here is that what is called load store op filtering, because the information that the hardware provides would have a bit somewhere in one of the MSR saying that, does this sample report a load or a store? So based on that, you can do filtering, and that would be very specifically specific, and you can take specific actions related to load or store operations. And another filtering that is done by hardware itself, which is more useful, is this L3 misfiltering, which is programmable a bit in the control register. If this is set, hardware would report only those samples which are load or store and which missed the L3 cache. So that would be more useful for memory access profiling, which typically means that it would have hit the other subsystems in the memory hierarchy, like DRAM or external memory or external cache, etc. So this essentially helps us to improve or increase the possibility of having useful samples. And let's quickly look at the kind of data that comes with each of these samples. In case of load store sampling, you have the precise instruction pointer, then you have the linear address as well as the physical address of the data operand, which becomes important because it's not just the linear address, you have the physical address, which means if you are feeding this to the subsystem, which can directly take action based on the physical address, there is no necessity of you further walking the page tables to figure out the physical address. So it's already available there. And exhaustive information about data source, like where it came from, the cache, DRAM, or the external memory, etc. Then there will be indications about whether the access was local or it was it remote. The cache miss information, etc. would be present. Yeah. So with that understood, I would like to spend some time on basics of Numa balancing, because this is the subsystem where I'm using IBS to consume the data provided by the by IBS for memory access profiling. So some basic, let me give some very quick introduction about Numa balancing. So it's a subsystem that exists in the Linux kernel, which tries to collocate the task and the memory that the task is accessing. Typically in multi-node Numa system, what it tries to do is it tries to migrate pages or the tasks across the nodes to ensure that most of the times you end up having local accesses, so you don't take the cost of cross-node references. The way it is done is that it needs to understand, for doing this, it needs to understand the page access patterns or memory access patterns of the task. For that, what it does is it employs a software-based mechanism of scanning process address space periodically, going through the PTEs, marking them as prot none, and when you do that, the next time such a page gets accessed, it will result in what is called a Numa hint fault. And this is the time, or during the fault time, we collect all the information related to the access. Importantly, where is the page that is getting accessed, and from where it got accessed, who accessed it, and where the page resides. Based on this information, subsequent action is taken by Numa Balancer. Essentially, what it does is it kind of categorizes this fault information as whether it was a local fault, or was it a remote fault, was it shared or private. Based on all these categories that it determines, it builds up some information, accumulates, generates aggregated stats, and builds some heuristics based on this, and finally arrives at migration decisions based on these faults. So the last thing that it does is that you don't want to periodically keep scanning the process address space at a constant rate, because workload, the expectation is that as you move pages across, as you move tasks around, the convergence happens, and it will identify that and kind of slow down the scanning rate. So that's one thing. And the last thing I want to note here is Numa balancing is a subsystem which is also used for hot page promotion. The part of that is hot page promotion uses the scanning part of NUMA balancing to figure out the access patterns. The other part of migrations and the decisions of how to migrate, etc., is kind of little different, because traditional NUMA balancing takes into account the fault stats, and the hot page promotion works on a different strategy. Yeah, this is some pictorial representation of what I described just now. The top one is about the traditional NUMA balancing. The bottom one is the flow where IBS-driven NUMA balancing is shown, and it shows where the data coming from IBS can fit in. As you can see in the left-hand side, there is no need to scan the PTEs or look at the address space, because hardware itself is giving the memory access information as and when it happens. Based on that, you get the interrupt, as I said, and this access information or the access data that is coming from the hardware is fed to this NUMA balancing logic. So I have not changed the balancing logic. Essentially, the idea is to replace the scanning and the software-based mechanism of access by the hardware-provided hints. So the next two steps are the same steps that exist in the traditional NUMA balancing. Instead of acting on the NUMA hint fault, now it acts on the access data provided by the hardware, which is via the IBS, accumulates the fault stats, does the same thing that it would do with the accumulated hint faults, and takes subsequent actions of migrations or whatever. And finally, similar to the way it adjusts the scan rate of in the default or the traditional case, it can adjust the scanning rate as well. So this is the flow, and this is how it fits in. Yes, please.
I think IBS is not able to do this, profiling the memory accesses within the VM, right?
Yeah, so this is not about profiling within the VM, but if you have a VM running, IBS is capable of getting memory accesses that get generated from the guest and figure out its host physical address. Based on that, pages can be migrated transparently across nodes in the host.
Yeah, I was a little skeptical on that because IBS might not work correctly, if I understand correctly, within the VM.
Sorry, come again?
I think IBS or PEPs may not work correctly inside the VM because of the identity maps, like the counters we have. The guests think we're using sort of some counters, but the host is using a different counter. I mean, those are
right.
That is that's no problem.
That's not the use case I'm covering here.
Right. Sorry, I was pointing out is like, since you are doing bare metal, right? If there are systems who's running VMs along with other host level jobs, right? If IBS is not able to provide information for those VMs, isn't it the result incorrect?
IBS will be able to provide information about the VM, the accesses that come from VM.
So you're saying that IBS will have to be run inside the VM?
No.
Okay, sorry.
So IBS won't run inside the VMs. IBS will run in the host, and it is capable of capturing the accesses that result from the guests.
I see. So you're saying if the if the vCPU is running on the sum of the CPUs, you run IBS, it is still able to get information. The memory access is coming from the guest.
Correct, and it is able to correctly identify the host physical address for that.
I see. Okay.
Yeah.
Thank you.
Thanks.
Is there anything similar for ARM64, the hardware memory hints? And if not, is there any hardware?
Similar? Can you repeat? Similar where?
Is there any similar hardware memory hints for ARM64 platforms?
ARM64, I'm not sure about. Intel does have.
Platform there have the hardware IP named SP static profiling extension. So it's CPU ARMv8 extension. So it's quite similar with like this kind of thing. Yeah, but it's different thing that is like the hardware trace. Here, like the hardware event, so it's here may be different because that is hardware trace. You need to decode it. So this one maybe I don't know how to. You know that this there has something that you need to do in the news color. But for the hardware tracing data, you how can do the decoding in the news color? This might be introduced that effort by the decoding itself.
So I just explained the high-level details of where IBS fits in the NUMA balancing workflow. This is some implementation bits that I want to touch upon. Similar to the NUMA balancing, here the access profiling is done on a per task basis. It's kind of tied to the regular to NUMA balancing modes, which is the regular mode as well as tiered memory mode for hot page promotion and the other default case. And similar to the per task NUMA scan period, we would have per task sampling interval that keeps varying and that keeps changing. And one of the things that is kind of has to be done in addition to what you typically do with NUMA balancing is that when the task enters into the kernel, you don't really want the IBS profiling enabled, and that's where you need to disable or program the MSRs to disable profile collection. So there are hooks in the kernel entry and exit points where you reprogram, disable and re-enable when you come out of the kernel. This is some additional step that is required. And once you have IBS interrupt coming in the form of NMI, a minimum amount of filtering that is required is done. All the information is read from the MSRs. And what currently I do is kind of raise a task work. And in the task work, you kind of interface with the existing NUMA balancing logic and let the NUMA balancing logic run from the access faults that is coming from the task work context. And hence all the migration, etc., will happen in the task work context as opposed to the fault handler context that typically happens in the traditional NUMA balancing. And of course, the hot page promotion also works in a very similar way. The only thing that is different is about a metric that hot page promotion maintains. It has a metric called a NUMA hint fault latency, which is the time difference between the scan time of the PT and the eventual the hint fault, which kind of is an indication of how hot the page is. Since there is no scanning involved here, the kind of idea I had is to have this latency recorded as a time difference between successive accesses, which kind of tells us how hot the page is still. And I have an RFC patch that I posted early this year, which had this implementation going. And let me come to the test setup and the results that I have seen with this experiment. Any questions before I go into the test the results?
Sorry. So the CXL node you're talking about is just the memory node. So this can work with CPU-less NUMA nodes also.
Correct.
Okay, thanks.
Yeah. So this is the test system I have. It's a 2P 3-node AMD Zen 4 system. It has 2 regular NUMA nodes with CPUs and 1 CXL node, 256 CPUs on either on both on individual nodes, and 128 GB memory attached to each of the nodes. And the distances look like that, 10, 30, and 60. The last one, the node number 2 is the CXL node. And I've written a micro benchmark to essentially test all these things. It is a threaded application that initially provisions a fixed amount of memory, 8G is what I have taken here, on a remote node. It can either be when you're testing traditional NUMA balancing, it is the remote node is the node 1. If it is CXL, it is node 2. And what it does is it has 64 number of threads, and concurrently they write to random bytes in the allocated range. First, it gets allocated in the remote memory, and from the local node, all these 64 threads continuously keep writing to random memory bytes, and there are some 1 billion accesses per thread that happens, and provided a delay of around 100 microseconds between 1,000 accesses, just to ensure that we just don't bombard the migration subsystem with so many migration requests. Of course, only 4K pages is what I've used. And the benchmark score is a measure of how quickly the fixed number of accesses are able to complete. The idea here is that NUMA balancing is expected to kick in and migrate all the 8 GB of memory, or however much that is possible, from the remote node to the local node. That's the measure of the success, or that's the measure that we are interested in. And what are we evaluating here? What we are evaluating is that it's not about things won't be very dramatically different if you are using IPS provided access hints. The things we are interested in is that we want to see whether the hardware provided access hints can match the existing software based mechanism. Can it be ever a replacement of the scanning mechanism that we have in NUMA balancing? And if so, and what are the other possibilities and other subsystems that can make use of it? And also the overhead part of it, whether it is tolerable. So this is the first experiment where I have the remote memory on a regular node, node 1. So I have the default NUMA balancing set to 1, which is balance across regular nodes. And if you see the benchmark score, both of them are kind of behaving in a similar manner, 203 versus 205 seconds. And if you look at the PTE updates for the default case, there are so many PTE updates that happen due to the scanning process, that scanning step that is present. And if hardware is providing hints via IBS, obviously you don't have any PTE updates to make. And then there are hint faults. I have called the access faults that come from IBS as hint faults here to compare. And the other metric, which is always of interest, is number of pages that get migrated. Around all the amount that is shown here is 209, 7278, roughly amounts to 8 GB of memory. So in both the cases, more or less same amount of memory gets migrated. And the last two metrics are related to IBS, how many events that get reported by the IBS subsystems, which means how many times the IBS interrupted with the access samples, and how many of those samples were useful to us. So that's the metric I have. And yeah, this is the case where both the traditional NUMA balancing as well as IBS kind of match with each other. And though the eventual benchmark score matches, right, there is slightly difference in behavior. If you look at the blue graph, this chart shows the number of pages migrated versus time. So how much time does it take to migrate all those pages, and in what way it migrates, fast or slow compared to each other. The blue one represents the default case. In the default case, which involves scanning, right, most of the times it is heavy migration at the beginning. But in case of IBS, the samples get reported gradually, and hence the migration process is also pretty gradual. Eventually, they both achieve almost similar number of migrations, but the route they take kind of varies. At least in this use case, the effect is not seen on the benchmark score. So this chart kind of plots the number of accesses completed for one thread that I have chosen out of 64 threads. All of them do equal number of accesses. If you look at, compare that, right, versus time, more or less they match. So this has been the observation with regular NUMA nodes. Now the next experiment is with the same experiment with CXL being the remote node. Here things vary. what is happening here is the benchmark score also kind of default case is little better than the IBS case. The number of migrations, if you see, right, the hint faults and number of migrations, these are kind of comparatively less when you look at the default case. That is the reason because of which you are not migrating enough number of pages, and hence your cross CXL access latency matters here, and you end up accessing more number of pages on remote node rather than local node. The access pattern for the default case remains very similar. Most of the migration pattern, most of the migration gets completed upfront, whereas for the CXL case, it is really, really gradual, because that is the way the IBS is reporting the samples to us. And the effect of that is seen in the way the number of accesses that get completed over time. In case of the default case, it is able to move faster with respect to number of accesses, whereas in case of IBS, since we are not completing that migration faster, right? So we are having that lag.
Could you increase the initial IBS sampling rate to sort of pick up the pages quicker at the beginning and let it auto-adjust?
Yeah, those kind of things are possible. What I have done right now is that it's not a fixed sample that I'm working with. So I have a minimum, I have a maximum. Similar to the Numa balancing scan rate minimum and scan rate maximum. I have a sample rate minimum and a sample rate maximum. And based on the convergence of the workload, you keep varying it actually. So that's what I have done. There is always that you cannot really go below certain, because you would end up getting so many samples and kind of take a lot of overhead because of that. Can you pass on the?
So how different will the results be when you enable THP actually instead of just 4K pages?
THP, I have not done a lot of runs with THP, but it is kind of matching the pattern is what I would say now.
So I'm assuming with bigger, huge pages, like you'll have less faults and you'll have somewhat comparable. I mean, the only advantage here is scanning is done in hardware instead of software.
Scanning is not done basically in case of.
No, in case of IBS, the scanning is done by hardware. So that's the only advantage. But when you enable THP and the block sizes are larger, then I guess the other scores will be similar.
I've seen similar pattern actually. So.
Okay.
Those were the two main experiments that I wanted to show, and also look at the overhead data that we have. The comparison is different metrics. One is the scan time. In the default, we have that scan time, which doesn't exist with the hardware hinting. And the second one is the fault or task work time. So in case of default, all of the heavy lifting is done in the fault time, the migration, etc. In case of the hardware hinting or the IBS, the heavy lifting is done not at the interrupt or the NMI handling time, but most of it happens in the task work context. So when you put together those two, that's how the numbers look like, more or less matching, I would say. And the additional overhead exists, as I said earlier, is with respect to the user kernel entry exit points, where you would have to enable, disable the IBS, which involves programming of an MSR register. That's the overhead. And the total numbers look like that. And yeah. And I've kind of given numbers about kind of normalize it for per fault as well as the per migration. So not much difference, but yeah, this is how it typically looks like. Doesn't look all that alarming, but yeah, there exists a little bit of overhead right now. And I believe that playing with the sampling rate would probably mitigate some of these aspects. Yeah, so I had a quick experiment that I did on virtualization as well. The the experiment here is that I have a guest running KVM guest with all of its vCPU pinned onto node 0, and the entire guest RAM is kind of provisioned on a remote node, which is node 1 on the host. And what we do is that for that we manually move the guest's RAM from node 0 to node 1. So all vCPUs are running on node 0 and the guest RAM is completely on a remote node. Then you run this micro benchmark inside the guest. Essentially, it's a local access. You keep running and see how the host is able to migrate the pages belonging to the guest RAM based on the access hints that get generated by IBS. And this is the sort of results I've got. These are some initial results, not really done multiple iterations and other things like I've done for the other experiments. It does seem kind of better. Though the number of pages migrated is considerably lower, and the number of hint faults that get reported is also lower, but somehow for the virtualization use case, it does seem to help. Needs some further analysis here, but I just included this slide to show that the virtualization possibility is this basically.
IBS. So you have a conflicting case. Well, the host is using IBS. The guest,
Yeah.
Okay, I'm a customer. I want to use IBS as well. Great. I want to do it for my own workload.
Yeah, you can't use both of them anyway. I mean, either you have to be in the host or in the guest. So you will have
Right.
to.
In that case, it might be a little bit conflict, right? You have to turn off or you choose one of them.
Yeah. So that's in the future. Basically, this is a experimental
Right,
study.
right,
I'm trying to see
correct,
the
right.
feasibility of things. So
Right.
Today we don't have IBS inside guest. So it's only,
Right,
yeah,
that's okay,
yeah.
how much time do we have? Okay, I'm
Can
almost closing it. Yeah.
Can IBS also handle cache access? If you can handle cache access, I think you can also balance between triplets.
So you are saying, does IBS also handle cache accesses?
Yes, can you track cache access using IBS?
Oh, yeah, it
if
does.
So, if so, you can also migrate, you can balance between triplets within a single
Correct.
node,
You can take all those decisions basically based on which cache. Where is it really remote cache or it depends on two things, right? Where is your actual data residing? Is it really remote, and do you have a cached copy of it somewhere? So you need to take a decision whether do you really want to migrate or is it good enough? The cache access is good enough.
Yeah, you can just track whether it's a local cache access or remote cache access.
Oh, yeah, it gives
migrate threads between the triplets, even within a single
Yes,
Numa node.
can be done. Yes.
That could also give you some performance benefits.
Yes, definitely. Yeah.
So you said we could optimize this by changing the sampling rate. So for this experimentation, what is the sampling rate we are using?
I'm using minimum sampling rate as 5,000 micro-ops, and the maximum I've kept as 20,000. And the default as every task starts at default of 10,000. Based on the convergence, it can either go till 5,000 or 10,000, 20,000.
And the MSRs are programmed every time any task gets into the kernel.
Correct.
And then every time in the task switching path, context switch path, you program it.
Yes.
Can we do it like for particular, let's say I'm running like customer workload on bare metal, but I want only for that process, not for everything else. Like just that process, I'm worried about the performance of that, any pages related to that being migrated to the Numa node. So can we do that?
You can do that, but Numa balancing kind of, see, all those special cases can be done. But in this experiment, I was trying to replace the scanning part of the Numa balancing with this. Since Numa balancing right now cannot work for individual tasks, it works for everybody, basically. So there were patches, I think, to enable it for just individual patches. I don't think it went in. So if that is there, this will automatically work.
Okay, so it's all backend, like Numa balancing backend, it's all fit. So the metric is changed. So if the Numa balancing supports per process, then you can support.
Yeah, it doesn't have to be that way. It is just that in this experiment, I have chosen Numa balancing as a subsystem where this can be employed, basically.
Okay, thanks.
Yeah. And then there are some other do we have benchmark numbers. Okay, I think I'll quickly skip because the slides are going to be around. So yeah, this is where wanted some inputs and feedback. So we did see that it's an experimental study. There are cases where it benefits. There are cases where it kind of suffers. And there are situations where you would want more number of samples, but not available, etc. There are limitations. I want to know, like, how does this approach look like? What are the possible opportunities? Can we use it in other subsystems? Can we use it to replace the PT access bit, reading of PT access bit from within LRU subsystem? So what's the opinion?
So we saw something like this as LSFMM this year.
Correct.
Right, by IBM, I think.
Anish was talking about it, I guess, yeah.
Right, so you're aware of that. That's good.
Yeah.
I really like the idea of the cache monitoring actually more than the page tables, because it didn't seem like we have a win here on the page tables, but the migrating of the tasks and putting them on the right cores is an upcoming difficulty we're trying to figure out.
Mhm.
In fact, I think there's something later after this conference about that. And if we can get more view into what's going on even in there, it would be great, right? And if these counters let us do that, that is definitely something worth exploring. It would be nice to know the overhead of what time we've spent page table scanning on our side versus how much the CPU uses in your tagging, so we can finally grain tune what you're doing with different overheads, right? And that would be really cool to see.
Sure, thanks. Yeah. So there were other ideas that were proposed in that LSFMM session in May, right? So there were, yeah, we can discuss it offline, I think. Okay, thanks. Thanks for listening.
Isn't the argument that Numa already sucks? So trying to match Numa, we gotta beat. Yeah. I don't, so I can't really say what NR and GLRU will.
You ready?
Terrible time with
it. Have they got the slides? I don't remember what else. I think. No, I'm going to talk about the biggest.
No, but I was.
I went to the well, I haven't seen Jack, so I'll take that. I'm gonna go grab. Nice to meet you. I was observing how the actual yeah, so we find they have their own minds.
How do we get our slides on the? How to get the slides on the?
Slides, yeah, it should just be coming up. Give me a second.
Maybe it's his laptop that does it. I don't know what I was asking. We've all got the same question. So do we just do a stop sharing? Because like we.
I think they say they will need to upload this to some other system.
So I put our slides there. But who's in charge of the room?
I don't know.
As far as
I received a message from Ted to upload my slides, so maybe he is like a.
But he was down on the kernel. He was not even mucking around. Half an hour ago.
Okay. Maybe.
So I don't do full screen. Most of the time, people don't do full screen. Is there any reason?
I can control. Yeah.
I'm having a tech come over and helping me with it now because it should have just popped up. Everybody else is, I've never it's just kind of come up for me. So it'll be over shortly, like 2 minutes.
That's something you fucking charge at the movie or something, because they did it for some quick.
Yeah. This might be a short. Actually, they said, I think they said that's something that you're supposed to set up. That's what you're saying in the chat. Somebody else is having the same issue.
I can download the slides, but like, because they're just on the site, but when I download the slides, how do I then present them? Do I just like click on the share button on the is it
Yeah, it's supposed to be the share button. That's what I'm aware. Everybody's just been kind of on their slides.
Hey, there we go. Okay, so there's a, you can help me, but under the plus, under the actions, you can,
You
so
can
there, you can choose.
I uploaded all of the slides before. Yeah.
That's great.
I updated my slides, so can you use the new one?
Sorry?
I added like one extra slide.
Okay, sure. Here in here, did you
Yes,
upload it
this one,
already?
the second
Okay.
one. Yes, yes, already. The second one.
Just give me a second. Just want to refresh to make sure.
Not this one. The second one.
Ah, sorry. Damn it.
Isn't that
This one.
Yes, sir.
Yeah,
we contacted somebody on their team today.
Okay.
Thanks for the heads up there.
Yeah.
Good. Keep it up.
Sure.
Our talk's too short, so we want to start on time so that we give ourselves enough space. Oh, we win. Left and right work. Going? Okay. So thank you for coming to the talk. It's the last day, nearly the end. I'm Ian Rogers. Mike. Too close? It's on. Okay. I'm Ian Rogers from Google, and
I'm Wei from Intel.
okay. So yeah, we're giving a presentation together, and it's kind of awkward because we're on the stage together, and it's and so on. So because of the title of the conference, Linux Plumbers, we're kind of assuming that you're familiar with what Linux is, and we're kind of also hoping that you're familiar with what the perf tool is. And if you're not, I really recommend, Julia Evans's zine, but also Brendan Gregg's stuff as well. So kind of the big question is what are the metrics? And that's kind of what this talk is all about. So why do we have metrics? So we have events. Why aren't events good enough for everything? So when we have events, it's often unclear what are the units which are used by a counter. So we have bytes versus cache lines, cycles versus instructions. There are different clock sources. Does a counter count speculative events or not? When the perf tool runs, we do different kinds of aggregation of counters. And so the goal with metrics is to take multiple different counters from different PMUs and to combine these into something which is human readable and kind of like human understandable, and to hopefully do this in a way that's consistent across different architectures and from different vendors. So we have groups of metrics. We call these metric groups. Jerry, is that one of yours? Not sure. Okay, so we have metric groups, which are groups of metrics. So an example of a group of metrics could be like metrics related to data sharing. Then we have individual metrics within the metric group. And the metrics are comprised of events from different PMUs. So in this diagram, we're showing like we've got a memory controller, last level cache, the CPU, and interconnect. So the events, they either come to us from sysfs, or they get specified in JSON files. So the top thing here is just showing, you can see the CPU events from sysfs, and we have an example of one of the JSON encoded events. The JSON encoded events, they get compiled and built into the perf tool. So if you get newer perf tools, you get newer events, you get newer metrics. So if you want to see what the metrics themselves are, you can do it through perf list. So it's what we recommend. If you do -- details, it'll show you what the metrics expressions are. So how we actually compute the metrics. So in this example, we've got TMA core bound. The top value is the metric expression. And then the value below that is a threshold expression that we use for coloring the values from the metrics, either red or green. I'll speak a bit more about that later. So because it was the first metric in perf list, I chose as an example TMA core bound. And it's a somewhat complicated metric, but it kind of like shows you what's going on with metrics. So we start off, we've got this max operation, which is either going to be 0 in the case that the value on the right is negative, or otherwise it's going to be this value which is computed from two other metrics, TMA backend bound and TMA memory bound, and it's going to subtract one from the other. So I've drawn arrows in the diagram, hopefully somewhat clear. It doesn't really matter what the details are. But in this example, the lowercase values are all other metrics. So the metrics are built up from other metrics. The uppercase values are all events. And as well in there, we've got some constants. We've got a 5 in the backend bound expression, and so on. So where are all of these events and metrics coming from? Intel, we've been working, Google and Intel have been working together on a project called Valkyrie. The events used to be on a website called o1.org, but more recently they've migrated to GitHub. And so there's this Intel perfmon site. The pushing of events and metrics used to be kind of a manual affair. And so the events weren't getting updated that frequently, and so on. Now we have a single script which does everything. This is this create perf json.py, and this is hosted on the Intel perfmon site. It's taking in JSON files and it's creating JSON files. The files it creates get put into the Linux tree via LKML. The incoming JSON files, the event JSON, people are probably familiar with that. For the server architectures, so the Xeons, there are some additional metrics that get added, in particular for Uncore things. And then there's this TMA spreadsheet, which is historically how Intel has published its metrics. It's a CSV file here. Intel used to publish it as an Excel file. So some history there. After we have the JSON files in the Linux tree, we have JSON files from other vendors for other architectures. The jevents.py script runs and generates a PMU events.c file. The PMU abstraction in the perf tool uses what's in the PMU events.c file. And you don't really care what the details are.
Okay, so before I start a new topic here, is there any questions?
Events, clear how they get added to perf, but the formulas for metrics, who invents those formula? They come from Intel, from the engineer at Intel. Is that someone from the Linux community? So who makes the formulas?
So who's inventing formulas? So the TMA metric spreadsheet, the person we blame for this is kind of mentioned down the bottom there, is Ahmed Yazin. And so most of the Intel metrics are coming from this spreadsheet and so on. But there's also a team within Intel who create new metrics and so on. There was a patch I sent last week for adding UPI bandwidth metrics.
So Intel writes those metrics, and they come from Intel, right?
So Intel published them via the perfmon website, and then we pull them into the Linux tree via the create perf JSON thing. And it doesn't have to be me who sends in the updates to the Linux tree. It can be anybody.
The expectation is that the formulas are produced by the hardware vendors. Anybody coming up with the core or uncore has to produce the JSON events and the JSON formulas that go with them.
Yeah, there's some fudging. There's some metrics on things like TSX and things like that where I forward ported them and things like that. But it's all coming from the vendors.
So for our project Valkyrie, we also try to standardize the event and metrics and also provide the common ones that we feel valuable for you. And that's one thing that I think is a value of our project. So I will include a link to this open source repo. So please check that out if you are interested. Okay, so now let's get started to the next topic. This is the top-down microarchitecture analysis method. So this is a method that proposed by Ahmed Yazin in 2014. And this is a very useful and easy to use methodology for you to do performance analysis and try to find the true bottleneck of your program in in out of order processors. So for this method, you don't need to have very deep knowledge on the microarchitecture. You could still use it in using the tools that provide this method, like VTune or like our Linux perf tool, to do this methodology following the structures like showing in the graph here. So I will do a very simple example using the perf tool, how we can do this. So here, usually when we do the TMA, we start from the first level. And if you look at the graph here, on the first level, we have the 4 metrics, which are, when we do the performance analysis, like running using the top-down L1 metric group that's provided by the perf tool, we can get the value of these 4 metrics are all in the percentage value. And if we look at the graph here, we can clearly see that only one of the metric, the backend bound, is highlighted in the red color. That's because for this method here, it tried to figure out which, from the level 1, it tried to figure out which category is most likely that your bottleneck falls into. So for our example here, oh, sorry, I forgot to mention, I'm using a matrix multiplication workload from StressNG for this example. So here, my workload has the backend bound highlighted. So I know that for the next step to drill down, I will need to go into the next level of my metric, which are the children nodes of this backend bound node. Then I can do this by easily using the TMA backend bound group. The unschool group is the suffix for this type of drill down. So when I do that in the next step, I got the value of these 2 children nodes, the core bound and the memory bound. And then here we obviously see that my workload is a core bound workload. So 2 important features to notice here. First of all, if we look at the value of the 4 metrics in the level 1, the value of the 4 values should sum up to equal to 100%. So this is the property of TMA. And also on the level 2, the core bound node and the memory bound node, the value of them should sum up and equal to the value of backend bound. So now, if we continue with the same process to drill down to the children nodes of my core bound, then I can do the TMA core bound group and then continue to the TMA ports utilization group. Then I do the same process until I reach the leaf node of this structure. And I see that I have the TMA ports utilized 1 and the TMA ports utilized 2 are the likely to be my real bottlenecks here. So at this point, you can start to look into your program to do program optimization based on this. Or if you like, you can also do some sampling on the events that related to this metrics.
So on Ice Lake and newer models, what we do in kind of like the default perf stat output is we put the top-down L1 metrics there for you to see. Yes, we have top-down L1 on before Ice Lake Intel architectures, but we don't show them by default. I'll mention a bit about that shortly. You'll see here that the TMA retiring metric doesn't have a threshold calculated, so it's neither red or green, and I'll go into that now. So metric thresholds are themselves metrics. Quite commonly, a metric threshold will just be like the metric value and saying whether it's bigger than some value. Metric thresholds themselves can add extra events, and because of this, they can cause multiplexing because we have more events programmed. And so when we kind of like default opt you into metrics, we didn't want to have the multiplexing problem. And so that's why the retiring isn't colored in the default output. when you say that I want this metric, so you specify in the command line, I want, TMA core bound, then in that case, we say, okay, you want the thresholds now, and that means we're going to program these extra events, and you can opt out of that behavior by passing the metric no threshold flag. So as Waylon mentioned, one of the things that you want to do, kind of like when you've got to a leaf in the TMA tree, is to kind of like identify where in your program you're encountering this bottleneck. So in the drill down that the Waylon done, we got to this TMA ports utilized 1 metric, and with perf-list-v, we get the long description of what the metric is. And it's the fraction of cycles where the CPU executed a total of 1 UOP per cycle. Lots of other information there. But the bit I'm interested in is the bit I highlighted in red, which is the sample width. And so the event mentioned there, this exe activity.oneports util, we want to pass that through to perf record. And then what we're going to do is we're going to get samples in the benchmark, and we can analyze where these one-port utilized events are occurring with either perf report or with other visualizations like flame graphs and so on. Okay, EBS mode. So EBS is event-based sampling, but it's something which is in the TMA spreadsheet, and it causes controversy. In the TMA spreadsheet that was in the earlier slide, I can flip back to it. We're breaking things down into slots. We've got non-stalled and stalled slots, and we don't like the stalled slots. And in newer processors, the slots is an actual counter that you can program, and you can get counts for what the slots are. But in older processors, so pre-Ice Lake, slots wasn't a counter. And so it had to be computed. And the way it was computed, if you didn't have hyperthreading enabled, it was straightforward. It was your pipeline width times the number of cycles. If you have hyperthreading enabled, then roughly the number of slots you're going to be using is half the pipeline width times the number of cycles. But of course, you've enabled hyperthreading because you're going to get memory issues and so on the other hyperthread. And in that situation, the non-stalled hyperthread is going to get all of the slots. So there's an event for that called one-thread-active. And so what happens with EBS mode is the number of slots gets scaled up by the number of times you have one thread active. The problem with this is that this counter is buggy, and it leads to the number of slots not being calculated correctly. And so because of this, pre-Ice Lake, we don't enable top-down L1, because when you do the top-down L1 gathering, it uses EBS mode. And if you're not doing system-wide profiling, or you're not doing profiling on both hyperthreads. If hyperthreading is disabled, this is not an issue, but we still disable it anyway by default. The reason it's controversial is Intel are looking to make EBS mode disappear, and historically the perf tool has always had it and used it by default, because when people use the perf command, they tend to be going perf command and then the benchmark that they want to profile. So I'd raise it here. So something which is kind of new in like 6.5-ish, 6.6, why 6.5? We had this, I think even as early as 6.3, is that we support hybrid processors. So in this diagram here, we've got a per core type breakdown. So we've got top-down L1 on both the performance CPU core PMU and on the CPU Atom PMU, which is the efficiency core. And we've got the metrics for both of their top-down L1 groups. The Atom processor has somewhat more metrics than the performance core. The The thing that we don't like is we've got these percentages on the right, and that means we're multiplexing. So that means the counter isn't always active because we have to swap the counters around. And we're only doing this here for the Atom processor. And the reason for this is Perf has always historically given you a branch miss rate count. And the Atom processor doesn't have enough counters to calculate branch miss rate and to compute top-down L1. So maybe we want to get rid of the branch miss rate from the default output. But yeah, we can bug on Aldo and people like this to see what we should be doing there. So do you want to? Okay. So having lots of metrics is wonderful. You can compute all of these things, memory bandwidth, the TMA, do the drill downs and so on. But there's no use in having them unless they're actually, accurate and correct and giving you numbers which mean things. And so Waylon did all the work. She wrote a validation test. So what the validation test does, it does things like the parent-child relationship in the TMA. It makes sure that those things add up to things like, if it's top-down L1, they should all add up to 100%. So there's a bunch of things like that. So in earlier versions of the perf tool, it was quite common to see that we would double scale values so that we would compute things like memory bandwidth in petabytes per second. And so you would always see that you had 0 petabytes a second because it was too big a unit. These days, hopefully the metrics are somewhat correct. The test doesn't always pass for me, but we're working on it. So, okay.
So, yes, I think like Ian has already been mentioning that we don't like time multiplexing because that hurts our accuracy. And the reason why we are having that is that PMU events is helpful for performance analysis, but there are so many events, but we have only a limited number of hardware counters. So in the case that we need to collect more events than the real hardware counters available on the system, then we need to split the event into groups, and so that in each group we could clearly collect them all at one time successfully. And for this one here, I think currently our perf tool do the event grouping for metric groups, but it doesn't take the information of counters and the event restriction on the counters into account. So we want to propose a new event grouping method here to help trying to improve at least the grouping result. So before I dive into the detail of the algorithm or the method itself, I want to use this simple example to show some context, to set up some context here. So in this example here, we have a list of metrics we want to collect. There are 3 metrics here. We use this as an example because this is kind of a very common use case that when we do performance analysis, we might want to collect more than 1 metric at one time. And here in our example, we have different number of events for each metric. But we do want to ensure that we have this all the events for 1 metric, that trying to make them collect together to have better accuracy. So in this environment, I'm trying to make it simple. So we have only 3 counters available. Of course, we have more than that in the real system, but here we have only 3 of them. And based on the list of metrics and the events that we need to collect, in total, we will need to collect 5 events. And at the same time, also trying to make the example easier to show the context here. We have the counters restrictions for them very simple, that all the events could be collected by all the counters I have. So then when I start to do the actual grouping, if I don't have information about the total number of counters I have on the system, I might end up with a grouping result like showing in the circle here that I have 3 groups, and the first group actually have 4 events, which we can clearly see that this is not a valid grouping because I don't have so many counters for it. Then a very easy and simple solution to improve this is that we could place the event 4 into a new group. Then I have 4 groups in total, and every one group could be collected all at once. But if we look at the grouping result here, we can clearly see that we have so many groups, and some of the group only collect 1 or 2 events. We are not fully utilizing our counters. So we say that this is functional, but not very efficient. If we have some more information, then we might be able to create another grouping that we have only 2 groups, and we could be able to collect all the 5 events we need. And in addition to less number of total groups here, we also could see that we have the event 3 being collected repeatedly because it is being used in like multiple metrics here. And also for the second group, we can see that we collect event 3, 4, 5. That's all the events that needed for the metric 2. So for this several different reasons, we believe that this grouping is actually both functional and better than the one that we have before. With all this background described, I want to start to propose our new metric group event grouping method that we want to say that at least we could try to ensure that we can create a functional grouping if we have the information about how many counters we have and what's the restrictions for all the events we need to collect. Because to get functional grouping is actually very easy. We just need to ensure 2 things. One is that we only place events to the counter that support them. And then the second one is that we don't put too many events in the same group to exceed the total number of counters there are. So to achieve this, we need some extra information so that we could do this at the execution time of the perf tool. So the first thing is that we want to know what's the counter restrictions your events have. So this information we could very easily describe into JSON files. And a second information is that how many counters and PMUs there are on your system. This could also be very easily described in the JSON files. So for both of these 2, I think most of the information we need are already existing in our in the GitHub repository that we provide from the project Valkyrie. So we just need to include this information into perf source code and then do the load this information from the PMU events at the execution time of perf tool. But there's a third piece of information that we still need to resolve to help improve the result. That is the actual counter availability on your system. Because there are situations that not all the counters are accessible to the user when they run the perf tool. So this happens in the case that maybe there are multiple users using perf at the same time, or we're in maybe a virtual environment. So this is the part that we still working on. And if you have any suggestions or good ideas, please join our discussion. A little bit more detail about the grouping method. This grouping method is actually very easy. We could very simply describe this in 3 steps. So at the first step here, when we need to do the event grouping at the execution time of the perf tool, we need to, I described, we need to know the information about how many counters we have, and also what's the event list that we need to collect. That's the list of events that we get from the command line, from the perfstat -m command. And then we also want to know for this list of events, what type of restrictions we have. So I have a box here. This is not for reading for now because this is just for reference, that we have like a list of six types of restrictions, but just for reference, if you are interested, you can check this out later. So for all these informations, when I get them at the execution time, then I could start to do the real group generation. So for here, in our current implementation, we have a combined big list of events based on the metrics that we want to collect. So for this list of events, we go through each one of them and then check which PMU or PMUs this event needs to be collected on. And then for each PMU, we will create a list of groups for them, for this PMU. So based on the PMUs that this event requires, then we start to search in the list of group and trying to find if there is a space left for this event. Meaning in this group, we still have a counter, at least one counter available and support this event. If that's the case, then we can successfully fill this event into the group and set the bitmap for this and then continue to the next event. If we cannot find another space available, then we just create a new group for it and insert it into the PMU group list. So after we finish all the groups, then we go to the last step here that we just generate the grouping string. So for each one group in the group list, we have one grouping string for it. And the rest of step would remain the same, like how currently the perf tool works. For this whole method, we have an implementation and posted a RFC patch to the link that I included here. So please, if you are interested, check it out and give us some feedback. So one last thing about this event grouping method is that so far, I've been trying to say that we want to ensure at least functional grouping, but at least actually we want to improve it to make it not only functional, but also to do good groupings. So for good grouping, there are some challenges here. So for a good grouping, I think there are at least two conditions we can think of. The first one is that for each group, we want to have high counter utilization, so that the higher counter utilization, the more likely that I could use less total number of groups to finish all the events I need. Then I will have better time multiplexing and likely to have better accuracy of my metric and events. But at the same time, we've already been saying that metric requires a list of events. So we also want to try to ensure that for the list of events for one metric, we put them into the same group or at least a neighboring group so that we could have better accuracy on this metric. But if we think about these two conditions, they actually conflicting with each other. So this is an interesting thing that I think worth to discuss. So please check out the code patch and give us some suggestions and your good ideas about it. So I am going to go into another topic. And before that, is there any questions?
Yeah, a question about the grouping example you gave with the events 1 through 5. So you filled event 3 twice, but some of the other events did show up in multiple metrics. So I was wondering, like, how do you decide which event you want to overrepresent in this? And would it be better to add more groups so that you can more fairly get samples for like all the events. So like event 1 could appear in like another group just so it's more fair, so that like event 3 here isn't oversampled compared to other events?
Yeah, I think this is a very good question. And like I just described in the discussion part, this is a kind of challenging and conflicting situation. If we put another group here and repeat more events, then we will have more total number of groups and less time multiplexing percentage here. So which one is actually better, I think is hard to say. It depends on a lot of things.
So let's say in this case, I have 6 counters and you form that 2 groups, and then where event 3 is repeated, like then I can schedule like the both groups simultaneously. But if the one event is repeated in one of 2 groups, then how do you compute the values while calculating the end at the end?
So are you saying if we have 6 counters?
Assuming in this case I have 6 counters.
So
right?
in this case, if we have 6 counter, we don't need multiplexing anymore.
Okay,
because
so
we
you'll have like one group with all the 5.
Yes.
Thanks. And another question on the last slide before you went to the PEBs thing, where you talk about the locality of events, good locality of events, but same on neighboring groups. How do you know which are of them? Like, does the microarchitects or like the hardware vendor tells you that like these are events that are have good locality, or how do you decide that?
So this locality word is like I created.
Okay, so it's not related to like cache locality or those events
No, so
nearby
it's actually
the
like if we
microarchitect.
look at if we look at the example here, that means for example the metric 1, I have 4 events. I want them to be in same group or neighboring group.
Okay, thanks. Sorry, I misunderstood.
Sorry for this.
I have a question. So when you do this grouping of event, when you load it, do you load them like a per task event or there's a per CPU event?
I think that's a different.
It's the same for both of them. If you're doing task-based profiling, we will program the events with the groups, or if you're doing CPU, we'll program the same events, the same grouping. The tasks or CPU don't implicate it.
Okay, so the reason I ask is like I think in the kernel the per task per CPU event has a higher priority to get the counters, which means like if there are others using it, I think this is actually common for like our production. Like we have system wide and the service may have their own. So it's a kind of the ordering like will change the behavior. Like if you do the per CPU, the per task will have to wait. If you do the other way, like you probably get preempted by the per CPU event.
Yeah, I rewrote that code. So very familiar with it. But as Weilin was saying, we're doing a kind of a static determination of what the grouping should be based on like which metrics you want to have. And this determination is done in the perf tool, and it's assuming it has access to all of the counters. So, it's assuming that you don't have any CPU-wide profiling happening or any task profiling happening at the same time. And it's naive in that regard, but how we fix that is a more complicated problem, and we're not up to solving that at the moment.
Thank you.
But if that's a common use case, that could be one improvement we can add to the dynamic counter availability part. Is that?
Yeah, I think the dynamic or I was thinking maybe you want to just restructure some of the group in the kernel because it's going to change.
Yes. So if that's a common use case, then we can try to describe it in some way that when we do the grouping, we take this into the account as well.
We're doing the groupings in the tools, and the kernel's also doing its own things with groups and so on. And it's troublesome to work out where you should be doing what. The kernel algorithm is somewhat simple, and Yeah, we could make the kernel more complicated, but that would have like context switching costs and things like that.
Yeah, of course. Thank you.
Okay, so the next topic is about the timed PAPs. So timed PAPs, this is an enhancement we are going to provide as a new feature to our new generation of Intel processors. So this one, it records retire latency. The retire latency meaning the CPU cycles between the retirement of two instructions, your current instruction and the one that before it. So it uses a 6-bit field in the PAPs basic info group, like shown in the table here. So for any new Intel processors that support this, it will set the new bit, the PAPs timing info bit. To using this timed PAPs, we could increase the accuracy of some of our TMA metrics because before the TPAPs, sometimes for some of the latencies in the metric, we have to use a constant value. But this value is actually could vary based on the workload and your platform. So with TPAPs, we will be able to get even more accurate metric results in these cases. For the TPAPs, the status in the perf tool, the sampling mode, the perf record, we already have this enabled and upstreamed. So if you check out the latest perf code and also have a newer version of the Linux kernel source code, and you could be able to run the perf record -w on a platform that support this. And then in the counting mode, because we want to support this in the TMA, then we will also need to support this in the counting mode. And this part, this is still working in progress. And we want to describe a little bit more detail about how we are planning to support this in the perf tool. So because perhaps this is a sampling feature, to enable this in the counting mode, we have to, not have to, but we want to use both perf record and perf stat so that when from the command line, the user do a perf stat -m with a TMA metric that require retire latency, then perf stat would fork and launch perf record with the list of events that we need retire latency for it. So after that, perf stat and perf record will work at the same time in your system. And then at the time that perf stat need this retire latency value, it will send the signal to perf record. Then perf record will send the sampling data back for perf stat to process this sampling data and get the retire latency value out. Any question? And then perf stat will calculate the metric value and print it out to give it to the user. So for this work, we are implementing it and testing it in our new platform. And I don't know if anybody has any questions or comments on this.
So why do you need to fork and then hand the data back? Just record and then operate afterwards in a pipe on the recorded data. I think that's way simpler. Yes. I don't see the point of having the whole fork thing there.
There isn't. It's basically the way the code base at the moment is set up is that it kind of like everything gets globally set up either for sampling or for counting. And so just to simplify things to get something working, we're doing the fork and then piping things. We're piping the result of the perf record back to the perf stat.
Yeah.
There's no reason why you couldn't be doing everything as a single process. But
No, the question is why don't you just record the stuff and then do the statistics on it? That should just work. No?
I think the reason it's done like this is because you want to measure the timing during the measurement of the counts so that you get the closest possible.
Okay, we're out of time. Thank you so much.
Okay. Yep. Thank you.
Okay. Say something. Oh.
Hello, everyone. Thank you for staying so late for the last session. So my name is Vishal, and this is the work that I did with my colleagues at EPFL and my advisor, Sanidhya. So the work is basically about shipping the critical section instead of shared data. And what we want is basically the locality for shared data in the level 1 cache. So locks are the most widely used mechanism in the Linux kernel for synchronization. As we can see from this graph, there is a 4x increase in the number of lock API calls that you have in the Linux kernel in the last 20 years. This is because the kernel is moving from coarse-grained locking to fine-grained locking. So it is important for the locks to be scalable. However, we observe that the locks are not really scalable for certain workloads. So here we have a benchmark where it is trying to rename a file in a directory, and it is contending on a directory lock. On the x-axis, you have a different number of thread counts, and on the y-axis, you have millions of operations per second. And you can see that the performance decreases as you increase the number of thread counts. Also, the NumaWare locks like CNA, which was proposed 2 to 3 years back, also follows a similar trend. Our evaluation was done on an 8-socket Intel machine with 224 cores. So the basic reason for this is the movement of shared data. So here we have 3 different threads which are trying to acquire the lock. And in this, we have a critical section that is incrementing a counter. So when thread 1 transfers the ownership to thread 2, the shared data has to move from the level 1 cache of the thread 1 to the level 1 cache of thread 2, assuming that all the threads are running on different cores. And when thread 2 passes the ownership to thread 3, the shared data has to move from thread 2 to thread 3. So this movement of shared data adds additional latency in the critical section. Yes.
How big is How big is the data which gets moved over into the cache line? How many cache lines are you moving? I mean, in most of the cases, if you have, and that's what we strive for, if you have the lock, and the lock is usually cache line aligned, and it's at the beginning of the data structure, and then you fit all the hot important data which is protected by the lock right behind the lock, so it's in the same cache line. Then the data movement is exactly 0 because you move a full cache line anyway. The lock makes the cache line move, and it contains all the data. So the question is, how much data are you moving?
So the shared data here is like 1 or 2 cache lines, depending on what you are accessing within a critical section. But one of the other issues with if you have a queue spin lock kind of design is that when you want to, let's say, when multiple threads are accessing the queue spin lock, you have to do a compare and swap on the tail of the queue spin lock to enter the queue. So even if when you acquire the lock, you move the lock cache line into, let's say, thread 2's level 1 cache. If other threads accesses the same cache line, then the cache line will go away. So your shared data is anyway gone.
No,
So
it goes from exclusive and shared.
Hmm?
It goes from exclusive and shared, so it doesn't matter.
No, but like when you are modifying the shared data, you have to move
Yeah,
back
sure.
from exclusive to shared to exclusive.
Sure, but that requires extreme high contention and short log sections to actually matter. Because if it just moves over because a new contender comes in, then what happens? It bounces immediately back, and then the contenders just read, and read means shared state. They won't drag it back, because that's what we do with the queued spin logs.
Okay.
That's why we have queued spin logs,
Yeah.
because otherwise you would really trying to acquire it and bounce the exclusive state,
Yeah.
which is expensive, but shared state, bringing it back into shared is completely non-expensive and doesn't affect the log owner at all. Only if you have a very high number of contenders coming in and you have a very, very short log sequence, then it matters, because it's just lock, unlock, lock, unlock, lock, unlock. So there you see the actual effect. But if you have reasonably long sections of lock held code, plus not a gazillion of contenders, then it's almost not a problem. The thing is, of course, you can kill performance with all locks if you throw enough contenders on it. I mean, if you have a 256 CPU machine and do 256 threads or trying to do the same thing at the hammer at the same lock, performance will degrade. That's not a surprise. But the question is this a real use case problem, or is it just, oh, we found a way how to expose it? I know hundreds of ways to do that, but do they matter? No, because it's not a real world use case.
No, but we see performance improvement at 8 and 16, or like less core count also. So because the shared data, like it's not like the share, you can always fit the shared data that you are protecting in the same cache line as a log word.
Yeah,
So
that's true.
if that is not the case, then you have to move the shared data from one core to another core. So yeah, so the increase in shared data movement increases the critical section execution time. And with the spin logs, since you can execute only one critical section at a time, so this increase in critical section time results in lower application performance. So there is an alternative style of log design, which is called delegation style logs. And here it works like a server client model, where you have a server, which is the log holder, and you have the clients which are waiting to acquire that log. And the client ships its critical section request in the form of a function to the server thread. So in this example, you have a critical section which is incrementing a counter, and you wrap this critical section as a function and send the function pointer to the server thread for execution. So here, just a pictorial representation of the same thing. So the server thread, when it is processing the client request, it will execute the critical section. And since the shared data is present in the level 1 cache of the server thread, the execution time of the critical section is much smaller compared to a traditional log design. So here we did the same experiment, but we are measuring the critical section execution time. And as you can see, with a delegation style log design, the amount of time you're spending in the critical section is much lower compared to the traditional log design. However, the existing delegation style approaches that were proposed require you to modify the critical section and wrap it as a function, which is highly impractical for a code base like Linux, because it has like millions of lines of code and different constraints as well. So our goal with TCLock was to have transparent delegation, and we want transparency so that we can use the standard lock and unlock APIs. And we also want minimal shared data movement of the shared cache lines. So after motivating the problem, I will discuss about the design of TCLock and what it required to change TCLock for the Linux kernel, and some evaluation, and then some discussion on how to further improve it. So to achieve transparent delegation, we need answers for 3 critical questions. The first is how to capture the thread context without rewriting the whole application. The second is where to capture this thread context so that only the critical section is captured. And the third is, does the waiter thread modify its context while the server is executing the waiter's critical section? So we answer this question, and the solution is basically to reuse all the registers that you have, and you do a context switch. So how to capture the thread context is basically like you save and restore all the general purpose registers, the instruction pointer and the stack pointer. So you are moving the thread context just before executing the critical section and just after finishing the critical section. And does the waiter thread modified context? No, because when you are a lock waiter, you are just busy waiting to acquire the lock. So during that time, you are not touching your own state. So the waiter thread is not modifying the context. So you can safely transfer the context of the waiter thread to a server core. So putting it all together, so TC lock is basically a queue-based design, which is similar to queue-spin lock, and all the list of waiters are maintained as a queue. And it supports locking in different contexts, including tasks, IRQ, and NMIs. And there is a server thread that batches each waiter's request. And whichever thread is at the head of the queue will become the server. And this role will be transferred to the next waiter after some threshold. So currently we have implemented a counter-based threshold, but we can also have a timer-based threshold. So this is how it works. So you have a queue, and whenever a thread called a lock function, it will do 3 steps. First, it will save the context, which includes saving the instruction pointer, stack pointer, and general purpose registers. Then you join the queue by doing an exchange operation on the tail pointer. And the thread, which is at the head of the queue, will become the server. So now what the server will do is it will context switch to the first waiter, and then it will execute the critical section of the first waiter. And finally, in the unlock function, what will happen is it will context switch again back to the server thread, and then the server thread will notify the waiter that your critical section is complete. So then the waiter can context switch into its own context, and then it can start executing the non-critical section.
Where is the server running?
Sorry?
Where is the server running?
So server is one of the lock waiters. So the first waiter in this queue will become the server, and the rest will become the clients, which will send the information to the server. So the first waiter in the queue, when it acquires the lock, it will become the server, and then it will process requests from other clients.
Wait a moment. So the first waiter becomes the server.
Yes.
So and then 5 other waiters come in and throw their requests over. So you basically inflict the work of 5 other contexts to the context which happened to be the first waiter.
Yeah.
And how is that working? How is that supposed to do latency constraints? Not at all. You inflict the whole problem onto the unlucky thread which got the first which got to be the first waiter.
Yes. So like
and that's really not acceptable. That can't work, because if you have, especially in the case where you have a lot of contention coming in, then you slow down this poor first victim thread into I can't make progress mode, which might make loose deadlines or whatever it's looking for, and it makes the problem way worse for the scheduler, because if it's a spin lock you're talking about, then it can't even schedule out while doing that. So this is, and for if you want to substitute other lock types like mutexes or something like that, then it gets even worse, because the server can be scheduled out. So everybody else is going to to spin. No, it can't. They can't spin. I mean, they can try to spin, but if the server goes out for lunch, then you have to put the others to sleep, and you have the same wake up problem with which you have with regular mutexes too. So I'm not convinced.
So in the case of mutex, what we do is we check the need resced. Using the need resced, we check whether the scheduler wants to kick us out, and in that case, we will pass on the ownership to other thread. So we don't keep the context with locked ourselves.
No, you can't, because if you hold a mutex, you're preemptible by definition.
Yeah.
So you don't check need rescat.
Yeah.
You're not even asked. And then you get into another problem because you get scheduled out with the wrong context. Because you switch context in your server. So once it schedules out, you schedule out with the context from a foreign context, right? How is that supposed to work? Without messing up all the task state and everything. I'm not convinced.
Okay, so that is one of the points that I want to discuss. But the current so the context of a thread is defined by the current macro that you have, and currently we don't switch that macro. So when you schedule out the when the server thread is executing the client's critical section, when you schedule out, the scheduler thinks that the server thread is being scheduled out, and there is already the client thread which has gone to sleep because it knows that the server will execute its critical section. So from the scheduler perspective, it is thinking that there is one client thread and one server thread, and when it is scheduling out the server thread, it is just scheduling out. It doesn't know about the information that the server thread is executing client thread. So yes, we have to somehow fix that, but yes. So that is the current implementation that we have.
Okay.
Oh, I'm asking. Oh, yeah. Okay.
We can give it back to you in a second.
So what kind of application are you using to work? Hello?
Yeah.
Yeah. So what kind of application are you using? It doesn't seem like quite bit applicable in general. I mean, I've seen you publish papers about this.
Yeah.
So I mean, just curious, what kind of scenarios must be some workload that actually allows you to boosting performance?
So we observe like performance gains with like Willet scale benchmark, and also like you have workloads like Metis and these kind of things, where level DB, where we saw like good performance improvement. So like wherever you have like high contention, this will help. But at low contention, we will show that the overhead of context switch negates the performance improvement that you get with keeping the shared data in the level 1 cache. So at 2 and 4 cores, we perform very bad. But like after 8 and 16 cores, once you have enough beta threads, you can bash and you can get performance benefit.
I have a question. So each of the context node contain information like all the register. So its size will be architecture dependent, right?
Yes, but usually
and
like
maybe may also be dependent on which, even within the same architecture, different generation of CPU may have slightly more information you need to keep track of, right?
No, so it's ISA dependent. So in the ISA, you just need to save like for x86, there are 6 general purpose registers that you need to save, and plus instruction pointer and stack pointer.
So are these context node per CPU variable, just like the
Yeah, these are the CPU registers. So these are
And-
the registers that are switched when you context switch from one task to another task. So we are using the same thing.
And how big will be the log itself?
So lock is 32 bits. So it's the same as QSpin lock.
Okay.
Yeah. So because the log does not need to contain the node, so you have this per CPU node which is allocated.
Yeah,
and
I know
the
that.
node will have
Yeah.
like a slightly bigger size. So node size will increase by like one cache line because you have to store this information. But the lock itself will not increase in size. So the lock itself is 32 bits. Yeah.
Thing you talked about moving large data in locale sections over. How is this avoiding it? I don't see that because depending on what you're doing inside the logs, the actual move data which is protected is not that big, but you could copy a big chunk of data which is on CPU 4 or even on a different Numa node, and then you switch over to the poor sort who got the server, and he has to track 16K of data over in order to run the critical section. I mean, this is not going to help either. So there's I mean, it looks good on paper, but I think there are very many open questions which.
So to answer your question, we have a Numa aware policy where you don't transfer the context of a waiter across Numa nodes. So you only transfer the context of a waiter within a Numa node, and you pass on the lock ownership to another thread in a different Numa node.
But even on depending on the size of the data you have to transfer within a Numa node, it's going to be a horror show depending on
Yeah, so you have to
the architecture.
So let's say within a critical section you are accessing something in the stack, then you have to prefetch the stack variables and these kind of things. So
No. Look at critical sections in the kernel, especially mutexes or reader-writer semaphores or stuff like that. I mean, they do a lot of data movement out of a local context into some global thing, or right in a device or whatever. So you have 32K local data to write out to disk. So you have to copy it over from CPU 4 to CPU 1, and that's going to cross or might cross an L3 boundary, but it definitely crosses an L2 boundary.
Yeah.
Which is definitely way slower than if you have to move the stupid cache line over for the lock itself and the five bytes of something which protects the IO context. So it's you can't generalize this thing because it massively depends on what the locks are protecting.
Yes.
So you're completely right about the fact that this probably won't work for all of the cases. But in the case where so the point that you raised before about the latency of a particular request increasing, right? Because you batch everything together in the context of a single thread. So that thread is paying the cost for everyone else who is trying to execute the critical section. So in that case, if you have a case like that, this is probably not a good idea to use. Similarly, if you're pulling data from other cores inside your critical section, this is probably not a good lock to use. But if you have a case where basically the same data is being accessed from within the critical section, this might help with the performance compared to a normal QSpin log or something like that.
I'm not completely saying this is impossible, but I'm trying to understand what is the actual possible use case, and does it justify the complexity what comes with it. I mean, you also have, if you switch the context, you switch basically to the other context stack. That means you operate on the foreign stack, which is completely in the other cache line, in the other L2. So you have to drag that over, and especially in order to do something on the stack on top push stuff. Or if you have to access something which is deep on the stack, you drag that over too.
Yeah.
So there's a very interesting thing where you get a massive negative trade-off of that operation. And the larger your data sets get, the worse it becomes. And the larger your critical sections become, you have similar problems, especially, and this one concerns me most, or not most, but it's one of my main concerns, is that you inflict the latency on a random victim.
Yeah.
How do you do priority inheritance on that? The answer is not. So it might break.
So you're completely right about that point, but basically, like you could construe a case where you have these worker threads, right, which are not in the latency critical path, and which are the preferred waiters that get the ownership of this combining phase. And then everyone who's coming in from the latency critical path trying to take the lock can basically send the request to these threads which are owning the lock and combining it on behalf of everyone else. So you're right about the point about the latency critical part, but there are ways to do that if this really applies and helps in a particular situation. So that is what, yeah.
Thomas, I mean, you have a loud voice.
It's not the problem. So the real world use case is the critical question. But let's continue on your other issues you want to demonstrate.
Okay. So yeah, so let's see what we changed in TCLog to have it working in the Linux kernel. So we have to handle like whether the waiter thread is really being modified in the Linux kernel or not. What about per CPU variables? How are we handling nested locking? How are we handling out of order unlocking? What about mutexes? And what about reiter semaphore? So let's see how we handle these things. So as I've said that the waiter thread is not modifying during the context, but there are external events that can modify the waiter's context, like interrupts or whenever you're calling the whenever a thread is going to sleep. So the solution is basically to have an ephemeral stack, which is basically an empty piece of memory, which you switch during the critical section. And then the interrupts and the waiter's sleeping and wake up mechanism can use this ephemeral stack. Also, Linux uses a lot of per CPU variables, which you have to access within the critical section. And the kernel assumes that sometimes per CPU variables needs to be stable within the critical section and outside the critical section. But with TCLog, since you are moving the critical section to a different CPU, we are breaking that assumption. But is it? So as long as we are running in a certain context within the Linux kernel, we are not breaking that assumption. So in the spin lock code is written in the kernel in such a way that if you run a real-time kernel, all the spin lock will be converted to mutex, especially the spin lock _t. So if you have to have stable access, you have to use raw spin lock _t, or you have to disable IRQs, or you have to disable migration. So we check this condition before running the server thread and the client thread. Otherwise, if this condition is satisfied, then we fall back to QSpin lock. So in our log design, we are doing combining as well as we are keeping the QSpin lock the same. For like in certain context, you run QSpin lock, in certain context, you do combining. Apart from that, like kernel also uses nested locking, where you have like multiple levels of locks. And in the issue with the issue with TCLog is that when the waiter thread completes its critical section, it has to go to the server thread. But now, since you have 4 different unlock functions, how do you know which server thread to return to? So we use a solution similar to the interrupt processing mechanism, where when you have nested interrupt, when you go to the second level interrupt, you save all the context of the first level interrupt, and then you process the second level interrupt, and then when you go back, you restore the context of the first level interrupt. So here we do the same. So when the first thread, when the first server thread executes and it checks that it is time to execute a nested lock, it will save all of the information that it requires on the stack. And when the nested lock completes, then you can return and then you can restore all the parent server thread and then you can continue. So this is how we are handling nested locking. And this was an interesting one. So I didn't know that Linux kernel also have out of order unlocking. So this is basically means that if you have lock A and lock B, you can unlock the locks in any order. So you can unlock A first or you can unlock B first. And we have seen like multiple examples in the kernel where it is unlocking the locks in different orders. So the issue with TC lock is that here when you are returning to a server thread, if you return to a server thread with a different unlock function, then you are breaking the assumption that, let's say, you lock A and lock B, and you run a critical section, and then you unlock A first, and then do something, and then unlock B. So the code between unlock A and unlock B needs to be protected by the lock B. But in the unlock A, if you return to that function and give the ownership to some other thread, then the issue is that you are breaking the assumption that the code has written it with. So the solution is basically to track the lock order and you delay the unlocking of that lock until the point that the order is correct. So basically the order should be the same as how the lock has been unlocked. Apart from these things, we have also implemented the mutex. So the difference from Spinlock is that instead of saving the nodes and the state of the server thread on the per CPU variable, we save it in the task struct. And the rest is similar to that what you have in the Linux kernel, except currently we don't support mutex lock interruptible and killable. But we have to think about what we can do to support those things. Otherwise, currently the mutex lock interruptible and killable works the same as mutex lock.
How do you protect the case where I do migrate, disable, and lock a mutex, and then access per CPU variables? It's going to explode. Even the spin lock case is going to explode if you get an NMI. Because you need to switch, you would need to switch GS base basically to the foreign per CPU information, because that's where the context comes from. So assume spin lock. The spin lock case is easy. So you have, or in a context where you have this preemption disabled already, then you access a per CPU variable or get the pointer to it, which is GS based.
Okay.
So now you lock the lock in that data struct and go over to the other side. So you need to, then you either need to convert it into a linear address, or how do you do make sure that if the context function accesses a different per CPU variable, that it actually accesses it on the remote CPU, because otherwise you modify it on the CPU where the server is running, and then you get inconsistent state.
So
an NMI will explode right away.
So in case you have preemption or migration disabled, you wouldn't do the combining. That's the trade-off basically. If you're calling mutex lock, spin lock, suppose you're calling spin lock in a context where you have migrate disable, at that point the code after that really expects that the per CPU access will be stable, right? It has already disabled migration. So then you don't send over your critical section to the other side. You don't have to, you cannot do combining. Okay.
Cannot combine on any spin lock because a spin lock on a regular non-RT kernel is disabling preemption and you're gone. So, and then you have the issue that the per CPU variable access has to be stable. So, so how do you access the remote CPUs per CPU variables? You can't, because your GS base is wrong. If you switch to the other CPU's GS base, you mess up the complete per CPU state. And the spin lock health section can be interrupted. The spin lock health section can be interrupted by an NMI. You can take whatever other exceptions, and those assume that GS base is local. So it won't work.
So so the idea is that so as you said, on a non-RT kernel, this will be a spin lock where it disables the preemption. So you cannot do this. But the same code should work on an RT kernel, right? So the invariant is that if you're just calling spin lock, you cannot assume that preemption is disabled inside the critical section. So for a normal code path, suppose you're in the task context and you take a spin lock on a non-preempt RT configuration, like you will disable preemption, you'll run on the same CPU. But this same code should work on an RT kernel, right? So as per the API's contract, there's no guarantee that preemption is disabled.
The problem I'm trying to describe is you take a spin lock and your context gets migrated from CPU 1 to CPU 0. So then the function runs and does this CPU read. So which CPUs per CPU variable is it reading? CPU zeros or CPU ones?
So if it does get combined, then it will read the remote CPU's data. But whenever you're doing per CPU access, you do disable preemption, migration, etc. Okay.
Right. You have a spin lock. We talk about non-RT kernel. It disables preemption. This spin lock transfers the context over to some other CPU, from CPU 1 to CPU 0. Then the function runs, and the function does this CPU read. Then does it read from CPU 0 or from CPU 1?
So it reads from CPU 1, where it is run. Because when you're doing the spin lock call, right? At that very moment, there is no guarantee that you'll keep running on CPU 0, right? You could be scheduled out and run on some other CPU.
No.
Like before and after the call, right? Inside the critical section, like the preemption is disabled on a non-RT kernel. But before that, it's not disabled. The API contract of spin lock.
How do you read? You run in the critical section on
Yeah.
CPU 0.
Yeah.
You call that function, which does this CPU read. So how do you read this CPU, the per CPU variable on CPU 1?
We don't. We read it as if you're executing on CPU 1, because in some sense that threads.
It has to run on. It has to read from CPU 1.
CPU 1 is the one
It's the one which queued it.
Okay.
And you have the server running on 0. And now you run the
I see. I was confused about CPU. I thought,
So
okay.
0 is the server.
Yeah.
1 is the contender.
Yeah.
It ships the context and the function pointer. Now
Okay.
the function pointer is executed and it does this CPU read.
Yeah.
So how do you make sure that you read the data from CPU 1?
We don't. We read data from CPU 0.
Wrong.
Okay.
Wrong.
But
and you can't fix that problem.
Okay, but we'll probably try to explain you why we think it's right in the hallway. So I hope.
But this is a serious problem, and it can't.
Yes.
It's unfixable.
Yeah. But we'll try to explain why we think it's correct for the specific case we're talking about after the talk.
It might be correct for a particular use case, but it doesn't get correct for the general case.
No, but I was going to actually just say the use case. When you're saying the use case that you're saying, which I agree would blow up, but the problem is, I'm thinking, where do we have it where you're doing per CPU variables and you have a spin lock and contention on multiple CPUs for per CPU variables? Usually, which, yes.
No, from what I can see, there are a lot of critical section that one code not just to on the protected data. They also want use some auxiliary data from elsewhere. They are not supposed to be protected, and those auxiliary data can contain per CPU variable.
Right. That's opening up per CPU.
Yeah.
Because you have per CPU. Sorry. You have per CPU data and you want to write that into or transfer that into some global queue or something. So you need the lock, which is global, and then you rely on your per CPU data being stable. So, but if you run on if you ship it over from 1 to 0, and 0 looks at CPU data as 0, then the whole state is confused. So that's just, I'm looking at it from semantic point of view, and not from, oh, we made it work for a particular use case.
So what you're saying is completely correct, but the way we make it work, we'll try to explain it to you after the talk once this is over, or probably in the Q&A. Yeah. If we have time for
If we have 5 minutes, okay. I will just skip this. Let's go to some evaluation numbers. So here it's the same benchmark that we had, and we had like a lower critical section execution time, and we have like better throughput because the critical section execution time is lower. And at 2 and 4 cores, we are losing performance because of the overhead of context switch. But as you have like more waiters that are contending on the same lock, then then TC lock shines, and then it has like better performance. And also, like we did a small nano benchmark where you have a hash table, and you are each thread is updating and entering the hash table, and it is serialized by a global spin lock. And we can see that the throughput is increasing after like 8 or 16 cores, and the 99 percentile latency is also decreasing because every critical section that you execute is smaller, so the overall latency to execute will be faster. So it's batching is helping in this case because you cannot execute a critical section in parallel. You have to execute critical section sequentially. So if you can reduce the time you are spending in the critical section, the overall latency will improve. Sorry?
The average latency might improve, right?
Oh, this is the 99 percentile. So like if you have, like say, a high batching count, the worst case latency will increase, but the 99 percentile latency will decrease because only one thread will suffer out of like, let's say, 1 million requests.
Sure, I agree with that, but there are people who are concerned about worst case latencies very well.
I agree. Yeah, but I think the Linux also does not guarantee the worst case latencies for QSpin logger.
Ask networking people. They are very concerned about that.
Okay, yes. So yeah, so that was the first question for discussion. How do you set the batch count? So basically, there is a trade-off between throughput and latency. Second is like how to handle like performance regression that you have at low contention at basically at 2 and 4 cores. So with TC lock, we have shown that you can have combining and QSpin lock in the same lock mechanism. So we are also working on like having different lock mechanism which you can switch on the fly based on whatever contention you have. So you can have like a test instead lock, QSpin lock, a combining delegation or something else, basically running inside the kernel, and they are switching dynamically. And also currently, like as you have seen, when the server thread is running, it is executing different waiters critical section. So the server thread is eating up its own time slice to like make like because it is executing like waiters critical section. So how do you do like correct accounting for this? So this is a similar problem that you have for interprocessing, but we also have to fix it for TC lock. And also there is one more issue of the current macro. So basically, how do you fix this current macro? So when you are running on the server thread, you have one current, and when you are running on another thread, you have another current. So when you move the critical section to the server thread, if you are using the server's server's current, then it can lead to privilege escalation or other kind of bugs.
Funny enough, current is a per CPU variable.
Okay. Okay. Yeah. So yeah, that's it from there.
I was just waiting for this slide.
Okay.
Okay, I
Yeah.
think we're out of time. Thank you for this talk. I mean, you got first-hand feedback and discussion,
Yeah,
live
thank
running
you.
commentary. Excellent.
Yes, I think it's a lot of interesting questions.